Ladies and gentlemen, love Othel Wells, a great teacher and a great scientist. We're ready to
start.
start and to hear you.
Just before Athol, we will have a video and just 1 minute of welcome.
The European Respiratory Society is the largest scientific and clinical organization in respiratory medicine in Europe, with a growing membership from over 160 countries. Bringing together healthcare professionals and other experts working in respiratory medicine, united under a collective mission to promote lung health and alleviate suffering from respiratory disease. Advocating to reduce the burden of respiratory disease in Europe and producing science and unbiased education to share with healthcare professionals worldwide. We seek to tackle the current challenges in respiratory medicine across 8 respiratory disease groups. At the heart of everything we do are our members and our patients. Promoting funding and helping to drive scientific research through a variety of activities to advance respiratory medicine. Funding vital research projects, recognizing excellence, sharing and exploring new findings, and publishing one of the world's leading scientific journals in the field of respiratory disease. We create unbiased medical education and continuing professional development under the leadership of world-renowned experts in their field, harmonizing the standards and practice of respiratory medicines across Europe, helping thousands of healthcare professionals to improve their medical knowledge and skills, offering access to the highest quality online materials, and publishing learned educational journals and handbooks. We share knowledge, promote collaborations, and best practice through ERS events and conferences. Increasingly investing in the latest technology to make cutting-edge education accessible and affordable to healthcare professionals worldwide. Across the 2 pillars of science and education, we are dedicated to encouraging researchers and healthcare professionals to improve their skills, increase their knowledge, advance their careers, and ultimately improve patient care. Our leaders and dedicated officers advocate for change in Europe on behalf of the Society by raising awareness of lung health issues with politicians and the public. ERS and European Lung Foundation work closely with the EU and related institutions to ensure policies are based on science and patient needs. Through ELF, we work with patients, understanding their needs and hopes, involving them in research and guidelines, and supporting their active role in decisions concerning diagnosis and treatment of lung disease. ERS and ELF come together to provide support and information for patients, raise awareness about key issues affecting lung health, and campaign for healthy lifestyles and the prevention of disease. Each year, we host the largest gathering of respiratory professionals in the world at the ERS International Congress, a showcase of excellence for respiratory medicine. It's one of the world's major platforms for the release of new data. Additionally, giving access to live sessions and recordings to tens of thousands of virtual delegates, sharing new thinking and inspiring the respiratory community. The ERS International Congress is an essential ingredient for the advancement of respiratory medicine. The European Respiratory Society, supporting its members in advancing respiratory medicine and improving patient care, offering access to the highest quality unbiased medical education to all healthcare professionals around the world, raising awareness of unmet research and educational needs, and promoting lung health to meet the needs and hopes of our members and our patients worldwide. The European Respiratory Society. Every breath counts.
So I would like to welcome you with this European Respiratory Society video in Heraklion, not because I am an officer of the European Respiratory Society, but also I think that through the society we are all together here in Heraklion from all over the world. And I really thank you so much for this, that you have accepted this invitation from our department, which is very, very active with all other departments in Greece and also within European Respiratory Society. And from the bottom of my lungs, I wish you a nice 3 days in Heraklion, and I dedicate this event to our patients who are here with us, and they will cover a special event on Saturday night, and particular thanks to ERS, European Lung Foundation, and all of you, my colleagues from the University of Crete, my colleagues in the department, Professor Tzanakis, Professor Schiza, and of course, all of you who are here today live. Thank you so much. Athol, the floor is yours.
Athol, do we really need the new classification?
Thank you. It's truly a pleasure to be here, but there will be a short interlude while I work out how to load these slides. Is there anything I have to do? I can see them on the screen, but they have yet to appear. So I thank you. That's very good. So this is a very interesting topic, and it's an honor to open this school with this talk. And I'm going to launch directly into the key question. What does justify the creation of a diagnosis, a syndrome, or a classification? And I think it's useful to start with pragmatism. So this is William James, a leader of the pragmatic philosophy movement. Every way of classifying a thing is for a purpose. So you look away from theoretical principles and you look towards consequences. And William James took the view that the art of being wise is the art of knowing what to overlook. And I think he would have overlooked many parts of our current classification. So practical value. That's what classification is about. And we can break it down into two goals. Clinical utility. This is from a clinician, radiologist, pathologist, combined view of disease. Clinical utility. So a classification separates entities based on the natural history and treated course. It tells us what to say to patients. It tells us how to manage patients. And then an entirely separate goal, a classification separates disorders based on pathogenesis, so you can develop new treatments. And you can't cover both goals in a single classification. So I'm going to say we need two classifications. And I'm going to separate out these goals in the talk that follows. So let's start with what we have and consider the way the specialty was leading up to the millennium. It was an underdeveloped field. We had steroid therapy and very little else. And as is appropriate in an immature field, there had to be agreement on how one should think. This is not a criticism, but a necessity. So correct thinking was dictated by a very small group. And this amounted to an opinion hegemony. in which judgments were made as to how to view ILD. And make no mistake, these were not evidence-based judgments. Our whole evidence base is constructed on these precepts, and they were eminence-based, the Illuminati of ILD. And in particular, it was taken to be axiomatic that every individual diffuse lung disease must be viewed as a separate entity with separate pathogenesis. So diagnostic splitting was the only acceptable approach. And it's very interesting to contrast this with COPD. Same eminence-based approach, lumping. You mustn't separate. So one group of Illuminati went for splitting, one group went for lumping, and our whole evidence-based structures were set out at that moment, and in each field it became unscientific to take an alternative view. And then we know how diagnostic splitting played out. I can sprint through this section. Separation of IPF with the conceptualization of the underlying pathogenesis, epithelial fibrotic rather than inflammatory fibrotic, and the resulting classification that we've come to know and love, the idiopathic interstitial pneumonias. They're seen in its latest iteration in 2013. It's in the process of being reviewed at present. Now, I think you've got to acknowledge 30 years of scholarship. And one thing this classification does do is separate based on perceived pathogenetic pathways. So you do have a framework. You can study pathogenesis in relation to individual diseases, and this will deliver you disease-specific therapies, such as tocilizumab in systemic sclerosis lung. So it has pluses. And agreement on IPF, it gave us our trials. I don't think we would have had antifibrotic agents at this moment without this sort of initiative. However, there is clearly a problem with clinical utility, because our classification, and I amalgamate IIP with classification in ILD at large, because when you use the IIP classification, in the differential diagnosis is always such entities as hypersensitivity pneumonitis, occult connective tissue disease. So the problem is that these entities don't fit neatly to outcomes. And you might think that IPF does. Surely every IPF patient progresses. But as you well know, there are major subgroups in other disorders that have IPF-like progression in spite of management. And then within diagnoses, there are radically different behaviors, and I'll come back to that. And then there's the terminology problem. How many individual disorders are contained within the following terms? Now, please don't answer that. And if any of you get it right, you should be getting out more often. That's all I can say. But the answer is there are 4 disorders with these conflicting terms. And so this is jargon that disenfranchises patients, and it disenfranchises specialties other than the ILD specialty. So just the confusion between bronchiolitis obliterans and bronchiolitis obliterans with organizing pneumonia has confused specialists around the world. And when the terminology changed, it took 5 years for that to filter through to the medical literature. And these separations don't have concordance with what we do about our diseases. We have hundreds of ILDs, but in terms of management goals, we have just 5 disorders. So I ran an experiment nearly 8 years ago. So this was an autoimmune summit in Prague, mostly rheumatologists plus some immunologists. And the IIP classification had been applied to CTD for well over a decade, with a lot of publications. And I simply asked this question, and 350 people answered this electronically. So they were given 4 options. How do you rate the IIP classification? And I'm talking about the specialty that would know the most about this outside ILD itself. So I won't ask you to guess because I have answers. So 43% of this audience thought that the classification was basically hopeless. And 30% thought that it was somewhat hopeless. 17% thought it was somewhat useful. And 9% plainly had psychological disorders because they felt this was going to be easily understood by patients. So what do we do when we're confronted by a disease process? I said we have 5 disorders. What can we do? We can leave it alone because it's self-limited and it's going to go away, especially if we find a trigger. We can leave it alone because it's past history. There's a footprint left behind from something that happened earlier. There's some damage, all right? There's some often limited fibrosis. We can try to remove some or all of it. If we can't do that, we can try to stop it getting worse. If we can't do that, we can try to slow it down. And so this leads me neatly halfway through my talk to the alternative approach to ILD classification. And just as a break, I'm going to give you a well-known stress test, just to make you nice and relaxed so you can concentrate for the second half. And this was a study that was very highly regarded. You're about to see identical dolphins, and I want you to study the picture you're about to see very, very carefully, because it's been shown in this most impressive study that if you see differences between the dolphins, you are in great need of a prolonged holiday. So I want you to be ready to concentrate. You ready? And there you are. Now, the point I want to make here, you can split these entities. At a single point of time, they have a different pathogenesis, but their disease behavior is identical. So you get the point. So the disease behavior classification came about by accident a long time ago in a galaxy far, far away. A certain individual was asked to provide, quote, guidelines for ILD, just one side, please. And what they got was one side with 35 pages of footnotes. But you can describe ILD management based on just one side. You categorize likely disease behavior with 6 bits of information I'll come back to at the end, and then you manage accordingly along the goals. So that was the start of the disease behavior classification in 1997. Now, at the time, it was developed for the thing that we called IPF. IPF hadn't been separated as it was subsequently. You know, it became separated officially into a number of other categories, including NSIP. And so it became obvious that what we called IPF had a number of different disease behaviors, and that was the start of the classification. And it eventually became applied by some people to the whole spectrum of ILD. So that was the latest iteration before it was upgraded. And don't go into this in detail. You still have IPF categories used, which wasn't right, but listed on the slide are a great many individual disorders that can have a number of different disease behaviors along the lines that I'm going to show you. It was 2 IPF based, but note, you had what we called PF-ILD or PPF set out as the 4th category, inexorably progressive fibrosis. Acronym, IPF, I suppose, inexorably progressive fibrosis. So initially an IPF subgroup classification didn't include stabilization because at that time, the view was that IPF always progressed. The moment fibrotic NSIP got separated out, it became appropriate to include this. And there were some embarrassing features, explosive ILD, which of course matched with acute exacerbations, but a bit embarrassing in a chronic disease classification. So what was needed above all was not a classification for observed disease behavior, because you've got to wait for the disease behavior in order to use it, but a classification for anticipated disease behavior. And I come back to these 5 things you can do for a disease, and from this, the 5 entities that we have. Reversible and self-limited. When this got taken up by the classification group, I actually wanted the first 2 categories to be leave it alone. So reversible and self-limited and stable with residual disease. Doesn't matter. You've got the 5 categories. Reversible disease, and each of the categories has a logical treatment goal, and each of the categories has a logical monitoring strategy. And you will notice, especially before I go on to this slide, the last of these categories, present since 1997, is progressive irreversible disease despite therapy. And that was conceptualized further in this statement. I haven't seemed to have highlighted the reference, but the statement in 2018, a perspective from a working group of 33 international leaders, setting out subgroup behavior in each of our other diseases that has the hallmark of IPF progression in spite of management. What do I mean by that? Progression generally over 6 months to 2 years, in spite of our traditional therapies. I think you would say a major minority in other diseases. And just to focus on this very briefly, fibrotic idiopathic interstitial pneumonia, I want to highlight the first series by the late, great Pepi Lazzi. And what you will see is survival in a group of patients that had either biopsy-proven IPF, there's UIP mentioned on the slide, but that's what it means, biopsy-proven IPF, or biopsy-proven NSIP. Now, what you're going to see is outcomes from a year of follow-up. And you're going to see separations based on, firstly, is it IPF or NSIP? And secondly, have they progressed in that year or not? And you'll see DLCO, but the answer was identical for FVC. And what you see is that if you have progressed, maybe I'm confident enough not to plunge the room into darkness and I'll be able to use this pointer. Can you see anything? No, you can't. Well, anyway, the 2 lines doing badly are the patients that progressed. And if they had, it really did not matter in the slightest whether they had IPF or NSIP. There were less NSIP patients that progressed, but if you did, you had the same outcome as IPF. And if you hadn't progressed, once more, it no longer mattered whether you had IPF or NSIP. You had a better outcome. And there were a series of studies in different disorders, including rheumatoid lung, scleroderma lung, hypersensitivity pneumonitis, but they all amounted to the same message. Across these non-IPF disorders, serial FVC was the surrogate for mortality, exactly as in IPF. Across the disorders, the baseline severity, this should not surprise anyone, I think, was a separate driver of a worse outcome. The difference between UIP and NSIP mattered at baseline, but in every study where this was separated, they no longer mattered. This distinction no longer mattered once you knew about disease behavior in the next 6 to 12 months. And whatever you did in these cohorts, and in our two studies, they were certainly treated cohorts, an FVC decline predicted higher mortality, and it didn't really matter what else you did once you had an FVC decline. So we come back to the disease behavior classification. And I think I'm not too far away into moving to my closing slides, but just let's now think in 2022, what else we can add to this. So the self-limited entities were always important. They're now really important because of ILAs. And we need a structure to understand how best to view ILAs, and they fit neatly into the two self-limited categories. If disease is reversible and you get a response, we can think in terms of the inflammatory fibrotic model, with good data in some diseases that if you get an initial response, that gives you a much better long-term outcome. And then the key distinction we now have, especially if disease is irreversible, is stabilization as against the recent agreement on an entity that progresses in spite of management. All our fibrotic patients present with progressive fibrosis. That's why they present. To have PPF as a defining term for a sort of 30% subgroup is actively confusing, but that is what is meant by PPF or PF-ILD. So I think I'm going to close in my remaining 4 minutes and 30 seconds into, first of all, integrating the two classifications. They're complementary. We don't have to have just one. One is a splitting classification. The other's both lumping and splitting because you're bringing together entities, but you're making distinctions, so it's not pure lumping. And currently, we start by managing by splitting, and when splitting management fails, we manage by lumping. But we do need to integrate. I'm going to do a little sidestep here. In about 2004, from memory, in renal medicine, they changed the classification because the terms were highly confusing. They weren't understood outside the specialty, and their separations didn't fit with natural history and treated course. And they flipped over to a simple classification based on amount of structural damage in the kidney, amount of functional damage, and change over 6 months. Their great regret, they got much more grants because for the first time, people outside their field understood what they were talking about. But their great regret was discarding histology. And that is something we mustn't do. And to make this point, I said I'd come back and tell you what items one should consider in separating out disease behavior. And the histospecific diagnosis is very helpful because it tells you what patterns of disease behavior are possible. If you know it's IPF, you know it's category 5. If you know it's HP, any of 5 patterns are possible. And that applies also to drug-induced disease, and it applies also to CTD, ILD. So those are the things that you need. There isn't time to go over this in detail, but it's anticipated disease behavior. And note that observed disease behavior is just one of 6 things, but if you have that with time, the classification becomes stronger. And patients understand this. When I talk at patient days, I often get the comment, when you talk about what you can do about disease, there are 5 categories. It's as if a light has been switched on. And I think it's helpful. We do this in our multidisciplinary meeting. We make a traditional diagnosis and we make a disease behavior diagnosis. Now, there's nothing more killing to a patient other than death itself. There's nothing more killing than to be told that you've got unclassifiable ILD. And I don't say that. I say we've got a diagnosis of the likely disease behavior. And if they push, I say, we're not quite sure of the trigger of this, but it doesn't matter because we've got a logical management. So in conclusion, we must have a classification of anticipated disease behavior because this tells us what to say to patients and what to do. It's like the traditional classification. Sometimes you know the answer, sometimes you have differentials of disease behavior, and you work that out with the passage of time. The strength is that it becomes stronger the more you follow the patient, but we have to hold on to decades of knowledge because our traditional classification will continue to drive advances. So we need a new classification and we need the old one. Thank you.
Thank you very much, Alfred, for your excellent talk. Questions at the end of the session. Okay, thank you.
We have to proceed to the next lecture by Bruno Crestani. I'm not sure if he is connected from his office. Bruno?
Demosthenes, do you hear me? Hello?
No.
Demosthenes? Do you hear me?
Okay, good morning from Heraklion, great Bruno.
Hello, Demos. So, thank you very much, all of you, and really apologies for not being in Heraklion. It was a bit difficult this year to come to Crete end of June. Hopefully, there will be a 3rd session, and we will be able to come to Heraklion. So thank you very much for organizing this.
Particularly week for you in August for vacation.
I will tell everyone. Yeah, yeah. No. Okay. So thank you so much.
It's pioneer work, and will talk to us pathobiology of IPF from bench to bedside.
Yes, thank you very much, Demos. So I will, hopefully you hear me. I don't see you, so I suppose you hear me. So I will, sorry. Yeah, I have some disclosures. So idiopathic pulmonary fibrosis, you heard a few minutes ago for Professor Attol-Wells and his unique perspective over 25 years of history in the field of interstitial lung disease, where we understand that we need an whole classification because it helps working on pathophysiology, but we need also a clinical-based classification, which is highly understandable for the patients. And we need, as physicians, to combine both to make the progress for the future generation. So this is idiopathic pulmonary fibrosis currently. It's based on HRCT and clinical data and some biological data. In most of the cases, I don't use lung biopsy, and we will discuss later with Venerino the surgical lung biopsy, the cryobiopsy, and the biomarkers that could help us avoid the biopsy. Anyway, it's very useful, as already told by Professor Wells a few minutes ago, to have biopsy because it helps understand the disease, but obviously this is not a daily basis. So where the disease is beginning? The disease is beginning here in the peripheral lung, where the epithelial cells, the endothelial cells, the alveolar macrophages, and the fibroblasts or mesenchymal cells come together. They speak together in the normal lung, and they certainly speak together in the disease lung, and particularly in the fibrotic lung disorders. We understood, and I understood, idiopathic pulmonary fibrosis and in general fibrotic lung diseases when genetic came, because genetics are coming from human beings. They don't come from mice. And clearly, it sets the stage to understand fibrotic lung disorders and particularly idiopathic pulmonary fibrosis. Currently, in the last 20 years, we made, I would say, two very important steps to understand the disorder. The first one was to understand that mutation in surfactant protein genes were able to associate with fibrotic lung disorders with very different histopathology. The same mutation, UIP, NSIP, desquamative interstitial pneumonia in young and old individuals. So one etiology, different histological pattern, but also clearly illustrating that a disease initiating in the alveolar epithelium, where these genes are specifically expressed, was able to induce all these different histopathological patterns associated with pulmonary fibrosis. Second step was the identification 10 years ago of a mutation in the telomerase complex, which were associated with pulmonary fibrosis, again, with different histopathological patterns and different age of disorders. However, this allowed us to make a clear link between aging and lung fibrosis, and particularly aging of the alveolar epithelium. This is very helpful, I think, and we killed millions of mice, but I think the most important information we got came from patients. And so telomere dysfunction allowed us to introduce the concept of alveolar stem cell failure as a basis for lung fibrosis, injury to alveolar epithelium, repair after injury, and exhaustion of alveolar epithelial stem cells, leading to the accumulation in the abnormal lung with a very abnormal extracellular matrix of aberrant epithelial cells, some of them with an alveolar bronchiolar phenotype, which is highly abnormal in the distal lung. Some data suggested that telomere attrition was associated with mitochondrial dysfunction, and some groups suggested that this was a key point in the pathophysiology of fibrosis in the lung. But clearly this allowed to make a link with cellular senescence being central to the pathophysiology of idiopathic pulmonary fibrosis, but probably also with other fibrotic lung disease. And the third major step, which again was made 10 years ago, was the identification of what is probably the major genetic risk factor for pulmonary fibrosis, which was MUC5B promoter polymorphism. Interestingly, again, this promoter polymorphism with an allele at risk for pulmonary fibrosis was first identified in familial pulmonary fibrosis, but later on associated with sporadic idiopathic pulmonary fibrosis, but then also shown to be associated with non-idiopathic pulmonary fibrosis. This is very interesting because genetics allows us probably to understand most of the pulmonary fibrosis disorder we are seeing in the clinic. Most, but probably not all. Why MUC5B? This is unclear at this time. This polymorphism is associated with an increased expression of MUC5B, which accumulate in the abnormal alveolar spaces, in the highly modified peripheral spaces in the fibrotic tissue. This has been so associated in mice with abnormal mucosal area dysfunction, and this could promote an abnormal interaction of the epithelial cells with pathogens in the lung, but clearly we don't know if this is the key link between MUC5B and pulmonary fibrosis. But this is interesting because beside telomere maintenance, besides surfactant, some genes associated with inflammation pathogen response have been clearly associated in the humans with the development of pulmonary fibrosis. Clearly, these gene variants are absolutely rare, but they are associated. And remember, some of these pathways have been associated more recently with a COVID-associated pulmonary fibrosis. Genetics can help also going for new hypotheses. For instance, this very recent GWAS data identified genes, polymorphism in genes which are associated with the mTOR pathway, some new associated with telomere dysfunction, and some polymorphism in genes which are associated with mitotic cell cycle intracellular processing, suggesting that again, the proliferation of epithelial cell was being targeted with these genes. Interestingly, however, this very recent study showed that using polygenic risk score, despite the relatively large proportion of disease susceptibility associated with genetic signal, IPF is highly polygenic, with potentially hundreds unidentified variants associated with disease susceptibility. So the general scheme we have does not tell us everything about the pathophysiology of fibrotic lung disorders. Many gene variants are being involved, probably. So the IPF pathogeny currently very basic. I would say it's a scheme for children. An individual is susceptible to pulmonary fibrosis because of aging and genetics. His type 2 cells are exposed to noxious agents, drugs, virus, tobacco, etc. And these abnormal type 2 pneumocytes experience endoplasmic reticulum stress, mitochondrial dysfunction, senescence, allowing for the production of pro-fibrotic mediators. And this will drive the fibrosis, and the abnormal mesenchymal cells will produce abnormal factors, which will then with a normal extranormal matrix, which will make a vicious circle. This is very basic. I'm sorry for that. Obviously, abnormal macrophages with a profibrotic phenotype accumulate in the lung and can contribute to this pathophysiology. And the mechanical structure associated with breathing might also contribute to this vicious circle. What about, this was for IPF. Is it okay for a general UIP pathogeny? I think we can add here autoimmunity and inflammation and keep this pathway. And I believe it can work for most of the UIP pathogeny we identified. And again, there is a shared genetic susceptibility in disorder where UIP is quite common. But what about the non-UIP lung fibrosis? We have probably to think broader and consider that beside epithelial cells, there could be other cells being involved in the fibrotic process, and particularly the endothelial cells, which have been poorly studied until now, and because they are difficult to study clearly, could be involved in the pathophysiology of non-UIP lung fibrosis, but this has still to be clearly demonstrated. Interestingly, this basic and very simple pathogenic model fits quite well with the progressive fibrosis phenotype, which has been identified a few minutes ago by Professor Wells, where indeed autoimmunity, inflammation, direct injury to epithelial cells or to endothelial cells could be the initial trigger of disorder. And then this process being driven by abnormal epithelial cells or other cells here might drive the disease in the final phase, but could be shared across disorders. I will give you now a few recent data from our lab. In this abnormal crosstalk between epithelial cells and fibroblasts, fibroblast growth factors have been considered to play a role in the last 20 years, I would say. A few words for non-experts in the room. The fibroblast growth factors, it's a big family. In fact, there are 22 fibroblast growth factors with 7 subfamilies, but I would say the most important family is here in blue, which are the canonical paracrine fibroblast growth factors, which are secreted. The endocrine growth factors, you see there are only 3 members. And the intracellular fibroblast growth factors, their role is poorly known, poorly studied. We have data, and there are many data in the literature suggesting that fibroblast growth factors are very important for embryogenesis and lung homeostasis. This fibroblast growth factor, they interact with cells through 4 tyrosine kinase receptors named FGFR1, 2, 3, and 4. And for each receptor, there are 2 splice variants. One is expressed by the epithelium, the other one by mesenchyme. And interestingly, these FGF receptors, they require a co-receptor. It can be alpha or beta fibroblast growth factors, or heparan sulfates, which are at the cell surface membrane, which help bringing the fibroblast growth factor to the receptor. And they are very important for the biological efficiency of the fibroblast growth factors. In general, we consider that paracrine FGFs, the canonical FGF, exert anti-fibrotic effects, but it has been shown also that some of them promote fibroblast migration and proliferation, suggesting that they could be pro-fibrotic in some conditions. And interestingly, looking at the cells where the receptor is expressed, the role could be different. For instance, the mesenchyme-associated fibroblast growth factor are required for fibrosis development, whereas the epithelial-associated fibroblast growth factors are required for efficient epithelial repair and are anti-fibrotic, in fact. And consider this molecule. We are clinicians. We are treating lung fibrosis currently with nintedanib. Nintedanib is a known inhibitor of FGFR1, 2, and 3 tyrosine kinase activity. It is not active on FGFR4. So this is quite interesting, but because it indicates that currently we are inhibiting fibroblast growth factor receptor, which are anti-fibrotics when they are expressed on epithelial cells. I will focus now on endocrine fibroblast growth factor. 3 endocrine growth factors, FGF19, FGF21, and FGF23. The role of this endocrine growth factor is poorly known and poorly studied in the field of pulmonary fibrosis. Why? Because they are not expressed in the lung. They are expressed in the gastrointestinal tract for FGF19, in the liver for FGF21, and the bone for FGF23. So you will tell me, what is the link with the lung? You will see there can be a link. In fact, we focused our attention on FGF19. FGF19 is named in the murine ortholog of FGF19 is FGF15. This fibroblast growth factor, as I told you, is expressed and produced in the gastrointestinal tract. It is very important for glucose metabolism. It's a key metabolic player. And the receptor, the main receptor of FGF19 is FGFR4 and requires the beta-klotho as a co-receptor. This is very important because it has been shown that this axis, FGF19, beta-klotho, FGFR4, is anti-fibrotic in the liver. And currently, some companies are developing analogs of FGF19 to target liver fibrosis. So we ask a very basic question: is FGF19 also protective anti-fibrotic in the lung? So we first measured FGF19 in patients in the plasma, and we were very interested to see that this level of FGF19 was reduced in patients with idiopathic pulmonary fibrosis as compared to control, age-matched controls, and particularly in the most severe patient as compared to GEP1 patients. And we decided to overexpress FGF19 in mice using an associated adenovirus. You take this adenovirus, which expresses FGF19, and inject it intravenously. It comes to the liver in mice, and it is secreted by the liver into the blood. And then, through the blood, it can go to every tissue, particularly the lung. In fact, this worked quite well. We inject the adenovirus in mice, and 14 days later, we injure the mice with bleomycin, a very used model of lung fibrosis. And we sacrifice the mice 14 days later, meaning that the mice were receiving FGF19 since 1 month before being sacrificed, 14 days after injury. Interestingly, this model allowed us to increase FGF19 in the blood circulation of animals. And this FGF19 was detected in bronchoalveolar lavage, particularly on day 14 after injury. And you note that there is no FGF19 being detected in the blood in the control mice. And the mice are protected. If you give FGF19 in animals, you protect them from the development of pulmonary fibrosis, and the control mice received an adenovirus which overexpressed green fluorescent protein, which is not biologically active. obviously. And you see here that there is less injury, less collagen content in the mice which were treated. And how did it work? It was associated with a decreased apoptosis of alveolar type 2 cells in the animals receiving FGF19 adenovirus as compared to the animals receiving GFP adenovirus. So meaning that this factor, when given to the animals, were protective on epithelial cells. So what this is very basic, and if you want more, you can go to these recent papers which is available online. What does this shows? This shows that there could be a link between FGF19 being secreted outside from the lung, coming into the circulation, and being anti-fibrotic by targeting alveolar epithelial cells. And indeed, this suggests that there is a GI-mediated, FGF19-dependent, anti-fibrotic shield, an endocrine kind of anti-fibrotic shield for the lung, protecting the epithelial cells, but also, I don't have time to show this, which was able to modulate fibroblast differentiation. Does FGF19 in mice go through FGFR4? We did some experiments to study that, and will not go into the detail, but no, this is not linked to FGFR4 expression in the lung. In fact, probably FGF19 is protective for other FGF receptors, particularly 1 or 3, which are being targeted also for FGF19. We also explored FGF21. We don't have enough time to go into the details, but we have data indicating that indeed FGF21, which is normally produced in the liver and is increased in the plasma of patients with idiopathic pulmonary fibrosis, is protective in experimental models of pulmonary fibrosis, suggesting that besides this GI-mediated anti-fibrotic shield, there is also a liver-mediated FGF21-dependent anti-fibrotic shield, which is endocrine again and protective against lung fibrosis and working through a protection of alveolar epithelial cells against induced death. So this is, I think, something quite new. We are currently exploring further in patients because the evidence comes from experimental data in animal models. But again, we should think globally. The lung is not alone. Our patients are global patients, obviously, and there is an anti-fibrotic shield for the lung coming from elsewhere. So with this, I will finish. I will thank everyone in the group who are contributing this study. And as you can see here, you see Dr. Irini Vasarmidi, who spent some time in Paris last year, and we really enjoyed Irini staying with us. Thank you very much.
Thank you very much, Bruno, for the nice talk. We have a big progress in the pathogenesis of fibrogenesis. I wonder when we'll have a unified theory of fibrogenesis, like the unified theory of the world. How close we are.
Do you want me to answer now, or should we go to the end of the session?
It's better now. It will be free.
Yeah.
After that.
No, we don't let them feel free. He will stay.
Okay, Katerina ask you to stay. Not...
Oh, I will stay. Obviously, I will stay. Yeah, no, I think you saw my suggestion, but I believe that there is a common trunk, a common pathway for lung fibrosis over the different etiologies. And this is why our current antifibrotic drugs are slowing the fibrosis, and we have good evidence for that now, I believe. Probably there could be some different pathways at the beginning, and this is why I told you that we have good evidence for UIP, and considering that maybe most UIP comes from an epithelial damage. But for an SIP, I'm not sure, at least the important NSIP we see in the clinic, for instance, in CTD-ILD. But you saw that if you consider just surfactant gene mutations, which are specific to type 2 pneumocytes, it has clearly been shown that the histopathology can be very different for the same mutation. UIP, NSIP, desquamative interstitial pneumonia. So there are commonalities, it's clear, and but I think there is still work to come.
Okay, thank you. We'll proceed to the next speaker.
So we now have a radical change in theme when my slides eventually arrive. Thank you very much. So intriguing title, and I could give you a 4-hour talk at this point on this title, but I decided to focus on lung function. And I'm going to give you lessons down the years. I've basically gone through and thought about what I've learned in lung function and the things I wish I'd known at the start. Now, looking at the audience, I rather suspect that a lot that I'm going to say will be rather obvious, and I apologize for that in advance. But if just one person walks away with insights that took me far too long to get, it will be worthwhile. So I'm going to actually touch on 3 topics. First of all, 3 questions you should ask of lung function when you see a lung function sheet in a patient with ILD. What we can say about lung function and disease severity with regard to prognostic evaluation, and lung function and monitoring progression. So rapid interpretation of lung function. This is just a personal algorithm, but it will be very similar to many personal algorithms in this room. Starting with the total lung capacity, are the lungs big, small, or somewhere in between? And then, as part of the first question, characterizing the ventilatory pattern as restrictive, obstructive, or mixed. Now, some people seem to believe that ILD is always restrictive, and they couldn't be more wrong. Now, it's traditional to show flow volume curves. This is a normal flow volume curve. I will make this quick when I see people in the room. I think I'll just wait till the door is closed because I can't even hear myself speak right now. Great, thanks. So that's a normal flow volume curve. This obviously is an obstructive flow volume curve. Note the reduced peak flow and the concavity of the curve. This is a restrictive curve with very rapid emptying and a very rapid fall in flow as the lung empties. And this is a mixed defect where the first part of the flow volume curve, the restrictive part, empties more rapidly, and you have a restrictive profile, and then the obstructive part empties much more slowly and dominates the latter part of the flow volume curve. Now, please note, we don't define these things on flow volume curves. They're merely for illustration, but a mixed defect ATS criteria, could you close the door after you, thank you. ATS criteria is airflow obstruction based on spirometry, but the total lung capacity less than 80%. Now, I've set this up to make an important point, and it's useful at this point to go to sarcoidosis. And this is a fairly large cohort of over 1,100 patients, and about 750 had ventilatory impairment. And you can see in those cases, about 40% had pure airflow obstruction with pulmonary sarcoid, about 40% had pure restriction, and 15 to 20% will have what looks like airflow obstruction, but when you measure the plethysmography, you find that it is mixed. Now, why does this even matter? Well, I think it's interesting that it's the mixed disease cases that have easily the strongest association with bad fibrosis on a chest X-ray. And perhaps that's not surprising if you have both bronchocentric and diffuse involvement. Interestingly, in this cohort, if you did define pure airflow obstruction and you took out the mixed cases, their survival was the same as the general population, and patients with mixed or restrictive disease had a mortality that was about 2 to 3-fold higher. Now, this turned out to be due to DLCO differences. And again, perhaps it's not surprising if you have pure airflow obstruction, then the total lung efficiency, the gas transfer, if you like, is quite close to the lower limit of normal on average. And if you have airflow obstruction, but it's mixed disease, you might as well have restrictive disease in terms of the DLCO. So I'll come back to DLCO, but before closing on this particular issue, in other forms of ILD, there are exceptions. In smoking-related ILD, in Langerhans, you can have airflow obstruction, but often the obstructive element is due to admixed emphysema. And mixed disease is frequent in some disorders, but not in IPF unless there's quite a lot of emphysema. You would think that if there's some emphysema, you would end up with mixed disease, but what seems to happen more often is that you get spurious normalization of the flow volume curve. But a mixed pattern should always make you think of hypersensitivity pneumonitis or a connective tissue disease. And sometimes you will find that the airflow obstruction is confined to small airways. So this is a flow volume curve in which the peak flow is normal. You have what is an initial restrictive pattern, but you have 1.5 liters of low airflow at end expiration. And I think that metric, what is your volume of low airflow, is a very useful marker of there is or isn't a major small airways component. Now, rapid interpretation of lung function, is the gas transfer appropriate to lung volumes? That's question 2. Keep in mind DLCO is a calculated variable. You're measuring KCO, carbon monoxide uptake, for a given unit. That's what you measure. You multiply that by the alveolar volume. The first bit, KCO, is very reproducible. It's probably more reproducible than FVC. VA is very noisy. And DLCO is noisy because you have the measurement variation of 2 variables. Generally, DLCO will be 10 to 20% lower as a percent predicted value than percent predicted FVC. I've given you a typical profile on the slide. So disproportionate DLCO reduction is going to be captured by the KCO. And an uncomplicated ILD, that's usually either at the lower limit of normal or slightly reduced. So if the KCO is less than 70%, everyone instantly thinks of pulmonary vasculopathy. Concurrent emphysema is equally a large driver of that. And just be very careful with subtle, diffuse interstitial abnormalities. I suppose pneumocystis is a good example, where lung volumes can be normal because there isn't really enough damage or, I suppose, stiffness of the lungs to reduce volumes. But gas transfer is the giveaway. And sometimes in very early acute lung injury, you will have normal volumes, subtle change on a scan, which is widespread, or in some forms of HP, and the gas transfer is disproportionately reduced. Now, in IPF, concurrent emphysema and pH are both fairly frequent associations with the disease, and that is why in typical IPF cohorts, you're not on average at the 10 to 20% lower. On average, you will often have the sort of profile in drug trials where you have a wider gap, in this case, up to 30% on average, because of these complications, associations in some patients. Do not use the FVC-DLCO ratio. This was invented by USA rheumatologists who'd never heard of the KCO. And because it is, my God, it's American, we've all got to use it. It's now compulsory in other American series in PH doctors, because you can't go against the American literature. KCO is very tight. KCO is more reproducible than FVC. The FVC-DLCO ratio has the measurement variation of KCO, the measurement variation of FVC, and the major measurement variation of VA. It's a noisy mess, and there isn't enough time to show you comparisons of the values of the two that I do have, showing the better predictive value against outcome of KCO versus the FVC-DLCO ratio. Happily, the last question is just one slide. There are limited data, but they do support this. So is PO2, be it at rest or desaturation, is it proportionate to DLCO reduction? Because as a general rule, in ILD without pulmonary vasculopathy, you usually don't see major desaturation if the DLCO is as high as 40 to 50% predicted. So if you see that, always suspect concurrent pulmonary vasculopathy. I'm not going to ask you to answer this because the audience, as I look around, is far too knowledgeable. I can tell you with a less knowledgeable audience, when I ask this question, I'm moving to disease severity, I will get generally some rather interesting answers. For some people, some reason, people always focus on the KCO. Not quite sure why. And the answer is DLCO. And you can do this, first of all, you can do it in two ways. You can look at the degree to which individual lung function tests fit against the extent of disease on CT, and you can examine prediction of mortality, and you get the same answers with both. Now, I don't have time to show you something like 8 different studies. I'm giving you a representative study in which DLCO, here you see, fitted against the extent of disease on CT, within this particular case, an R value of about minus 0.65, that you will see that it fits. In this case, it doesn't matter if disease is reversible or irreversible. It's a very old series. We were asking those questions then. And I think of all the studies I've been involved in, the only one that comes close, and that's such an old study that I'm refusing to actually cite the year. Too embarrassing. But the best lung volume with an R value of minus 0.57 got quite close to the DLCO value. Spirometry was miserable. FEV1 and FVC had R values of about minus 0.4. So against the amount of disease on a scan, DLCO rules the roost. And why does it the best severity measure? Well, I've given you CT, and again, in a variety of ILDs, And there will be outliers with smaller cohorts, and sometimes people limit disease severity. They're thinking about lung biopsies and outcomes. But overall, in over 80% of studies, DLCO best predicts survival. It also does sum the impact of everything that's going wrong. So it will add together the impact of fibrotic lung disease, the impact of emphysema, and the impact of pulmonary vasculopathy. So it is a composite of bad news in the lungs. Why is FVC a very, very poor measure of severity? Two reasons, and I will just dwell briefly on both. Firstly, it is completely messed up by associated emphysema. So when you have combined pulmonary fibrosis and emphysema, the TLC and the FVC that should be reduced in ILD are often spuriously preserved. Now, this seems weird. How can emphysema actually cause an increase, especially in FVC? It should cause an increase in TLC, but not FVC. But the answer seems to be based on VQ studies, that the fibrosis holds open the small airways and dead lung ventilates. So you get this spurious preservation of FVC, but a very disproportionate to volume reduction in DLCO, because that's driven downwards by both processes. This is just, again, the same very ancient study, where you can see that if you have emphysema, this one shows TLC, FVC much the same, until the fibrosis tends to be overwhelming in this cohort, with 65% of the lung involved. TLC values are preserved, despite the combination of two diseases. But this is an insight that follows that I really want to get across, because I wish I'd known this earlier. It's one of two things, and I'm going to spend the rest of my talk basically on these two things. Consider an FVC level of 75% predicted. Now, you don't know ever where the patient started in the 80 to 120% range, right? You don't know if they've lost 5%, 25%, or 45%. So there is a 9-fold variation in the amount of FVC reduction due to disease, a 9-fold variation, and the signal is 25% on average. So 25% signal, 9-fold variation. So that's a very, very high noise to signal ratio. Now let's consider DLCO, 50% on average. Now the reduction from pre-morbid values is 30, 50, or 70%. That's just over a 2-fold variation. And the signal is 50%. So just by virtue of the fact that it is dragged down much more by disease, you have a hugely lower noise to signal ratio. So that by itself would explain why DLCO predicts survival better. So I think the point here is that even with DLCO, you're really worried by the confounding effect of the normal range, aren't you? You're talking about an over 2-fold variation in an individual as to what that level might mean from where they started. And that's why you've got to be multidisciplinary, not in a meeting, but you should bring together CT and symptoms. And if, for example, you're getting far more symptoms and more disease on CT than you expect with a DLCO of 65%, we'll consider that patient probably had a personal normal of 120%. And so the real impact in DLCO is lower, so you adjust that. And always, always include DLCO in the lung function evaluation of ILD. Some people seem to be content with just doing spirometry. And I'm going to go back to sarcoid because that's the most neglected disease when it comes to full lung function. The statements often refer to spirometry. They patchily refer to DLCO. And prognostic evaluation tends to focus on whether you've got a stage 4 chest radiograph. So this has yet to appear. It's in its final form, but I'm going to show you what happens when you examine lung function against mortality in the nearly 1,200 consecutive patients presenting with pulmonary sarcoid. And you're going to see bands of abnormality in DLCO, more than 80%, 60 to 80, 40 to 60, below 40, and this is what you see. So with DLCO, there's a tipping point. And suddenly, you have a mortality rather like IPF in this cohort in about 13% of patients. So you are capturing the problem of danger in pulmonary sarcoid. And I won't bore you with details when you go through a very simple staging system, also integrating an FVC threshold. This is the separation you then see in outcomes in sarcoidosis. And once you know this, not much use paying much attention to chest X-ray stage 4. It adds nothing, it's relatively useless, although it does provide some separation in outcomes when considered by itself. That's the validation cohort in over 1,100 patients in Utrecht with what is a very simple staging system. The point I want to make, never, never, never fail to measure DLCO when you're assessing severity. Now, in my last 5 minutes, I believe, yes, I just had a nod from the chairman, always good news. I'm going to say something about lung function in defining progression because it is the single most reliable measure of progression as compared to symptoms and imaging. And there's no doubt, in spite of what I've said about the FVC being a lousy severity measure at a single point in time, mainly because it's close to the normal range, if you have change in FVC, it really doesn't matter about the normal range anymore. That's an equal confounder in the first measurement and the second measurement, and FVC is more robust. It's clearly also more specific to the interstitium than DLCO. And what I want to talk through, though, is what we use practically for what is called a significant change. And this tends to be, most often, a 10% change from baseline. There isn't time to go into various measures, but I'll start with that. And that's really the point, the second point I want to highlight. A change of 10% from baseline is often assumed to mean clinically significant change. It doesn't mean that. It's absolutely not the case. The 10% threshold is about measurement variability. So you have variability of the first measurement, variability of the second measurement. A 10% change in an IPF patient, there's not time to take you through the maths. The pre-monitoring likelihood of progression is also important, but a 10% change is 95% likely to be real. Even if it's something else other than disease progression, it's real change. And if you didn't have measurement variation, in a rather bad lung function lab, it would lie somewhere between 1% and 19%. With a better lung function lab, you're probably talking about 4 to 16%. So in an individual, this doesn't mean major change. In some patients, it's minor change. In some patients, it's catastrophic change, but it's about measurement variation. Now, again, I don't have time to show you the maths, but a 5% decline is 70% likely to be real and 30% likely to be measurement variation. So you need something else, either to take that up to 95%, or to, if the something else adjudicates that there isn't change, make the likelihood a lot lower. And that's exactly when you use a second variable, which might be DLCO change, separate measurement. I think the very confused guideline statement about DLCO is just going to create immense difficulty. That's how you use DLCO. And I'm nearly there. DLCO decline might be non-specific, but you expect it to get worse if there's ILD progression. So if you see it, it means a marginal FVC change is more likely to be real. And since we're going to have an imaging talk, I won't traduce serial CT at this stage, and symptoms are difficult. So let me just summarize in the last 27 seconds. So you see here that patterns of ventilatory impairment are extremely important in ILD. DLCO is clearly the best measure of disease severity, but the confounding effect of the normal range is critical and should always be considered. Both measurement variability and alternative causes for progression are obviously going to cause trouble with lung function monitoring. And so if you're going to use lung function well in defining severity or identifying progression, it's a multidisciplinary exercise. You need to integrate them with symptoms and the amount of disease or the change in disease on imaging.
Thank you, Vassalou. Great lecture, as usual. Then we can proceed to the discussion.
What? Yeah, that's right. So it was fresh in my mind.
Have some questions, okay?
Hi, Atul.
So,
Thank you very much for your excellent presentation, as you said, as usual. Thank you. Thank you very much. Look, I'm not a very good physiologist, but I had one of my first boss who was an excellent one, and we were used to do also the capillary flow and the membrane diffusion. And perhaps it's something to rediscover. What do you think about?
Yeah, I think it should be reappraised now that we know very much more about our ILDs. I didn't include it because right now I don't feel confident in using it. And it was very much a compendium of hard lessons I've learned. But I do think that that is a measure that should be developed once more.
And one more short question. Do you think in patients that are in the initial phase of a disease and do not have respiratory failure and they need oxygen, we can reconsider also the use or study better the use of cardiopulmonary exercise test?
Yes, that's a question that remains a question. So for a very long time, of course, we used cardiopulmonary exercise more routinely. And then it became apparent that you were very much getting the same information from DLCO, and you could supplement that with a 6-minute walk test. I think when it comes, though, to ILAs especially, it would be interesting, would it not, to have a systematic approach to maximal exercise testing. 6-minute walk testing probably will not show an issue in most ILA patients. But what that actually means in terms of disease behavior, which is the key thing in ILAs, are they going to progress? Are they going to remain stable? Isn't clear. So I do agree with you. I do that sometimes in connective tissue disease because there are so many causes of dyspnea to disentangle. And if you do a maximal exercise test and the patient doesn't desaturate, then you're able to say it's a very good negative predictive test that the dyspnea, which they will experience and limit them, is not due to cardiopulmonary limitation. It may be lack of fitness. It may be any of a number of other things in connective tissue disease. So I do think it's sometimes a helpful negative test to understand dyspnea, and especially if you don't get that understanding from a 6-minute walk test.
Thank you. As I have the microphone, can I make a question to Bruno? Okay. Bruno, do you listen to me? Do you hear? So first of all, congratulations for your excellent presentation and for your great work. Really very interesting. So thank you really and congratulations. My question is, are you also studying some genetic aspect in patients that develop COVID-related interstitial lung disease?
So as you know, there is a huge network looking at pulmonary involvement and severe pulmonary involvement with COVID. We had some connections with this network, but it's not so easy, I would say, to manage, because these are big stars in genetics. And we have one of our fellows is working in Jean-Laurent Casanova lab in Necker, and you know Jean-Laurent Casanova and Laurent Abel are the two among the people who identified the defect in the interferon response in patients who develop severe COVID. So we are connected. I hope we will have the possibility to have the data, but we are struggling, I would say. But yes, something is ongoing.
Freddie Manali is with us. If Freddie, have you any question? And then Argyris. We can't hear you.
I'm στο μικρόφωνο.
Yes, I did, but it didn't work. So good morning to everybody. Thanks to Professor Wells and to Professor Crestani for the excellent presentations. My concern sometimes is the early disease, not only the progressive fibrotic pulmonary fibrosis. I wonder sometimes whether we can approach this category of patients either through the classification or at the research protocols or at the therapeutic trials, because for me it is an aspect that maybe has a great impact in the management of those patients, because when the disease is already advanced, sometimes the options that we have are quite limited.
So I'm not sure if that's a pathogenetic question for Bruno or a lung function question for me. I'm going to assume it's a pathogenetic question for Bruno because I've answered it first. I can say something to you about lung function briefly when Bruno has said a great deal about pathogenesis.
Okay.
No, I think we have a unique opportunity with familial pulmonary fibrosis to look at early disease. And there are many groups working on this all over the world. And for our center, we are currently developing a cohort of familial subjects identified around one first case. So this is a unique window of opportunity to study pulmonary fibrosis at a very early stage. There are very interesting studies performed by the Belgian group of Wim Vuits, Laurent Sadler in Leuven, in collaboration also with Naftali Kaminski, where they look at the lung in the transplanted lung, where they look at the very severe area and some normally looking areas, considering that this could be a window to understand what is ongoing over time. Obviously, it's an hypothesis, but it gives interesting views of what could be the first step of pulmonary fibrosis, because obviously in most of these cases with very early abnormalities, in a case of familial pulmonary fibrosis, we don't have tissue. We will not go for lung biopsy. So this limits our understanding of what is ongoing. But this kind of studies being performed by these two groups are very interesting. I think this is a very important question, Efrosine.
Pepe, here Papakosta, you are with us. Do you have any comment on or any question?
No, they were all impressive talks. Good morning from me at first, and thank the three professors of the organizing committee to have invited me to co-chair in this session. I'm very sad I'm not here with you because of family health reasons. But really, all these talks were were excellent. I could have an answer to Professor Crestani, which is the future of this pathobiology of IPF you developed. When do you think we could have something more stable?
Practical, you mean? So as I told you, it is very interesting because companies are currently developing drugs which are targeting the endocrine fibroblast growth factors pathways in the field of liver fibrosis. So there is already an interest of these pharma companies to look at the lung with these molecules that they already developed, which are, for instance, stable forms of FGF19 or stable forms of FGF21. And so by ourselves, we will not do that. We will have to do that with pharma companies, but I would say at least two companies are expressing some interest in that, and we are collaborating. So it could translate into clinical trials in the future, but it's a bit too early today to say something more than that.
Yes, thank you. It was all this pathobiology was impressive.
I'm Venerino speaking. So good morning, Pepe. Good morning, Manali. Good morning, Bruno.
Good morning, Venerino. Nice to hear you. I cannot see you, but it's nice to hear you.
Thank you. I have questions for Bruno and for Athol. First of all, fantastic. Fantastic talks. For Bruno, the question is that in liver fibrosis, you have fibrosis. In pulmonary fibrosis, you have a huge proliferation of bronchial cells. So the question is that the culprit probably is the stem cell exhaustion, but the next effect is proliferation of bronchioles, typical bronchioles. Do you think that this could be part, and when it happens, I think it's too late to prevent damage in the lung. Do you think that this kind of plastic embryological proliferation in the lung should be more considered for the pathogenetic point of view? This is for you and for Apple. It was a fantastic talk regarding classification. Do you think that the list of risk factors that can predict behavior could be included in the classification?
I'll let Bruno answer first, so I have time to think about your question.
This is very interesting, and I have a slide which was given to me by Arnaud Mailleux, who was working with me. I would say I am working with Arnaud. Arnaud was first a scientist in the developmental field. He has a very nice picture of a fetal lung, and he put together the fetal lung on one side and the IPF lung on the other side. And you cannot say any difference. It is absolutely fantastic. So clearly, these developmental pathways are abnormally expressed in the fibrotic tissues and probably contributing to this abnormal epithelial cells continuously proliferating. And for instance, the Wnt pathway is involved here, is very important into lung development. Sonic hedgehog pathway, also very important. And fibroblast growth factor, evidently. It could be that these fibroblast growth factors coming from the plasma come to the blood, to the lung, and then stimulate this bronchiolar epithelial cells proliferation. But at the beginning, I told you was anti-fibrotic, but in fact could be pro by maintaining this abnormal epithelial cell survival. This is very interesting. Thank you for this very nice question, Venerino.
Venerino, I think you're asking me whether there's a big picture classification that might be helpful in pathogenesis. And if we separate pathogenesis into predilection, initiation, and then progression, and focus on progression, I'm going to suggest that you can, and that it's very like playing chess. So when you play chess, you have a king side attack, a queen side attack, you take the center, or you play a defensive game. Now, we have inflammatory fibrotic pathways and epithelial fibrotic pathways. And so our strategies, we need a classification that you're going to focus management on inflammatory fibrotic pathways, king side attack, epithelial fibrotic pathways, queen side attack them both at the same time and the right patients take the center, or actually observe and monitor, play a defensive game. So that's the strategy. The tactics are using the right individual drugs, just as they're using the right pieces when you implement a strategy. So choosing the right drugs with the right sub-inflammatory pathways, maybe you're dealing with acquired immunity, innate immunity overexpression or deficiency, and choosing the right drugs for the non-inflammatory fibrotic pathways. And every good chess player reviews their strategies. So you need the biomarkers that show the drug is working in the short term, predicting long-term efficacy. So I think you can devise such a classification. You've got to play chess, where you actually go for biomarkers for strategy, biomarkers for tactics, and biomarkers for are the tactics working. Thank goodness you gave me a bit of time to think about it.
So
That was a great talk, as always. Very inspiring. So I have a couple of remarks and one or two questions, depending on the time. So based on the classification, I know that we work a lot of biomarkers, and biomarkers have failed so far for prognosis and also for diagnosis. But we have made major advances in genetics, and it's kind of sad that we don't do not in terms of classification, but in terms of sub-classification, those genetics. And we know that
we know that MAC5B then predicts about 30% of predisposition of disease, and also have telomeres. We have telomerase mutation, and all these factors, they have to be included for a sub-classification of these of patients with IPF. And I'm not a big fan at the moment of changing the whole area of classification, but I think we have to move forward in terms of treatment, because we need biological enrichment of clinical trials. I mean, in the end, if we have a UIP pattern, then it's we can lump the disease, we can lump the treatment. But if we have patients that they have a relatively mild disease, or now with the ILAs, we need to better classify those patients for, prognosis and also for treatment response.
I did want to say something about that actually after Bruno had commented. So yes, first of all, one should separate predilection, initiation and progression. And no doubt in established disease, it will be helpful to do that. But Bruno cited familial pulmonary fibrosis as a great way to look at early disease. And I think the right term might be preclinical rather than subclinical in that subset. So for early disease, that's fine. And that is as distinct from ILAs, where you don't have very strong genetic determinants of outcome. I don't think we're at a stage where we can use that in ILAs in individual patients. And we do need biomarkers for disease behavior for ILAs, whether that will be genetic detail, whether it will be just short telomeres, whether it will be some other biomarker, but we desperately need biomarkers, I agree, to separate out a minority that are going to progress. And without that, we're going to get nowhere with trials in ILAs.
But that's why we need also tissue, because in lung cancer, we
Maybe.
have about 15 to 16 different variants, and they have subclassified lung cancer based on these variants.
I understand that,
found, like, different
but we don't,
types of treatment.
We don't necessarily know that with ILAs. We don't know, actually. I mean, in lung cancer, you have primitive clonal cells, and you have a much higher chance that biomarkers will drive outcome, that various receptors will. In ILD, you have a huge amount of homeostasis. You have upregulated ancillary pathways. I don't think we know that the cancer model works for ILD. It's thought to be politically correct that you are supposed always to say that. I think it has everything to be proved. So it may be right. It may be that tissue will do what it does in cancer, but we're not dealing with primitive clonal cells here. We're dealing with pathways that result in upregulation and downregulation of other pathways, and we have a tsunami of co-activated pathways. So the idea that a single measure, a single therapy against a single pathway cuts the web, I don't think we know that.
No, definitely not. And one question for Bruno.
Sorry?
And a question for Bruno. So thanks a lot for your presentation. Regarding your paper in the Red Journal, the FGFR19, you mentioned there is an axis with clotho gene, and clotho gene also plays a role in cell senescence. I was wondering whether you are you planning to make any genetic studies on the clotho gene and see if IPF patients, they have SNPs or mutations in the clotho gene, and whether we can identify a subset of patients that they may benefit from enhancing this axis?
Again, a great question, Marguerite. We have looked at in our IPF patients and in our RAILD patients. And currently, we didn't see something coming out, looking for polymorphisms. Obviously, this was a bit preliminary, but negative, I would say. The alpha and beta clotho story is not over right now. The data in the literature are more focused on alpha clotho, and the beta clotho has still to be evaluated in a better way, we believe. And for instance, it's quite interesting. We have preliminary data suggesting that beta clotho by itself in vitro has an effect. Maybe because there are already in some FGF being there and the FGF receptor being there. Then when you come with beta clotho, you have a biological effect. And interestingly, we measure this in the lung and in the plasma, and there are some interesting things. So I think this is something which has still to be worked on.
Okay, there is some discussion, but we have to stop. 10 minutes break. Okay. Come back.
So, good morning, everyone. It's a real pleasure for me being here among world experts in the field of lung fibrosis and interstitial lung diseases. And it's also, all of them are friends and good colleagues. And it's also a real pleasure to be here in Crete, where I studied. I did my major, so I feel that I owe a lot to this place and also to the University of Crete. And thanks a lot to the organizers, and particularly Katerina and Antoniou, for giving us this opportunity to be here and sharing with you important knowledge. And also to my co-chair, who is a very good friend and world expert in the field of ILDs, Professor Poletti, doesn't need a lot of introduction. So without any further ado, I'm going to move forward to the session. We have really important talks related to both imaging and histopathology. So the first combo talk, I'm not quite sure if it's going to be a debate. Hopefully it's not going to be a debate. It's going to be a combination of how a pulmonologist can interpret the HRCT and how a radiologist can interpret the HRCT. And I'm sure there are a lot of commonalities in the interpretation. So the first presenter is Vasilis Tzilas. He's a consultant, respiratory consultant in General Hospital of Sotiria in Athens. And is also a very active member of the ILD, the Greek ILD group, and a very good collaborator, and one of the very few pulmonologists that can interpret in that way the HRCT findings in ILDs. So, Vasilis,
απλά να βάλουμε την άλλη την ομιλία. Can we put the other talk because it's...
So we have, the program says, has first your name. So can we change the...
Μπορούμε να αλλάξουμε την παρουσίαση?
It's not...
Εκτός...
So, based on the schedule, is Vasilis first.
We are under the
okay. Set.
Can we put down the lights because they're going to show images, so it's better if we...
Okay. In English, sorry, not in Italian. Professor Poletti, unfortunately. So I feel really very honored and at the same time very humbled to give a talk as a physician about HRCT. I really want to thank Professor Tzanakis and special thanks to Katerina. Really thank you very much, Katerina, for giving me the opportunity to talk about a topic that I really love. And maybe one of the... You always act along the facilities. So because we have a lack of thoracic radiologists, and if someone is really into the ILDs, you have to develop such skills. So this is a clinician's perspective. And whenever I give a talk about HRCT as a clinician, I always use this picture of a Swiss knife, because actually HRCT is a Swiss knife. You always have it in your pocket. It can give you solutions to a variety of problems, not just in ILDs, but of course ILDs are a characteristic example. So the ideal ILD doctor, you have to be a pulmonologist, a radiologist, a pathologist, and to tell you the truth, for me at least, a radiologist is up there with the clinical skills. So, of course, this is not an exhaustive talk about HRCT and ILDs that can take not just hours, but days. This is the outline of my topic. It's actually a storytelling of my personal experience, and I tried to highlight specific points of how HRCT can help in real clinical scenarios. So, although this may seem trivial, like UIP or not UIP, I find that many of my colleagues, even radiologists, struggle with this distinction. So here we have two characteristic examples. We have the UIP on the right side, of course, where you see cysts, that they are clustered together. There is no normal intervening parenchyma, so the cell walls. But I want to highlight that the first layer is in total contact with the pleura, so there is no normal intervening parenchyma. And also see that actually the fibrotic process is working its way from the periphery to the center of the lung, while on the left-hand side, you see that you have a fibrotic process, but you have the infamous and very helpful subpleural sparing. So we have NSIP on the one side and UIP on the other side. And if someone wants to approach it from a clinical perspective, so both from a pathophysiology point of view and a biology point of view, I think that this is one of the most underrated papers and under-recognized from a certain Dr. Poletti, if you know him. So I think that it really highlights what is the distribution of disease. So we know that stress induces actually with a mechanical way the activation of TGF-beta. So when my residents ask me why you have this distribution in UIP, because in IPF you have the universal tendency of the lung to fibrose, and this will happen at the sides of the lung with the greatest mechanical stress. And with this elegant way, Professor Poletti shows that exactly this starts from the periphery of the lung and it works its way to the center of the lung. So this is a characteristic example, and you see that, unfortunately, I don't have a pointer. Anyway, and I can show it with a cursor. So you have a fibrotic process, you have traction bronchiectasis, but you see that there is this characteristic sparing of the immediate subpleural parenchyma. So this is an immediate, I think that we can all agree, this is a case of subpleural sparing. I can translate it from Greek, but I think that you all recognize UIP. So the report of the radiologist wrote this is a UIP type of fibrosis, which is definitely not the case. So in the general setting, it is not that easy. And with the universal lack of thoracic radiologists, I think that ILD clinician should have a very firm grasp of imaging. So this is what we wrote, and I have the privilege of writing it with Argyris, Professor Bouros, and Simon Walsh. This is a paper about what pitfalls are hidden in recognizing honeycombing in HRCT. And I think that it is really helpful to try and recognize if the first layer of cysts are in direct contact with the pleural. If it is not, then it is not honeycombing. Another important area that I would like to emphasize in this table is the case of smoking-related interstitial fibrosis. We see it all the time, and I don't know if it's the same in Italy or in the United Kingdom. This is honeycombing and this is UIP. This is definitely not honeycombing. And why? Because you see that the cysts, they are subpleural, okay, but they are larger than they usually are. They have much thinner walls, and you have these septations. So this is smoking related. And I think that we tend to put everything under the umbrella of CPFE. So this is not the classic fibrosis. This could be smoking-related emphysema with smoking-related fibrosis, but we don't know what is the natural history of this disease process. We don't know if just with smoking cessation this will stop evolving. And we should not overuse antifibrotics in these patients, and we should definitely not call them honeycombing and IPF. Now, with the subpleural sparing, This is, if not my favorite, one of my favorite signs, because I think it has great clinical values. Of course, this is not maybe the perfect case, but this was a case of a 62-year-old male with progressive dyspnea on exertion and canaris. I think you can appreciate on the left base the mosaicism and the fact that, that in the hyperlucent areas there is diminished vascularity, and you can see the fibrotic process on the right base that is centrally located. Of course, after 43 months, you can see the evolution. Personally, I still wouldn't call it honeycombing, the findings in the right base, but it's something that it's more resembling, maybe one could say that it could be IPF. So in order to recognize a pleural sparing, and I think this is an important point, always ask for previous imaging. So timing is important. You have to find the exact time phase in which you can see the most distinctive radiology pattern. And I think that, sorry, Professor Wallace, I have put also the year of the publication. Okay, and I can do even worse, you will see it. So this was really highlighted almost 15 years ago, that the patients with an NSIP radiology pattern, they can evolve over time in an imaging pattern resembling IPF. So the best and most useful, in my opinion, approach is ask if they have previous imaging. It can really help you, because at the end, it all looks alike. It looks like end-stage fibrosis. One other reason why I love subpleural sparing is depicted in this patient. So this is a 53 male. He had a biopsy, so even in ILDs, biopsy is not everything, and it shows us UIP. You see this concept that is that the paper by Professor Poletti really helps to conceptualize. You see fibrotic process, of course, you see traction bronchiectasis, but watch how the fibrosis, you can tell it starts from the center of the lung, it spreads outwards, not the other way around, and you see this characteristic subpleural sparing. Sorry, right in here. So it flowers outwards. It blossoms from the center to the periphery of the lung. So even if the pathology tells us that this is UIP, I know I would never say, even not knowing the age of the patient, that this is IPF. So it is one of these cases that imaging can, in terms of clinical diagnosis, it can trump pathology. And this was a case of seronegative rheumatoid arthritis. I'm always very cautious when I hear that someone has seronegative rheumatoid arthritis, and this was eventually proved to be MDA5 positive. But I think that from this case, the key message is that radiology can trump pathology in terms of clinical significance. Now, talking of CTD ILDs, there are some signs that we can see in a CT and raise suspicion of an underlying CTD ILD. So if you have extensive honeycombing, the official definition is that if fibrotic changes, that if honeycombing is at least 70% of the whole fibrotic process, they name this exuberant honeycombing. Like in this case, then think of a CTD ILD, mainly rheumatoid arthritis, and also when there is involvement of the anterior segments of the upper lobe, that in sagittal reconstruction, they create this four-corner sign, okay? I have talked with Professor Simon Walsh, and he told me, be cautious, of course, that this can be also seen in IPF. So we need larger cohorts. This was from a publication by Jonathan Chang back in 2018. I think that this sign is even more important, the straight edge sign. So when you have sharp demarcation between the fibrotic lungs and the normal lung, like here, this is strongly against IPF. And actually in IPF, because there is universal lung involvement, you want to have some involvement of the apices, of the upper and mid lung zones. When you have this sharp demarcation, this is strongly also evocative of an underlying collagen tissue disorder. And now, also moving on, what about traction bronchiectasis? So what is traction bronchiectasis? And I would love to have a poll about this case. So you have this patient. I'm not giving you anything else. Okay, I'm showing some traction bronchiectasis with the arrows. And I would love to have a vote. So is this a fibrotic ILD? Okay. Yes. So, because we have the best doctors in Greece, this was the outcome. So this is not a fibrotic ILD because it's a reversible fibrotic. It's an immature fibrosis. And I would love to hear the comment by Professor Walsh. Yeah.
Have some residual abnormalities actually done.
Yes.
So this is clearly a mixture of inflammation and immature fibrosis.
And exactly. Yeah. Hearing. So, Professor Walsh, hearing you saying immature fibrosis, it made my day. Thank you very much. So, this is actually indeed, it was in a series of cases with nitrofurantoin. Yes, so it is nitrofurantoin-induced lung toxicity. And I would like to apologize from Professor Walsh because this is not something new. And I challenge Professor Walsh to see what will be the next slide back from the 2000. So it was described already from the Brompton team back in 2000. So nitrofurantoin-induced lung disease, 2 cases demonstrating resolution of apparently irreversible CT abnormalities. I did not have access to the full text, Professor, but I think the images must be more or less the same. And with post-COVID. So, bronchiectasis, the official definition is pathological, irreversible, localized or diffuse bronchial dilation. If you have mature fibrosis, then this is called traction bronchiectasis. But I want to stress out that although it is not mentioned formally, the evolution over time is a key component in the diagnosis. So this is stolen from the Brompton. When I think that Professor Hansel used to show it in his talks. So actually, honeycombing is the most reliable thing to ensure us that we have underlying fibrosis. Traction bronchiectasis, okay, but not as much as honeycombing. Volume loss, just 1 star. And when we have all things together, we are much more certain. I would also add what is the course over time and also what is the clinical background. So if you have a patient in an acute or subacute phase of a disease, there can be reversible bronchial dilation. And I don't want to use the term traction bronchiectasis in this patient. So I will say that we have traction bronchiectasis, but we will have to be patient and see how it evolves over time. And as Argyris said, I think that post-COVID residual abnormalities, and I will not call them fibrotic, is a characteristic example. I think that it was overemphasized, the fact that this is traction bronchiectasis. So unless in the context of a chronic disease, avoid using the term traction or use it with with extreme caution. So I think, and this is my personal view, I think that morphology has to play a role in here. So when you have this curly, this corkscrew appearance, I think that in order for the bronchi to be that much distorted, then I would say that this is probably due to established mature fibrosis as the paradigm that I'm showing to you on the right. So another fun fact about HRCT is that sometimes you have the ability to recognize a 4th dimension, and this 4th dimension can be outside the lung, can be even outside the lung. So we have this case of apparent lung involvement, very mild bronchial dilation, mainly diffuse ground glass, some consolidation, irregular reticulation. But if you turn to the mediastinal window, I think that you will agree this is one of the brightest livers. So you don't need BAL in this patient. I know that it will show me foamy macrophages. I know that the patient is full of amiodarone. And for the disbelievers, okay, so we have a Hansfield unit of 90, so we know that this is amiodarone-induced lung toxicity. Another thing that I discovered in my practice is that HRCT actually, it's not something separate. It's like clinical practice and radiology. It all comes together. So it increases clinical suspicion. What do I mean with that? This is a case. I think that the imaging is very characteristic because you have consolidations, but it's distribution that makes the difference in this case. So you have a very distinct and peribronchial distribution. Personally, I've only seen this pattern in two diseases, in granulomatosis with polyangiitis and in drug-induced lung toxicity. So what is the interesting about this patient? When she was, when we asked her, do you take any medicine? She said no. And we were very, we asked again, and she said emphatically, I'm not taking any kind of medication. And then we asked specifically, do you take nitrofuradoin? And she said yes. And why didn't you tell us? Because it's not a drug. So I think that you all know that do you have pets? No. Do you have birds? Yes. This is a case of, do you take any medicines? No. Do you take Furolin? Yes. And this was the result not of some kind of illumination, but what the CT showed to us. And another case, and this was a case that we saw with Argyris about 4 years ago in Soteria Hospital, 64 male follow-up after pneumonia, thorough clinical examination. We saw these white dome-shaped papules in the forehead. We asked the patient, what is this? And he told us, don't bother about it. I'm a welder. I have a dermatologist. I have an allergic photosensitivity dermatitis because of my welding. Because of my welding. But if you look on, you clearly have a diffuse cystic lung disease. And look at the cysts. They're a bit floppy. This one is bilow. And on the right side, you can see that the cysts are in direct proximity to the fissures. And actually, in the right lung, the cyst is within the fissure. So it's as typical as it can get for Berthold-Dubé. Of course, how many Berthold-Dubés have you seen? At least in Greece, with Argyris, we have seen 2. So we noticed these papules, but after seeing the CT, in the beginning, we said, okay, he has allergic photosensitivity. When we reviewed the CT, we told to the patient, just in case, go and have a biopsy. Because in Greece, genetic testing is too expensive. And this is the biopsy, fibrofolliculomas. So HRCT and clinical practice, not two separate things. They are bound together and they help increase clinical suspicion. And I want to close with the point that, nevertheless, even though I love HRCT, it is not a panacea. So this is a patient of a 60-year-old female, never smoker, progressive dyspnea. You can see that there is a fibrotic lung disease. You have traction bronchiectasis. You have peripheral reticulation. There is some kind of mosaicism. I think that you agree. These are the traction bronchiectasis. I don't know if you would call it a 3-density pattern. I don't know what's your opinion, but I think that you can agree that there is a mosaicism. So this patient had an exposure to duvet. We did a biopsy, and it was sent to Royal Brompton, and Professor Andrew Nicholson wrote bronchocentricity, peribronchial metaplasia. I would equally consider chronic hypersensitivity pneumonitis, and that was our working diagnosis. The patient was put on steroids, but she did not improve. And looking thoroughly, we discovered some cracks in the radial aspects of the index fingers, and this was a PL7 positive patient. So sometimes HRCT can be misleading. And this is another case, 61 female, never smoker, progressive dyspnea on exertion. You can see that there is, again, a mosaicism. She had bought a canary 4 years ago. So when the pulmonologists hear about canaries, they already know the diagnosis. BAL lymphocytosis, 46%. Again, steroids, not improvement, JO1 positive. So this, I think, and I saw argues that you made the comment with Professor Walsh. This is, I think, one of the things in ILDs that needs special attention. We have described 4 patients with adysynthetase syndrome that were notoriously mimicking HP. These are the 10 reasons that allowed such masquerade. And the HRCT can play a role in this because it can show this diffuse mosaicism. And last one, I have discovered the best imaging sign of all times because it has 100% sensitivity, 100% specificity, and it is very consistent. So, this is the CT. If anyone wants to take a guess, this is where the sign is. Okay, so my observation, and I don't know if you agree, is that no matter how full the stomach is, you will always have this bubble, no matter how full the stomach is. So this is a testimony to the old saying that there is always a room for dessert. Okay, thank you very much.
We will have discussion at the end of the presentation or now? Discussion at the end or now?
We can do after the combo presentation.
Okay, okay. So now I think it's the turn of the radiologist. If nothing to say after this talk, probably Detorakis from you are from
Crete. From Heraklion, yes. Thank you. Dear Chairman, dear colleagues, ladies and gentlemen, I would like to thank the organizing committee for the invitation, especially Professor Katerina Antoniou. It is widely accepted that chest CT represents the workhorse of chest imaging, and there has been increasing frequency of chest CT being ordered the last decade due to the ever-expanding spectrum of the thoracic diseases and abnormalities. And let's go back to 1982. When, for the first time, Toto and colleagues described the term high-resolution computed tomography, and later on by other authors, focusing on the usefulness of chest HRCT imaging in the various pulmonary diseases, and especially diffuse lung diseases. Nowadays, multi-detector computed tomographers are almost ubiquitous, so this means that it is easy to find a multi-detector CT scanner, which offers, in case of chest thoracic imaging, a volumetric image acquisition of the lungs, meaning that we have acquired the entire volume of the lungs that can be obtained by using a submillimetric collimation, which means that we have very thin sliced images of 1 millimeter in thickness or less if possibly, no space interval between the various slices, and we have a very short rotation time and a high speed through the gantry. The gantry is, as you can see, this circular annular part of the scanner that includes the detectors, and through this the radiological table runs with the patient on it. So if the parade of the table is very quick, this reduces the image acquisition time and, of course, movement artifacts. From the moment we have received a volumetric image acquisition of the lungs, we then post-process these images with a high spatial frequency reconstruction algorithm that offers an exquisite detail of the lung parenchyma, which is really useful when studying interstitial lung diseases, and not only. Just in parentheses, I have put the sensitivity and specificity of HRCT in early detecting ILD. You can see that the sensitivity is much higher in contrast to the specificity. So we have an accuracy of around 80% in diagnosing ILD for the HRCT. In many centers, we do use an additional software in order to reduce the radiation exposure to our patients. It's called iterative reconstruction softwares. The fundamental scan is taken in supine position of the patient. The patient has been previously trained in order to receive images at end inspiratory phase, which is of crucial importance. We then post-process the images into soft tissue mediastinal window and also to lung window in order to see not just the lung parenchyma, but also other structures such as the cardiovascular structures, possibly presence of enlarged lymph nodes in the mediastinal stations and highly. The HRCT, of course, it's very useful in detecting diffuse lung disease, but of course we have to mention in a report the case of coexisting focal lung disease. So the volumetric data we have received can be furtherly worked in a workstation, external workstation, so we can achieve multiplanary reconstruction images from the axial plane to the coronal plane to the sagittal plane. Then we can have also the so-called maximum intensity projection reconstruction images that are really useful when we're detecting small nodules and also in cases of vascular diseases, such as, for example, pulmonary embolism. And the minimum intensity projection images really useful when we're studying the bronchial tree and possible presence of luminal or wall abnormalities. So, in cases we do suspect cases of small airways disease in our patients, we do an additional scan in expiratory phase. The patient has been previously trained in order to achieve end expiratory phase images. So the lung is scanned in a sequential manner, which means that we do not receive a volumetric acquisition of the lung in this case. We try not to receive and try not to expose our patients into more radiation exposure. So this is called a sequential scan in 3 or 4 different scans, in 3 or 4 different sets of scans of images, of thin sliced images. And in between these slices, we do have some slice interval of 10 or 20 millimeters in most of the centers. So in case we do have small airways disease, we have this classical image of low attenuation areas, usually in a patchy distribution in both of the lungs, of course. And in case we do suspect at our inspiratory scan subdural interstitial lung involvement, usually at the subpleural basal position, and we are not very sure if it has to do with reticulations or initial phase of ILD, we do perform a third scan, a prone scan of this area in order to discriminate. We were talking about the so-called dependent atelectasis or some early phase ILD. In this case, was proved to be early phase reticulations, so this patient has to be followed up in time. It's of basic importance to understand the anatomy of the lung, and especially the presence and the function, we can say, of the secondary pulmonary lobule. This is a classical appearance of the secondary pulmonary lobule that is practically circumscribed by interstitium. We have the perilobular interstitium in which run the lymphatics together with the perilobular veins. At the center of it, we have the terminal bronchiole and the intralobular artery. And all around these structures, we do have the centrilobular interstitium, and we have also the intralobular interstitium always inside the secondary pulmonary lobule. And of course, we have to know this in order to understand some basic findings of the HRCT. So the first approach in the pathway of interpretation of the findings in HRCT has to be the dominant pattern that we have to clarify. If this dominant pattern is a reticular one, is a nodular one, is of a high or a low attenuation one, it has nothing to do with the secondary pulmonary lobule. For example, can be the findings centrilobular, perilymphatic, perilobular, of a random location. Also, the distribution of the findings in total regard, for example, the upper lung fields, the mid lung fields, the lower lung fields. This can change totally our diagnosis. They have a central or peripheral distribution. So talking about a reticular pattern, of course, we mean the thickening of the septa with the intralobular septa, the interlobular septa. This thickening can be of a smooth or of a irregular appearance. In case of smooth appearance, the thickened septa can be attributed to other proteinosis, or in this case of cardiogenic interstitial pulmonary edema, or in case of nodular thickening of the septa, we can have cases such as silicosis, lymphocytic carcinomatosis, and of course, pulmonary sarcoidosis, such as in this case on your right-hand side. A nodular pattern can be seen, of course, in many cases. In this case, also to be clarified if it has a random distribution, such as in case of miliary tuberculosis. This is a classical appearance of miliary tuberculosis, or we may be dealing with hematogenous metastasis, for example, or in fungal infections. Can we have a centrilobular location, such as in smokers, for example, in case of respiratory bronchiolitis, interstitial lung disease, or in hypersensitivity pulmonitis, or a perilymphatic distribution, perilobular distribution, in case of, for example, sarcoidosis. This is a typical case of pulmonary sarcoidosis, all along the fissures with small-sized nodules, all of the septa. We have the thickening of the peribronchiovascular interstitium. What about now the attenuation, the density of the lung? So do we have high or low attenuation? We may have high attenuation patterns in case of ground glass opacities, and for ground glass opacities, we do mean the high attenuation areas of the lung parenchyma that they do not obscure the underlying vessels. This is of crucial importance to discriminate between this and the consolidative areas. The consolidative areas, of course, obscure the underlying vessels. On the left-hand side, we have a classical appearance of a HP. On the right, we have a classical image of organizing pneumonia, peripherally distributed consolidative areas. The low attenuation pattern can be attributed to air trapping and small airways disease, but not always. And if this is the case of 3-density pattern, we may have the low density areas that correspond to expiratory scans in air trapping. We may have ground glass opacities and also some areas of normal lung density. This is the so-called 3-density pattern seen in hypersensitivity pneumonia, but we may see low attenuation areas also in pulmonary embolism and chronic pulmonary hypertension. So low attenuation areas can be attributed also to cystic patterns such as honeycombing, most of the times in a subpleural basal predominance in clusters with thick walls comparing to emphysematic, for example, cysts. And it's the basic pattern of the UIP pneumonia. We will see later on some other slides to analyze it. In case we have a major pattern of ground glass opacity at the low lung fields, and we do or we do not sometimes have an underlying, for example, drug-induced reaction, or, for example, a connective tissue disease, we have to think of the cellular type of NSIP. In case we do have traction bronchiectasis together with thickening of the lung interstitium, intralobular and interlobular interstitium, this is a classical case of fibrotic NSIP, and with in a patient with scleroderma, small-sized nodules at the center of the secondary pulmonary lobule, at the upper to middle lung fields distributed. In smokers, most of the times we're dealing with respiratory bronchiolitis, ILD, always at the center of the secondary pulmonary lobule, and patients with underlying history of Bed-Fancer's disease, or, for example, exposure to dust, think of subacute hypersensitivity pneumonitis, and the combination of consolidative areas and ground glass opacities together may be seen, for example, in acute interstitial pneumonia, such as in this case of drug-induced ILD. The distribution of the ground glass opacities is of a crucial importance to identify if we're dealing mostly...
I'm sorry to interrupt,
yes.
but we have 2 minutes. So
2 minutes, okay.
Thank you.
So we have an upper lobe predominance in case of RBILD, NHP, a lower zone predominance in UIP, NSIP, and DIP, a central lobular distribution in case of HP, RBILD, and in case we have a perilobular distribution of the findings, try to think of organizing pneumonia. A peribronchial distribution can be seen also in chronic hypersensitivity pneumonitis, as well as in sarcoidosis. In sarcoidosis, we do see also some small-sized nodules all along the fissures, all along the septa, and bronchocentric organizing pneumonia can be seen in cases like polymyositis and dermatomyositis, and also the last 2 years we can see many cases in COVID-19 infections. So we have to understand if we're dealing with fibrosis or not. So do we have, together with articulations, traction bronchiectasis and bronchiolectasis? Do we have distortion of the lung structure, architecture? Do we have volume loss, loss of smooth air interstitium, honeycombing areas, or the so-called idiopathic pleuroparenchymal fibrinostosis findings? Yes, so we're dealing probably with fibrosis. Not all the articulations represent fibrosis, so many cases, like for example, pulmonary edema or lymphocytic carcinomatosis may have involvement of the interstitium. So we have to see these patients in consecutive scans. And in 2017, this is very important to report, the paper by the Flaschen Society underlying the discrimination between the various categories of the definite UIP, from the definite UIP to the alternative diagnosis. This is of crucial importance to know that we do have to meet in our diagnostic criteria the presence of honeycombing areas in the clusters, and together with traction bronchiectasis and bronchiolectasis at the subpleural basal predominance in the case of a definite UIP, and especially if we have the clinical spectrum of IPF. Of course, we have to pose this final diagnosis. It's not so difficult to do it. Probably UIP if we have all the above stated findings, except the honeycombing presence. And in case of the indeterminate UIP, we do not have this distribution of the findings. We may have some articulations, some slight retraction of the lung, but not this extent of findings. It's quite not so clear to our eyes, but we will see in the next slide why. Alternative diagnosis means that we do have other patterns than UIP. For example, mostly ground glass opacities, cystic patterns, nodular patterns, or hair trapping. So 1 year later came the American Thoracic Society, together with the European Respiratory Society and the Japanese one and the Latin American one, to clarify that we may have slight and mild extent GGOs in the case of probable UIP, and also underlines that the distribution in case of indeterminate UIP has to be, or at least most of the time, says subpleural and basal, and also add some additional findings regarding the alternative diagnosis in order to pose the final diagnosis. For example, the presence of pleural plaques in case of asbestosis, or for example, pleural effusions and pleural thickening in case of connective tissue diseases. So from the moment we have excluded the UIP, we have alternative diagnosis. So try to think, for example, GGOs, air trapping cysts, and peribronchial distribution in case of chronic high hypersensitivity pneumonia, especially if the underlying history suits. Or if I have mostly a GGO pattern at the low lung fields, especially with the subpleural subpleural sparing of the lung, try to think of NSIP, the cellular pattern of this NSIP. In smokers, ground glass opacities together with thin wall cysts. The desquamative interstitial pneumonia has to be at the top of our list. And also in smokers, small size nodules at the center of the secondary pulmonary lobules. Respiratory bronchiolitis, ILD, has to be also in our list, at the top of our list. In case of peribronchiovascular consolidations, try to think of the bronchocentric organizing pneumonia, and history is really important to pose the final diagnosis. In case of immunosuppressed patients, thin wall cysts, ground glass opacities and diffuse distribution, think of lymphocytic interstitial pneumonia. Sarcoidosis has been also referred in the previous slides. And last but not least, one word about idiopathic pleuroparenchymal fibrinostosis that, in contrast to what we were believing till now, this may lead to a significant volume loss in progressive CTs and to respiratory failure. And a great article by Professor Walsh and his colleagues in 2019, and thanks to these indications for some measurements in progressive follow-up scans, as HRCT scans, we can have adverse prognosticators about the volume loss, especially by measuring outer-sternal distance between the posterior surface of the sternum and the anterior surface of the inserting aorta, or the so-called oblique fissure retraction distance, or the craniocaudal diameter of the lung from the lung apex through the mid-clavicular line down to the level of the diaphragm dome. And last but not least, one word about artificial intelligence. It seems that we have many softwares the last years that have been released, but it seems that we have a long road to cross, since many of the, at least all of the softwares are not in the position to discriminate between the various interstitial lung diseases, for example, between UIP and other types of ILDs, and especially regarding the course to fine reticulation. Also, it's not at the position to discriminate or between honeycombing areas and emphysematous cysts. So the accuracy is still not so satisfactory and has been a high risk of bias in a review paper. So conclusively, HRCT plays an important role in the detection, classification, disease extent, calculation, and follow-up of ILD. We have to look for UIP firstly pattern, and even if we cannot assign a definite or probable UIP pattern, we have to look at described findings such as traction bronchiectasis, volume loss, PPFE, etc., and explain why if you're assigning indeterminate or non-UIP patterns, and look for history of the patient, clinical context, and clues for their underlying etiology. In order to increase the chance of a correct diagnosis, many times a formal multidisciplinary approach may be necessary. Thank you for your kind attention.
Thank you very much. That was a very extensive presentation. We don't have a lot of time, running out of time. So just one small comment for both of you. We're dealing with a lot of skepticism regarding the probable and the definite UIP pattern, whether they should be merged into one radiological entity. And there was also a session ATS saying whether it should be merged or not. I mean, I would like to hear your opinion based on the prognosis and the treatment response. Vasily.
Yeah, thank you. Well, I think that since they have the same significance in terms of diagnosis, in the recent guidelines, I acknowledge the fact that they said that the probable UIP pattern has a little less specificity for UIP pathology. But I think that if we also merge the concept of disease behavior, at least in my clinical practice, I think that for me it's the same thing. And sometimes there's a lot of debate and we start, and I think that we devote too much time to say, okay, so we have a clear image, peripheral basal distribution, and then we start arguing with radiologists. I think this is honeycomb. No, this is peripheral traction bronchiectasis. I think that it has no practical value. If you have excluded all alternative diagnosis, according to Professor Poletti's work with the peripheral bronchiolar hyperplasia, I think that since it is peripheral, it has the classic peripheral distribution, it doesn't matter.
Even if the patient is younger and has milder disease?
No, if he's younger than 60 years old, then this is a different clinical scenario. For the typical scenario of a patient that has a clinical background supportive of an IPF diagnosis, I think that for me it's the same.
Not the same for me. I do agree with what you implied. So in the right IPF age group, the prevalence of IPF to NSIP is more than 20-1. So if you have a CT appearance that might be NSIP, might be IPF, in the IPF age group, it will be very strongly predictive of UIP. But it's an 80 to 85% predictive value, even in those cohorts, not a 95% predictive value. And in younger patients where NSIP is relatively more likely, then probable UIP is probably not UIP. And in rheumatoid lung, the survival after controlling for severity in quite a large cohort was substantially better with what we call probable UIP than it was with definite UIP. So it's a confusing term that should be reserved to the IPF age group and phenotype.
Would you like to comment about what Vasily's presentation regarding the autoimmunity flavor in the HP CT? because I think it's a good.
Well, look, I'll make this very brief, but I have seen over the years quite a number of patients who both have an HP look and often with an antigen and autoimmunity. And I'm not sure you're right that the history was misleading. If you have a CTD, we know even when you don't have very overt ILD, you have DTPA clearance abnormalities, often an elevated KL6. So you have a predilection in the airways, and I suggest that if you have a predilection due to autoimmunity, you may be more likely to develop HP when you inhale an antigen. So I'm not sure your histories were misleading. I think you may actually have evidence of what is a combination of two disorders.
Okay, so we should proceed, although there are a lot of dilemmas and unanswered questions, but we have to proceed. Thank you. Thanks a lot for your wonderful presentation, both of you.
Yes, and now we move to the echo approach, and I invite Vasarmidi and Vassalou, I think, a radiologist. Are they here?
Yes, Irene is here.
Irene?
Amy will start? Okay.
Is online? Okay, he's not yet online. Okay. Okay, can you hear us?
Can you please unmute your microphone?
Ah, yes.
We can't.
You're muted.
Yes.
It's the echo. This is the problem of the echo, usually.
We can't hear.
What is happening?
Maybe her microphone got muted, or she has to reconnect.
Yeah. No, you are muted. We cannot hear you.
Okay, I have to leave.
Yes, now yes.
Yes, now we can hear you.
Ah, okay, a miracle, because I was unmuted. Okay, is it fine now?
Yes.
Okay, let's share the screen again. Okay, is it okay?
Yes.
Very good. So thank you for this kind invitation, and kindly excuse me for not being there with you. This is due to a current COVID infection, but I think you are going to enjoy this web lecture. So we are going to talk about the utilization of transthoracic lung ultrasonography in ILDs. Lung ultrasonography, and it's almost 30 years since Harrison referred that the lungs are a major hindrance for the use of ultrasound at the thoracic level, while since then the method was used only for the evaluation of pleural effusion. In 1994, Genta firstly described the presence of B lines in abnormal lungs. It was in 1997 when Daniil correlated this sign with HRCT findings. And this was the very beginning of lung ultrasonography, which represents a validated method for lung and pleural imaging. So nowadays it is well accepted that Harrison's statement is not fully true. Admittedly, in an aerated lung, nothing can be depicted deep to the pleura due to the presence of air. However, when subpleural segments are replaced by fluid, tissue, or interstitial pathology, several imaging signs, together with artifacts, can be depicted, allowing the differentiation between normal and abnormal. And talking about ultrasound, it is a fast, easily available, non-invasive method with a portable ultrasound machine without using radiation of low cost and, of course, reproducible. On the other hand, the inability to depict lesions which are not in contact with the pleura and, of course, the operator dependence represent the major drawbacks of this method. Moving to technical parameters, before starting a lung examination, several settings are required. Firstly, the lung protocol is regarded optimal. When unavailable, the abdominal preset should be used. Additionally, the depth of our image should be set at about 10 centimeters with slight variations based on patient's BMI, while our focal zone should be placed at the site of maximal interest, usually the pleural line. Finally, any filters or harmonic imaging should be set off, as such presets may hide artifacts which, as said before, are of diagnostic value. The transducer choice now is also very important. In general, low-frequency curved probes allow the depiction of deep, while high-frequency linear probes are ideal for the evaluation of superficial structures. The microconvex probes are regarded optimal by allowing the depiction of both superficial and deep zones. Additionally, owing to their small size, they can be effectively adjusted in the intercostal spaces with limited accessibility. Regarding patient positioning, it has been proposed that the supine position is optimal for the examination of anterior and lateral lung segments, while the posterior zones should be examined with the patient in the sitting position. Alternatively, the lateral decubitus position, especially in patients with inability to move, allows for efficient imaging of all lung segments. In this regard, examination of the left lung is performed with the patient in the right lateral decubitus position and alternatively. Additionally, this approach ensures paramediastinal shifting of the dependent changes, which otherwise may pose a challenge in the interpretation of our image. It is suggested that for lung imaging, the more extent in the examination field, the better. And it is logical considering that most ILDs follow a diffuse distribution pattern. For this purpose, and according to international guidelines, each hemithorax is divided into 6 segments, 2 anterior, 2 lateral, and 2 posterior, according to predefined anatomical lines. In this regard, the anterior segment are defined by the parasternal and anterior axillary, the lateral by the anterior and posterior axillary lines, while the posterior segments lie between the posterior axillary and the paravertebral line. Coming to the scanning technique, the probe should be placed along the short axis. This is vertical to the examined intercostal space and then is moved along its entire length. If we choose, for example, to examine the anterior segments of the right hemithorax, we start scanning along the superior intercostal spaces from the lung apex, moving caudally until we have covered the whole area. The same technique is applied for the lateral and posterior segments, as shown here, by avoiding the scapula. Then, in areas of specific interest, the probe may be shifted along the long axis of the intercostal space, allowing the picture of a larger field of view. That was for the technique. Now, in the normal lung, there are 4 ultrasound signs that we have to know for image interpretation, namely the pleural line, the BAT sign, the A lines, and lung sliding. So, when we place our probe vertical to a normal lung intercostal space, we can see from superficial to deep the subcutaneous fat layer, the thoracic wall, and intercostal muscles. We can also appreciate the ribs with their acoustic shadow at the superior and inferior part of the intercostal space. This is the cephalic and this is the caudal part. In between the 2 ribs and about half centimeter deeper lies the echogenic line, namely the pleural line, which represents the parietal and visceral pleura. The two ribs now, together with the pleural line, give rise to the bud sign, with the ribs representing the wings and the line the body of the bud. Deep to the pleural line and located at equal distances from one another, you can see further hyperechoic lines identical to the pleural line. These are the so-called A lines and represent reverberation artifacts emanating from the pleural line, being indicative of the presence of air, either in the lung or in the pleural space. Lung sliding. Lung sliding refers to this movement of the pleural line owing to sliding of the viscera over the parietal pleura. When we see this sign, we want to see this sign, we are sure that the two pleural layers are in contact and move freely. So imagine that this sign may be absent or reduced in fibrotic lungs, and then the lung volume is changing during the breath cycle. Abnormal findings in ILDs defining the so-called interstitial lung syndrome can be categorized into the B lines and pleural abnormalities referring to pleural line irregularity or fragmentation and the presence of subpleural nodules. B lines are defined as laser-like vertical hyperechoic lines arising from the visceral pleura, that is, the pleural line in the ultrasound language. These lines should extend to the bottom of the screen without fading and move synchronously with lung sliding. The pathophysiology behind B lines remains undetermined. However, they are believed to be due to partial lung deaeration, due to fluid accumulation or DTO, or the other theory is that they are due to septal thickening, due to collagen or fluid deposition. Talking about B lines, the number matters, and that is to say that in normal conditions, we can expect to see about 1 or 2 B lines per scanning site. However, when this number exceeds the 3, so more than 3 B lines per scanning site, this is regarded abnormal and gives rise to the term alveolar interstitial syndrome, which, beyond pulmonary fibrosis, includes many other conditions. The differentiation between them is very important, and ultrasound has some clues to do this. We will not talk about pneumonia. This is a completely different entity with specific signs that beyond the topic of this lecture. But we have to say that, unfortunately, B lines alone have a low specificity in the differential of the diverse causes of alveolar interstitial syndrome. That is, they cannot differentiate interstitial lung syndrome from other entities described under this term. For increasing the diagnostic specificity, the clinical setting, and both the distribution pattern of B lines and several other characteristics should be evaluated. In this context, we have to consider the distribution pattern of B lines. That is, in cardiogenic pulmonary edema, the typical appearance is multiple, diffuse, and bilateral distribution, while in ARDS, we typically expect to see what is called spurred areas, that is, normal lung segments spurred between lung abnormalities. On the other hand, on pulmonary fibrosis, typically we expect to see a separated pattern. We are going to see examples later on with a predilection of the lung bases. Additionally, pleural line irregularities are expected in ARDS and pulmonary fibrosis. Consolidations and pulmonary and subpleural nodules also expected in these two conditions, while lung sliding appears normal in cardiogenic pulmonary edema and reduced or completely absent in the other two conditions. Of course, pleural effusion is a characteristic of cardiogenic pulmonary edema. And let's see that this different distribution patterns of B-line in different clinical settings. Here you can see that these laser-like structures emanating from the pleural line to the bottom of our screen, and observe that there is a large distance between one and another, and they appear thin. In this case, B-lines are thicker, they are more close to push from one another, but we can see normal lung segments interfere with the pathology. This is in contrast with this case where you can see completely, totally confluent B-lines giving rise to the so-called white lung. And what we know is that the presence of separated B-lines, these are separated B-lines with a distance of about 7 millimeters from one another, is indicative of septal thickening on HRCT, while confluent B-lines, this and this appearance, is indicative of the presence of ground glass opacities. This is a case of reduced lung sliding. Remember the normal sliding in the previous case in a patient with idiopathic pulmonary fibrosis, and not the presence of several B-lines. They are a little bit thickened that do not move normally during the breath cycle as expected. This is a feature of ILDs. The other feature, and to my opinion the most important, is the assessment of the pleural line. So in patients with interstitial lung disease, we expect to see thickening of the pleural line, thickening compared to the normal side where is a thin homogeneous line. This is quite different. The other feature is the irregularity and fragmentation, and not this case where you can see parts of the pleural line. Here there is an interruption, another interruption here. So this is a fragmented pleural line. This is indicative of fibrosis. Again, irregularity and fragmentation here, small gaps in the pleural line. And another feature is a small hypoechoic nodule in contact with the abnormal pleural line. This is the typical appearance of the subpleural nodule. Another thing to note here is the presence of several B lines arising from the abnormal pleural line, and this image includes all we have to see in order to characterize a lung as fibrotic. Again, thickened and slightly irregular pleural line with a typical subpleural nodule, always compared with normal lung segments. On real-time imaging, you can see in patients with interstitial lung disease, again, see the abnormal line, small interruptions here, a little bit thickened, and here you can see a small subpleural nodule, while here a larger subpleural abnormality with a completely dearranged pleural line in a patient with IPF. Okay, that was from me. Now I'll move to Dr. Vasarmidi for the description of clinical applications of this method. Thank you.
Sorry, I cannot see it here. For us, it was a combined presentation in order to keep it short. So maybe... Yes, Evie, maybe you should stop sharing so I can... Okay, let me check. Okay, great. So I'm going to continue with the clinical applications since Evie, Dr. Vassalou nicely described the technical and the findings of the lung ultrasound in interstitial lung diseases. So the role of lung ultrasound in the detection of pneumothorax, in the evaluation and management of pleural effusion, and in the detection of ARDS is well established and well described in several guidelines and recommendations so far. But regarding the role of lung ultrasound in interstitial lung disease evaluation, I think evidence are gathering the last years. And so, interestingly, a couple of years ago, these guidelines published by a group from Poland put a role of lung ultrasound also in the evaluation of interstitial lung disease at the diagnosis mostly, and less in terms of disease monitoring, based on several studies published showing a high accuracy of this method. So a sensitivity over 84%, a specificity over 87% implies that lung ultrasound is a reliable tool for diagnostic of alveolar interstitial syndrome. Of course, the gold standard remains to be HRCT. So interestingly, in several studies, it has been shown that the score of lung ultrasound has a significant correlation with HRCT quantification scores and pulmonary function tests. So meaning that the number of B lines detected at lung ultrasonography is correlated with the findings of HRCT. And also importantly, pleural and subpleural irregularities have been shown to have a good correlation also with analogous findings of HRCT. Most studies have included patients with idiopathic interstitial pneumonias and interstitial lung disease associated with rheumatic disorders, without mentioning any distinction features among the diseases. However, we can assume that lung ultrasound has also a role in the detection of the upper or basal predominance of the findings, on the detection of ground glass opacities, as Evie showed in the last slides, and also we can propose that there is a role for distinction of honeycombing, or at least for a suggestion if there is honeycombing, as subpleural changes, pleural irregularity and fragmentation, and decreased lung sliding has been associated with honeycombing on HRCT. So in order to summarize the clinical application of lung ultrasound, we should say that, first of all, it is a reliable screening tool. Numerous studies and 3 recent systematic reviews have validated its role in rheumatic diseases. And all this gathered evidence, as you can see in the tables, show that there is a really high diagnostic accuracy of this method in patients with CDDs, ILDs. Most of the studies, as you probably know, are about scleroderma lung. So the sensitivity is approximately 100% and the negative predictive value also of 100%. So this means that the lung ultrasound findings can guide the clinician to further investigate with HRCT. Less studies for rheumatoid arthritis patients, but also enough evidence to show that there is also a high sensitivity and specificity of this method. And less patients with Sjögren's syndrome or inflammatory myopathies or ANCA-associated vasculitis with interstitial lung disease were involved in those studies. Second, prognosis. It can be used as a prognostic tool, mainly again scleroderma lung studies that show that lung ultrasound can be also represent a biomarker of pulmonary interstitial involvement. And in this recent study in 2020, it has been found that the increased number of B lines has an additional value over topoisomerase 1 positivity for scleroderma lung. Third, differential diagnosis. It can help us differentiate between cardiogenic and non-cardiogenic edema and pulmonary fibrosis. I use again the table that Dr. Vassalou showed us because it nicely depicts the differences and the commonalities between these three diseases. However, it can be challenging to distinguish in the context of pulmonary fibrosis. As you can see, the irregularity of the pleural line can make it difficult for clinicians to differentiate. And last but not least, disease monitoring. A few data until now have shown that it can be used also for monitoring of ILDs. This results of our study, of our group, that we recently published, follow-up HRCT and lung ultrasound findings in a cohort of patients with a wide spectrum of ILDs during 1 year follow-up. And we found that there was a significant correlation with the number of P lines and the HRCT scores, the Warwick score, and also the PFTs in our patient. And in this figure, you can see the lung ultrasonography findings of a male, 53 years old male patient with idiopathic pulmonary fibrosis. So on the left, you can see the lung ultrasound findings at baseline at the 5th intercostal space along the left paravertebral line. And 1 year later, you can see that there were more B lines, and this was in accordance with higher CT findings showing a progression of fibrotic changes on the bottom panel. And of course, one last slide for COVID, actually for post-COVID, because for acute COVID pneumonia, its role is well established, as you may know. But this interesting study published recently, last year, showed that maybe there is a role for the long-term follow-up of COVID patients with a high sensitivity and specificity again. So this group monitored patients 3 months after hospitalization, and they found an outstanding discrimination ability of lung ultrasound, and there was a high rate agreement rate compared to higher CT. So this implies that the lung ultrasound can be an effective first-line tool for the assessment of COVID patients, and the clinician maybe can perform higher CT based on lung ultrasound outcomes. So to conclude, although air is considered as an acoustic barrier in general, it seems that altered normal air-tissue ratio opens actually an acoustic lung window showing recognizable ultrasound findings. So lung ultrasound represents a reliable tool in evaluating the very early signs of fibrosis, so we can use it as a screening tool for pulmonary involvement in connective tissue disorders. Also, it can be helpful in differentiating between a fibrotic and a cardiogenic interstitial syndrome, and also for the follow-up of patients with ILD. Of course, more studies are needed for an optimal protocol in order to standardize the ultrasound examination of the lung and reach to a consensus on the semi-quantitative method. But I think there is a place for lung ultrasound on our everyday clinical practice, because we should not forget the many advantages. It's fast, non-invasive, non-radiating, low cost, well tolerated by the patient, and easily repeatable by the clinician. Thank you for your attention.
Thank you very much. I think in sake of time, we have just a short comment because we are in delay. And
okay, so.
I think that COVID-19 was unfortunately an occasion to implement ultrasound in all the departments. We are now plenty of ultrasound machine, and we
for
use,
acute pneumonia and ARDS in critical ill patients, yes.
And we used it as complementary of the stethoscope.
Exactly. Do you use it also for post-COVID longitudinal assessment of your patient?
Not so easily.
Okay.
I know it was an Italian group that
yes.
published. I know that. Yeah.
Yes.
But yeah, it's not. I think it's operator dependent much more than.
Yes, of course. Ultrasound is always operator dependent, but yes.
Okay, I think
it can be helpful.
Just a brief comment also. It has been used also to assess the diaphragmatic strength. Also
of course,
in patients,
yes.
Under mechanical ventilation.
I think really in ICU, it's well established its role in diaphragmatic. Yes,
the revolution of ultrasound was in endoscopy. In endoscopy was an absolute revolution. Yeah. Okay, so we can move on.
Okay,
and I invite Koutsopoulos from Crete, Histopathology in the diagnosis of ILD. Can we switch off the air conditioner? No, because in a few minutes I will be admitted to the hospital with bronchopneumonia. So it's online. It's online, yes.
Okay. So
go on.
Yes. Hello, Tasso.
Hello.
It's great seeing you. Professor Koutsopoulos is associate professor at University of Crete. So it's used to be also in Alexandroupolis for several years, collaborating with our department. So it's always good to see you, Tasso.
Thank you very much, Argyri. Good day to all. I'd like to thank the organizing committee and the chairs, of course, for the kind invitation to present you the issue regarding the histopathology in the diagnosis of interstitial lung diseases. I am trying to change the slide. Interstitial lung diseases or diffuse parenchymal lung diseases include a large category of diseases that involve the interstitium or parenchyma. Are both these terms accurate? In anatomy, parenchyma refers to the functional part of an organ, in contrast to the stroma or interstitium, which refers to the structural tissue of organs, such as connective tissues. All these diseases affect not only parenchyma, but also the interstitium. What is the pulmonary interstitium? It is the portion of the lung sandwiched between the epithelial and endothelial basement membrane, the tissue highlighted with the yellow color. Within the interstitium, there are collagen fibers, elastic fibers, mesenchymal cells, and a few inflammatory cells. This broad category encompasses approximately 200 entities in which the lung is altered by a combination of interstitial inflammation, granulomatous inflammation, or fibrosis. Most of these diseases can also involve pleura, bronchi, blood vessels, and epithelial cells. Sometimes the diagnosis of ILDs is difficult due to restricted and similar histopathologic reaction patterns of the lung, that is usually fibrosis and inflammation. For example, the UIP pattern can be seen on occasion, except in the context of IPF, in other conditions that have different mechanisms of injury, approach to therapy, and expected clinical presentations, like rheumatoid interstitial lung diseases and chronic hypersensitivity pneumonitis. The clinical course of DPLDs varies considerably. Some show rapid deterioration, little response to treatment, and fatal outcome, while others have good response in therapeutic interventions and even care. The overall survival of IPF differs dramatically from all other DPLDs. As you can see here, so there is an imperative need from prompt and accurate diagnosis for the optimum management of the patients. DPLDs include a heterogeneous group of mainly non-neoplastic disorders that are classified in 4 categories. These of known etiology, IIPs, granulomatous disease, and others, such as LAM and PLCH. According to this 2013 update, some of the authors are participating in this summer school. Idiopathic interstitial pneumonias are further classified in 3 categories: the major, the rare, and the unclassifiable IIPs. Furthermore, major IIPs were classified in 3 subcategories: chronic fibrosing interstitial pneumonia, which include IPF and NSIP, smoking-related IIP, which include RB-ILD and DIP, and acute or subacute IIPs, which include COP and AIP. The rare idiopathic IIPs include LIP and the new entity of idiopathic pleuroparenchymal fibroelastosis. For each one of the aforementioned IIPs correspond a specific histopathologic pattern. We will next discuss the pattern of usual interstitial pneumonia that correspond to the clinical radiologic pathologic diagnosis of IPF. Which are the characteristics that lead the pathologists to recognize the UIP pattern? The major histopathologic features of the UIP pattern are patchy lung involvement with specific distribution, the presence of dense fibrosis with architecture remodeling, temporal heterogeneity of fibrosis, honeycombing, and abscess of features that, to suggest an alternative diagnosis. According to 2018 update for the diagnosis of idiopathic pulmonary fibrosis, pathology should classify UIP pattern as UIP, probable UIP, indeterminate UIP, or alternative diagnosis. Below criteria of each column. In accordance to the same update, in this table, the HRCT and histopathology patterns are combined for the best approach to correct diagnosis. Protein gland, we can observe internal areas of fibrosis with relatively normal lung. These areas. The distribution of fibrosis, which is subpleural and paraseptal, and the mild degree of inflammation. In this lung section, we can observe an area of relatively normal lung, an extensive area of established by fibrosis, and the edge of which we see a fibroblastic foci, which represent newly formed active fibrosis in higher magnification. There is also cyst formation, micro honeycombing, smooth muscle cell proliferation, and a foci of mild chronic inflammation. In other words, we see the past established fibrosis, the present active fibrosis, and the future normal lung that is waiting to be fibrotic. Another additional finding in the modeling result to multicystic areas. The cysts are lined by respiratory cylindrical or metaplastic epithelium. Frequently in the lumen of the cyst there is mucus and inflammatory exudate. This is also a foci of honeycombing gland. The cysts are lined by respiratory epithelium. As previously mentioned, the fibroblastic foci represent the site of newly formed loose fibrous tissue. It is composed of myofibroblasts and stroma, poor in collagen fibers. There is an overlying epithelial cell cover. The macroscopic view of a normal and a fibrotic gland, you can observe the differences in appearance in the distribution of lesion in fibrotic lung. Closer microscopic view of honeycombing lung, you can see the multicystic appearance. Except from the previously mentioned major features, there are also some minor features. Some of them are frequently found and some are rare. I will show some images from the most frequent. Collections of alveolar macrophages. Inflammation is usually mild and consists of a patchy interstitial infiltrate of lymphocytes and some plasma cells. Type 2 pneumonocyte hyperplasia. Smooth muscle cell proliferation in the interstitium is commonly seen in areas of fibrosis and conegobin. When severe, the term muscular cirrhosis of the lungs has been applied. Median and intimal vessel thickening. Cholesterol crystals. Pleural fat metaplasia. Sporadic giant cells. And osseous metaplasia. The presence of findings such as active lesion of other DPLDs, marked inflammation, granulomas, inorganic dust deposits are not compatible and abrogate the diagnosis of IPF. We shouldn't find sporadic asteroid scars, poorly formed granulomas, granulomatous inflammation. Another case caused in borreliosis, marked interstitial inflammation. Also, asbestos fibers, hyaline membranes, or homogeneous involvement of lung parenchyma. The clinical conditions that are associated with the pattern of UIP include IPF, of course, collagen vascular disease, drug toxicity, chronic hypersensitivity pneumonitis, asbestosis, familiar IPF, Hamarski-Pudlak syndrome. In most cases, the histopathological feature will reveal useful information regarding etiology, activity, chronicity, reversibility, and prognosis. Examples, I have here 3 images from 3 examples of UIP, like I want to say pattern. The first is UIP of IPF that shows paucicellular subpleural fibrosis with multiple fibroblastic foci. The second picture is from rheumatoid ILD that show lymphoid hyperplasia with chronic bronchiolitis. And the third is from chronic hypersensitivity pneumonitis that show bridging centrilobular fibrosis with mild inflammatory infiltrate and peribronchiolar metaplasia. I quote here the 2018 ATS ERS JRS SALAT guidelines for the histopathological diagnosis of IPF 2020 guidelines for the histopathologic diagnosis of fibrotic IPF. There are also some difficulties in the interpretation of biopsy of neoplastic lung disease. The main causes are low frequency. Most medical centers have limited experience, lack of crucial clinical and imaging data, sampling error. Sometimes the histopathologic pattern can be similar to from different conditions. In this article, was shown that the diagnostic accuracy of IPs with only histology was 67%. When the clinical data were added, it increased to 82%, and when multidisciplinary discussion took place, the accuracy approached 100%. As a conclusion, I'd like to say that the combination of clinical imaging and histopathological data will guide us nearly always to the correct diagnosis. Thank you for your attention.
Thank you very much for your presentation. I think we have time for one or two questions or comments. Giris, you have one comment?
Yes, thank you. Thank you, Tassos. I think we're heading towards an era actually that I think we should involve more the tissue in the prognosis of the disease and also in classifying the disease. And also cryobiopsies. We have Venerino with us, so I would like his comment on my remark. I think cryobiopsies have offered us a possibility, and in order to have accessible lung tissue in these patients on a minimally invasive basis. So what do you think are the major prognostic marks in the IPF, in the lung tissue, based on your experience? So in order to classify the disease based on prognosis, like for example, you think it's fibroblastic foci, it's the traction bronchiectasis, is the presence of inflammatory cells, is the presence of areas of follicular bronchiolitis. So based on disease heterogeneity, do you advise clinicians for the prognosis of the disease based on histopathological lesions that I mentioned before?
Yes. Andrew Nicholson has published an article years ago. He combined the number of fibroblast foci with the prognosis of the patient and found that the number of fibroblastic foci are poor prognostic indicator for the survival. I agree with this opinion because, as you understand, the fibroblastic foci indicate the new formed fibrosis. That means if we have a lot of these foci, a lot of sites of newly formed fibrosis, we expect to have a poorer prognosis. If you have a method to count, I don't know, in the tissue section, we can count the foci, but I don't know any exactly quantitative method, or if in the HRCT, if they can number the fibroblastic tissue, I don't know. But I think that the main problem, the main factor for the prognosis is the newly formed fibroblastic tissue.
Okay, no, I don't have further comments, and I think because of time, we have to move on. Thank you very much again. And I invite Manuli, I think from Athens. Manali from Athens. Are you online?
I'm online. Can you hear me, Professor Poletti?
Yes.
That's great. And you can see my slides too?
We can hear you. Okay, and now we can see you.
Thank you. Thank you very much. I would like to thank myself to the organizing committee for this honorable invitation. I would like to apologize for not being there with you at Heraklion. And I would like to start my presentation regarding the genetics in the diagnosis of interstitial lung diseases. As you may all know, this July we will all celebrate the 200 years of the birth of Gregor Mendel, which is considered the father of the science of genetics, which has revolutionized the way that we look at human disease. And of course, interstitial lung diseases do not represent an exemption to this rule. So there is growing evidence about the genetic factors contributing to the development of interstitial lung disease, as you already heard, based mainly on 3 observations: on the fact that pulmonary fibrosis may also be encountered in children and young adults, that it develops 10 times more often in members of families with idiopathic pulmonary fibrosis, and that it may be a feature of multisystem inherited syndromes like dyskeratosis congenita, where bone marrow failure coexists with pulmonary fibrosis and liver disease. These observations, in association with the development of advanced genetic testing techniques, led to the discovery of variants in genes that are related to a very increased risk of inherited pulmonary fibrosis. As you heard before, we have a lot of families on genes implemented to this process. However, we can classify them based on their variant frequency, and we can talk about the variations, about the mutations that are very, very rare in the general population, with a minor allele frequency of less than 0.1%, that are represented mostly by the mutations regarding the telomere homeostasis and the surfactant homeostasis. These mutations, they are very, very rare, but they increase significantly the risk to develop interstitial lung disease. At the other edge of the range, there are the very common variants, those related mostly to host defense, cell-cell adhesion, and DNA repair. They have a frequency greater than 5% in the general population, but they have a smaller effect in the risk to develop the disease. And in between, we have a common variant, the variant of the promoter of mucin 5B, who is related to airway mucus homeostasis, as you already heard, but has a very significant effect on the development of interstitial lung disease. I will not comment on the pathogenetic mechanisms related to these mutations because Professor Crestani very nicely did before. So mutations provide evidence about pathogenetic mechanisms. They relate to important clinical and therapeutic options. But what about genetics in the diagnosis of interstitial lung diseases? The practical utility of genetic data is more evident in the diagnosis of patients with familial interstitial pneumonia. What is familial interstitial pneumonia? It is a pneumonia, it is an interstitial lung disease defined by the presence of at least 2 cases of pulmonary fibrosis in the same family. In order to realize if we have a patient with familial pulmonary fibrosis, we have to take the family tree, we have to make the pedigree of the family. The more generations that we ask for information, the better. The more members in any generation that we ask for information, the better. So you can see here a very typical pedigree of a familial pulmonary fibrosis case with a lot of members in the same generation, a lot of members in consequent generations. And this pedigree demonstrate that the prevalent, I would say, mode of transmission is the dominant mode of transmission for the majority of mutations, not for all, however. Familial and sporadic pulmonary fibrosis cases, however, are clinically identical. That means that our patients, whether they have familial fibrosis, whether they have sporadic disease, they will present with cough, they will present with dyspnea exertion, they will probably have finger clubbing. What can differentiate initially this approach? Radiographical findings could be an issue. For example, in familial cases, we usually have more unclassifiable patterns with honeycombing at the apices of the lungs or with kystic changes. And of course, the age of development of the disease. It is well known that in familial cases, the patients are usually younger, both at the development of the symptoms and at the diagnosis of interstitial lung disease. When a pulmonologist managing patients with interstitial lung disease has diagnosed a familial case of interstitial pneumonia, then he should probably ask about genetic testing. Why? Because this could lead to a specific diagnosis to short telomere syndrome or to multisystem genetic disorders in which pulmonary fibrosis is included. Here you can see a table that is not quite exhaustive, but very representative of all the genes that should be checked in such a case, of course, depending on the further clinical, radiographical, and epidemiological characteristics of the patients. And let's see an example. I would show you the first Greek patient that was examined genetically. I will tell you a small story. It was a patient, a 43-year-old patient, non-smoker, with these findings on the HRCT years ago. a very unclassifiable pattern, I would say, on an HRCT, a very destructive, however, pulmonary fibrosis, both clinically and histopathologically, as you may see, who had a very interesting family history. He had two patients, two relatives, an aunt and an uncle that had diseased 1 generation ago with interstitial lung disease, the one in the background of rheumatoid arthritis and the other in an idiopathic background. So when I presented this case in Copenhagen, I remember it was in Denmark, 2014, I was wondering what the diagnosis could be. Extrinsic allergic alveolitis, autoimmune rheumatic disease, unclassifiable pulmonary fibrosis. And I remember very well Professor Crestani being at the audience telling me that, Dr. Manali, your diagnosis is very clear. It is a familial case of pulmonary fibrosis with a genetic background, and this patient should be genetically tested. Indeed, this patient was genetically tested by Professor Caroline Canen-Chisser at Hôpital Pichat in Paris, and we had the result of a pathogenic mutation in the RNA, in the RNA component of the telomerase complex, and so we had put a much more concrete diagnosis to this very young patient who had a very bad outcome as well. So we started being interested in what is the genetic background in interstitial lung disease, what is the telomerase complex, what are the compounds of the telomerase complex. It seems that the mutations in every compound, in every single unit of this very elaborate compound are related to the development of pulmonary fibrosis and to inheritable disease. And why should a patient with pulmonary fibrosis know that he's a carrier of such a mutation? First of all, it's something quite common. Now we know that 20 to 30% of familial pulmonary fibrosis cases are related to TRG mutations. Then it is very evident that people who have pulmonary fibrosis and are carriers of TRG mutations also present with extrapulmonary abnormalities related to the liver, to the bone marrow, to the skin. And this is very important for their outcome and for their everyday care. So they should not only be treated by a pulmonologist, but also probably by a hepatologist, by a hematologist, by a dermatologist, and so on. And most importantly, it is shown that patients who are carriers of TRG mutations have a quite progressive disease with reduced transplant-free survival and a lot of complications post-transplantation. And these are the studies that documented all these very interesting aspects of TRG mutation related ILD. So this is the French study published in 2016. Again, Professor Crestani and his collaborators at Bichat demonstrated that patients who are carriers of TRG mutations develop pulmonary fibrosis at a younger age. They have less frequently a diagnosis of typical IIP-IPF pattern and have more frequently extrapulmonary signs. Most importantly, the survival, the transplant-free survival, as you can see here, the Kaplan-Meier curve period is much slower. So they have a much worse survival compared to those that are non-carriers of the disease. And the same study demonstrated that the higher the percentage of extrapulmonary signs, the higher the possibility to be a carrier of TRG mutations. And this is the fact. In the Greek series, we searched the family who had, you can see here, a 3-generational family who had a lot of patients with pulmonary fibrosis, either alive or dead, who had a father with liver cirrhosis without alcohol consumption, and who had a lot of young members in the 3rd generation with bone marrow failure expression like leukemia and other diseases. We searched genetically this family, and apart from the diagnosis of familial pulmonary fibrosis, we documented the presence of a mutations never described before, again related to the telomerase complex mutation, the NOP-DIS mutation that can predispose to short telomere syndrome. Another very important study at the same period of time was published by the Americans, by Professor Christine Kim Garcia, who made a very important for me approach, saying that no matter what the classification of the interstitial lung disease is, you can see here this study includes patients either with IPF, with NSIP, DIP, PPFE, chronic hypersensitivity pneumonitis, and so on. All the patients are carriers of TRG mutations. And what this study showed, it showed that no matter what the radiographic findings, no matter what the histopathologic documentation, even in the same family, the outcome is mostly confirmed, is mostly defined, I would say, by the carriership of the TRG mutation and not by the classification of the ILD as we know it. It's a very bad outcome, actually, with a loss of AVC around 300 ml per year for all the patients, IPF and non-IPF, who are carriers of the TRG mutations. Another aspect that is very important, and we should know when we diagnose a patient with ILD that is a carrier of TRG mutation, and why is it necessary to do so, is because we heard that these patients are younger, these patients have a bad prognosis, so they will definitely need to be listed in a lung transplantation list. In such a case, the first French studies demonstrated that those patients had a very bad outcome post-lung transplantation. Why? Because they presented signs of myelodysplasia, either occult or clinically obvious, that led to pancytopenia and sepsis post-immunosuppression, post-lung transplantation. So this is a very important notion to have in mind. This is a notion that led, an observation, a very significant one, that led to the adaptation of the immunosuppression programs for selected patients, TRG mutation carriers, that are going to be lung transplanted. There are very recent trials, both from the American and the French group, that confirm this finding, that confirm the fact that carriers of TRG mutations that are lung transplanted will die sooner. But why? Because they will develop sooner, earlier, and in a much higher frequency, the chronic lung allograft dysfunction syndrome. The French team, again, Professor Crestani and his collaborators, have demonstrated that the main reason why this happens is the myelodysplasia, and hematological evaluation should be systematically performed before lung transplantations in those patients to ameliorate the outcome of such a difficult and demanding procedure. So from 2014 until now, we have we are very honored, we are very lucky to have the collaboration with the genetic department and the pulmonary department of the hospital Bichat in Paris, with Professor Crestani, with Professor Raphael Bory and Professor Caroline Canen-Gisser, to study and to analyze all the Greek patients with inheritable pulmonary fibrosis. The same thing applies with the department at Hôpital Trousseau in Paris for the surfactant protein mutations. Besides for the TRG and the mucin 5B, and Trousseau is for the surfactant protein mutations. Dr. Nadia Nathan, who has helped us a lot in that issue as well. So we started from 2014 with the collaboration of all of you. You know very well all the centers in Greece, all the professors, all the teams that are participating and managing patients with interstitial lung disease. We have collaborated all together with our French colleagues in order to study the Greek profile of the inheritable pulmonary fibrosis. We have published an initial result of our effort in 150 patients who have been checked genetically for mucin 5B, for TRG mutations, and for surfactant protein mutations. And we have found a big variety of mutations like the ones already described in the literature. We have found mutations very rare and not described before. And we have tried an original approach to describe both common and rare variants together and separately. And what we have shown is that this approach confirms the fact that TRG carriers have the worst prognosis in interstitial lung disease. But we have shown also that the addition of mucin 5B in such a patient could probably change the phenotype, and this is something that we want to further study with our colleagues in France in the future. Another reason why it is very important to study genetically a patient with ILD when we first diagnose him is to know what treatment we will apply. This is a question that all my patients ask. Dr. Manali, why is it important to know that I have a mutation? Will this change my treatment? So far, we know that the molecules that we are applying for sporadic interstitial lung disease patients apply both for inheritable disease. Antifibrotic treatment is both safe and effective in the same way that it is for sporadic disease. But another issue is the inclusion in specific studies with new molecules that in the future may be more effective in the treatment of those patients. Another issue why genetics could be very helpful in the diagnosis of ILD is multisystem genetic syndromes. It is an issue where pulmonology is included in internal medicine. So I will show you a pedigree of a young patient, 45 years old. It's courtesy of Dr. Tzouvelekis. He was addressed to him to evaluate him for lung transplantation, and then to us. He was very young. He had albinism. He had an exuberant pulmonary fibrosis, as you may see here, and he had a lot of other members in his family with albinism. The same patient had bleeding disorders and he had problems with his eyes. He couldn't see well due to this dysfunction at the melanin to the albinism. So he had ocular and dermatic albinism plus pulmonary fibrosis. When this patient was referred to us, he was young and he was referred to us as an idiopathic pulmonary fibrosis case. The same applies for my patient. This was a 59-year-old patient who had albinism, pulmonary fibrosis. He didn't know if he had bleeding disorders, but when I saw him at the outpatient clinic, I noted the problems with the skin. I asked him and he told me that he was diagnosed with ocular albinism since the age of 6 years old. So it was first the eyes that set the diagnosis, then the skin, and finally at the age of 60 years old, the lung. And then I thought about the Hermansky-Pudlak syndrome, and I talked with Professor Canenchisser, I talked with Professor Ravellier at Bordeaux, and we confirmed the diagnosis of both patients by disclosing the presence of two variants at the two mutations at the Hermansky-Pudlak syndrome 4 gene, explaining the syndromic form of pulmonary fibrosis in this patient. We do not have time to discuss about Hermansky-Pudlak syndrome right now, but what I want to say is that it's a syndrome, as I told you before, that associates albinism, bleeding diathesis, colitis, and in many cases pulmonary fibrosis. Our patients should know that they have this syndrome because they have to take care of all the other aspects of the disease, but mostly because regarding the lungs, if they need to have lung transplantation, then the whole team should be adjusted to the possibility of increased risk of massive hemorrhage and prepare accordingly for such a procedure. So it is very important for the patient to know that he has pulmonary fibrosis in the frame of a syndrome and not a sporadic disease. And finally, why patients with interstitial lung disease should have genetic testing. Another indication where they should have genetic testing is development of interstitial lung disease at a very young age. Tomorrow, I have a presentation about children's interstitial lung disease. We will have the opportunity to talk more in detail, but I will show you the first patient that we examined. It was a 26-year-old female patient addressed to our department, Professor Papiris and me, by our pediatricians. She was a lady that had been diagnosed at the age of 5 years old with chronic interstitial pneumonitis. She had a biopsy, but not a genetic testing. She survived for 20 years under hydroxychloroquine treatment. And when she was addressed to us, because she was an adult patient now, we checked the HRCT, we checked a new biopsy, but we thought that we should perform a genetic analysis because she developed the disease at a very young age, and this is very indicative of an inheritable component in interstitial lung disease. And we discovered the presence of two mutations, different mutations of ABCA3, that is a gene that is related very much to the processing of surfactant proteins in the epithelial alveolar type 2, and is related to the development of interstitial lung disease, both at a young age and at a lower age. The surfactant protein mutations related to the development of interstitial lung disease are multiple. You can see here the protein B, protein C, NKX2, and alpha-1 and alpha-2 protein mutations that are related to the development of such a disease. We do not have time to discuss in detail, but I would like just to point out that the presentation is many times atypical. The young age, as you may see here, is the one that we make us think about such an association of surfactant protein mutations and the atypical radiologic findings. A lot of cysts are a major characteristics in the radiology examination. A study by Dr. Nadia Nathan that appeared a few years ago demonstrated another very interesting feature that we need to know: the coexistence of lung cancer in patients that are mutated with mutations of protein alpha-1 and protein alpha-2 of surfactant. These patients, you may see here a very interesting pedigree. It includes patients with ILD from the age of 6 months to the age of 69 years old. Some of them have died at birth. Some of them have survived in adulthood and have developed fibrosis. Some of them have developed only lung cancer, and some of them have developed more. So you can realize how this changes the screening of the family, the approach, the diagnosis, the follow-up of the patient. And this is why we should think about it and try to confirm it if we have the opportunity. All this approach cannot be done in a basis that is not an expert basis. The important message, I think, is that the management of inheritable pulmonary fibrosis needs an expert team that has the knowledge and the expertise to perform the genetic analysis, to think about the indications, and to help not only the patient, but also the family who has subclinical disease in 15 to 31% of cases. This we may have the opportunity to discuss it in detail tomorrow when we will discuss about the early disease, the early diagnosis of interstitial lung disease. I think I have only 5 minutes, and please correct me if I'm wrong. Because the title of the presentation was Genetics in the Diagnosis of Interstitial Lung Disease, I have included some slides regarding other categories like the sporadic ILD. Is there a meaning to test genetically the patients with sporadic disease? At a research level, of course, there are a lot of mutations found related to host defense, to cell addition, to DNA repair, as you may see in this table. There is no consensus saying that it is very important to do so for rare variants and what is the meaning of that. However, there is an exception. There is the exception of the mutation regarding the promoter of the mucin 5B gene, which increases tremendously the risk to develop both sporadic and familial interstitial pneumonia, as we already heard. And for me, this is the most fascinating aspect and perspective, I would say, how we would use this information to stratify our patients and to learn more about the response to treatment. This is a paper of 2014 in the Blue Journal saying that analyzing and stratifying patients regarding another mutation, regarding the TOLIP gene, not the mucin 5B, which demonstrated clearly that the patients who were carriers of the TT genotype had a very bad outcome when they were treated with NAC, whereas the other two teams had neither no effect or a beneficial effect. And this could be applied in the future to help us, I would say, optimize the treatment for our patients. What about genetics in ILDs, interstitial lung abnormalities? You heard very well Professor Wells saying that there is no strong evidence relating ILDs with a genetic background, and what is the meaning for all this? For me, the importance in ILDs is to find out which ILDs will develop to clinically significant ILD. And in that perspective, there are a few trials showing that mucin 5B again increases tremendously the risk to develop such a condition, and a condition that will progress to clinically significant interstitial lung disease. Here you may see a model evaluating factors associated with progression in ILDs, and the presence of a mucin 5B variant is along with age, the two parameters that are related to such a perspective for our patients. What about genetics in connective tissue interstitial lung disease and the diagnosis? Again, the French team here, it's Professor Philippe Diodet, with Professor Crestani, Caroline Canen-Gisser, and Professor Bouros, who have enriched the literature with a lot of evidence regarding the role of TRG mutations in the CTD ILDs. This is the first study in 2017. This allows us to understand there are common shared mechanisms between CTD ILDs and non-CTD ILDs. The study of New England that demonstrated clearly that mucin 5B, the presence of the variant of mucin 5B increases the risk to develop an array UIP pattern, not simply an array ILD, but an array UIP pattern, in patients with rheumatoid arthritis. And finally, a very recent publication in May 2002 from Philippe Diodet, who created a risk score to try to allow to stratify high-risk patients with rheumatoid arthritis who will develop RA-ILD. This is very important. You can see here all the parameters included in the score, the age, the disease activity score, and the mucin 5B genotype that strengthens very much this score and the risk to develop the disease when it is present. Finally, about chronic hypersensitivity pneumonitis, very few information in the literature, very scant studies. Here I keep in mind the result of the American study saying that the prognostic importance of background genetics sometimes are more important than the currently used ILD diagnostic classification. And finally, the last few slides, you can see here a very interesting figure showing the ILDs divided based on the classical classification and showing the ILDs how we could diversify this classification if we take into consideration the common genetic background that we encounter in different ILDs, as we already described. It is definitely clear, as the last paper of the ATS demonstrated, that there is an urgent need for a consensus, an international consensus that will tell us how to validate the utility of family history or genetics in the diagnosis of ILDs. I know that there is a task force ongoing at the ERS, headed by Professor Bory and Professor Colin van Moorsel, who is working on that, and we expect very eagerly the results of such a task force. I thank you very much for your attention.
Okay, thank you, Frini. That was a very intuitive presentation. It was very extensive. We're running out of time. I don't know if there are any questions.
I think we have to move on because we are very in delay.
Okay, so proceed to the next presentation. So it's my great pleasure and honor to present Dr. Tsitoura.
Tsitoura.
She's going to talk on BAL procedure and flow cytometry in the laboratory of molecular and cellular pneumonology. So Dr. Tsitoura is principal investigator in Professor Antoniou laboratory, and she has done a lot of work on BAL macrophages and also innate immunity, the role of innate immunity in lung fibrogenesis. So Elisa, thank you very much for your
Thank you very much for this kind introduction, Argyri. So I will try to be very quick. And this is an outline of what I would like to speak today. So Katerina asked me to give an overview of what we do in the lab and maybe just present you a little bit of our data on profibrotic macrophages. And if I have time and you don't stop me in the middle, I can show you some results about our post-COVID ILD patients.
You have 20 minutes. You have 20 minutes, Elisa.
Exactly. Okay, so just a quick photo to remind you of how BAL looks. So usually you know this type of image and this type of results in your differential cell counts as pulmonologist. This is how the cells look in the light microscope. So we have a mixture of macrophages, occasionally bronchial epithelial cells, and this is how they look under the fluorescent microscope. So they are actually highly autofluorescent cells, the alveolar macrophages, whereas you can see here the other types of cells do not autofluoresce much, which is an indication of highly active cells, actually. So what we do in the lab, and this is a very old slide, which we presented like in 2016, I think. It's a long time ago since I was in the lab already, to a couple of years. So we collect, of course, the fluid and separate it from the cells that we get. We can use the fluid for studies of cytokines, other soluble factors that could be there, but we mainly focus on the cells. And at the beginning, we're just collecting them for total RNA or protein or DNA. We would do our MGG stains and some FACS analysis. And another important part of what we can do with these cells is that we can shortly culture them. So we can do some assays And from these assays, I will show you like a couple of publications that we managed to have in the last years. Now, a more intriguing part of what we do in the lab, and I'm not going to go further into in this talk, is that we actually cultured them for a very long time. And we seem to pick up a type of cell that is a stem cell in the BAL that can grow for many, many weeks afterwards. And we're still trying to understand which patients and actually have these positive cultures for these fibroblast-like looking cells. Sorry. So our initial approach to the FACS analysis of the BAL was to use a CD45 leukocyte marker, and then we played with some autofluorescence side scatter or measuring the dimension of the cells, but we eventually decided that granularity and CD45 were very nicely separating the populations in the BAL, and we have been using this since. So you can see the airway macrophages clustered here. You can see a set of monocyte cells that we now know are monocytes because of their staining for CD11C, 16, and 14. We can clearly have a nice image of the lymphocytes, and unfortunately, with this type of classification, we cannot distinguish PMNs and eosinophils, so we call them granulocytes. So in the last 2 years, we have in the university a more advanced fax machine, so we can have 3 lasers. We have included more markers. So now we can test for CD11C, which is a nice macrophage marker. We can test for CD14, which is a monocyte-derived marker that some macrophages contain, and this is a very important marker if we analyze, for example, damage, which is also a case for ILDs. We have an M1 marker and the classic 163 marker that was previously associated with fibrosis and M2 macrophages. And now we have implemented the study of osteopontin, which is a more profibrotic marker that has emerged in the last 5 years. And we can also check these same markers in the smaller population that I showed you in the monocytes. The other thing we routinely do to the BAL cells is to check for them for oxidized mitochondria. So again, we can gate on whichever population we want and study the levels of oxidized mitochondria using Mitosox dye, which is a cell-permeable dye, and then we can just very easily detect and measure it by fax. And this resulted in our first, I think, one of our nice publications where we could show that mitochondria oxidation and dysfunction, which was already being shown in epithelial cells by Anna Mora, that we could show that this was also the case for alveolar macrophages and in the BAL. So we could show that there is an increase in mitochondrial ROS. This was correlated with disease severity. And we had to do some electron microscopy analysis to actually prove the fact that the mitochondria were dysmorphic. And we could see a significant downregulation of markers involved in the health of mitochondria, either from the nucleus expressed either by genomic or mitochondrial genes. We also could show using these cells that inflammasome activation is also associated with increased mitochondrial ROS. And this was the work we recently published. And sorry, this is not in preparation, it's an old slide. And we could also show using FACS and Mitosox that you can actually, inflammasome activation increases a burst in oxidation of mitochondria. And if you use antioxidants, you can really downregulate this. And in our hands, and it's not on the slide, if you put pirfenidone in the same system, it actually has the same effect. So it completely blocks this burst of ROS. So this was with the previous And finally, just a reminder, we have never published this, we still don't have, but you can actually also in the BAL measure telomere length. And we have some nice correlation between age, and this is all patient samples, not only IPF. And we could show that actually in IPF, telomere length is reduced. So the BAL can offer you an array of information that is very indicative of disease, or maybe, as you seem to mention, that the need of tissue, maybe BAL is actually a very good material to recapitulate some of the pathogenic mechanisms of ILDs. So now we also have in the last year a cell sorter in the university, so we can actually start separating the cells, because this was always a problem, and a lot of criticism came in our studies because we could never see if what we see is actually come from the macrophages or from other types of cells. So now we sort the cells so we can separate the macrophages, monocytes and lymphocytes, and we use these either to collect the cells for RNA studies or to do metabolic studies using a seahorse analysis, and to further study mitochondria homeostasis or disease in these samples. And the last thing that has been implemented in the lab since December is that we're now in a big biomarker study where we actually do single cell analysis from the blood and the BAL from patients with ILDs, and this in collaboration with Bonn University, and I will show you some of their results. And you will be, I hope, impressed with the complexity of the populations in the BAL. So this is in COPD. So the team of Professor Schultz have actually done an amazing mapping of BAL cells in COPD, and they have currently measured at least 13 types of airway macrophages in COPD. And there is no such study yet in IPF, but soon, hopefully, we will have. And what is very interesting to see is that these macrophages, we start to see markers like senescence, which is a very important aspect also in IPF. So I think the BAL actually contains a huge amount of information, but has not been yet revealed due to the lack of technology. So this is, to finish up the first part of the talk, the biomarker study that we're involved. It is a small patient number, but quite in-depth study where we will actually do BAL analysis at the baseline before therapy, and we will have single-cell RNA-seq, whole BAL-seq. We will do our analysis on seahorse and mitochondrial oxidation, phenotyping, and in some samples, we will also have some proteomics. This is coupled with peripheral blood analysis at baseline 6 and 12 months. And this I will talk to you a little bit about this afternoon, which is the analysis of the breath samples, so which is like a breathomics analysis of these patients. Hopefully, we will identify some biomarkers that could either give us information about disease progression and maybe diagnostic valuable tools for these very complex and overlapping ILD diseases. So the second part of the talk, which is I think my favorite so far, is what in the last 5 years or so, profibrotic macrophage term has emerged in the literature, which seems to proliferate in the lower part of the lungs in IPF patients. And this is tissue studies from lower and upper lungs. And what you can see is this osteopontin expressing macrophage, which expands in fibrotic disease. These were two independent studies that came out together. And one of the top genes, as you can see, is collagen metabolic processes. Just a quick overview of what osteopontin is. I mean, osteopontin is not a new candidate for IPF. It has been already by Annie Pardo published that it's highly upregulated in IPF, and it was a potential serum biomarker, although it didn't pass tests and it was not specific for IPF. It was more or less increased in other ILDs. And we know now that if you block osteopontin, you can actually reduce fibrosis in mice in the bleomycin model. So the question was, can we detect these profibrotic macrophages in the BAL? And the first study that came up also had in the supplement a small figure where they could show that this is their BAL cells. You can see it's an older study with much less detail than what we have now, as I showed you for COPD. But still, we could detect this macrophage. So in the lab, and before these studies were actually coming up, we had an observation that one of the profibrotic microRNAs, microRNA 29 actually, which was strongly downregulated in IPF, we found it to be downregulated in the BAL, in whole BAL cells. And the target of MIR21 is actually collagen and other ECM molecules. So we started to investigate collagen expression in the macrophages. And in our first paper, we had severe criticism, and people were saying, oh, you have the odd fibroblast there, and this is what is causing collagen expression. So we continued in this second paper to actually check again that actually BAL cells from IPF have a higher expression of collagen 1, which is something you wouldn't expect for a macrophage. But also we saw that in other ILDs we could have variable degrees of upregulation, although it was less homogeneous in the other ILDs. Another interesting finding, again with very few amount of samples, is that the UIP pattern in a group of CTDs was actually associated with higher collagen expression. So, and then to answer the criticism about collagen expression in the BAL, we did an analysis on published BAL data from PRASE, where we could actually show that collagen is among the statistically more than twofold upregulated genes in their BAL study. And then with our collaborator in Fleming, we checked the expression of collagen in bleomycin treated mice. And again, we found that it is regulated in the BAL cells. And also this was a study published on a dataset published on bleomycin mice, and we also find collagen there. A further proof that it was the macrophages that were producing the collagen was that we stained them with CD45, and then we can clearly see here with red you have the CD45 staining, and with green you have a nice ER staining of collagen, which means that this is a protein produced in the cells and not something they have phagocytized, which is another comment that we used to get on this expression. And again, this is 163 staining, and we could show that, again, the collagen expression happens in these cells. So we assume these are macrophages. And with the help of Professor Wells and Athina Trahalaki, we analyzed some parameters regarding progression and severity of disease. And we could see that if we took all ILDs together, we could actually show that in the patients that progress, collagen is actually upregulated. And in the same paper, we tested a little bit the expression of osteopontin, and we also find it upregulated in the BAL cells from different ILDs, even much more clearly than collagen. So clearly, you can find osteopontin profibrotic macrophages in the BAL of all these patients. And here is a colocalization of collagen and osteopontin. So we know that the cells that express collagen also express osteopontin. So this is a paper I would like to share with you, which I'm not putting any figures, but the interesting part of this paper is that the group of Kaminsky and Wim Woods, they could show that from previously BAL published data, that the signatures that come up and are important in the BAL are increased epithelial and innate adaptive immune signatures, and they have correlated this with sex differences, so male and female have differences. But they had a numerical association with telomere mitochondrial dysfunction, loss of proteostasis, and increased myofibroblast signature in the BAL of patients that progressed. So again, this says a lot about the information that checking for these profibrotic macrophages in ILDs might give us. So this is another study in systemic sclerosis where again they could show an upregulation of, here we have fibronectin that is expressed in BAL cells. And to even more, to extreme effect, these cells can actually express alpha-SMA. So there are data that suggest that macrophages may actually also be part of the ACM-producing population in the lungs. It has been shown during in developmental studies and heart generation in mice and zebrafish. And there is also now some discussion about the similarity of senescent cells and macrophages, and we could think that these profibrotic macrophages are a part of a senescent macrophage population that may be influenced by the milieu of the lungs in fibrosis. And to even more extremes, you can actually have, if you all remember EMT transition, epithelial to myofibroblast transition, now we have perhaps a transition from monocyte to macrophage to myofibroblast, and this is just to give you an idea of where the field is going. And I will finish this part of the talk with this slide where actually macrophages can be targets for therapy. And we know from the pentraxin studies, but also we know that redirecting the macrophages may have beneficial effects as shown in this study using bleomycin. So I'm trying to be very, very quick. And so, of course, in COVID patients, you have osteopontin and profibrotic macrophages. I will be very quick. And this is our cohort so far. We have just 29 patients, I'm afraid. But there is a discrimination between ILD and fibrotic ILD patients. So we're still trying to decide on the grouping of the patients. And 6 of these patients actually are under antifibrotic therapy now. So what we show in these post-COVID ILD patients we do see an upregulation of polymorphonuclear cells and the trend for eosinophiles. So we see this, let's say, ILD, fibrotic ILD profile in their BAL. We also see an upregulation of these cells that I showed you at the beginning that seems to be even higher when you have honeycombing in the HRCT of these patients. We tested 163 on their surface, and we actually see that the ILD patients, which are more inflammatory patients, may have actually higher CD163 expression. And if we split the 2 groups of the fibrotic ILDs with the one in between the ones that have honeycombing and the ones that don't have honeycombing, we see that CD163 actually might decrease. And this is a previous observation we had with Irini that when we compared CD163 expression on the BAL cells, we could actually see that the more severe patients had less 163. So 163 is not, as it used to be, remember, the molecule that is associated with not necessarily a bad thing to have on your macrophages. So and the most interesting finding so far is that we see a very nice upregulation of zeopontin in the fibrotic relative to the non-fibrotic ILD patients after COVID. And we seem to also, we need to still analyze the collagen, but we see also cells co-expressing collagen and osteopontin. So finally, we are trying to analyze the mitochondria of the cells, and I can just give you the tip of the iceberg of our analysis because I still have a lot of data to analyze, but we seem to have an increase in glycolysis and obviously a drop in oxidative phosphorylation in the fibrotic ILD group. And this may reflect some process of activation of the cells that we will hopefully depict when we sequence the samples from these patients. However, when you go to the honeycombing patients, this is not the case. And in general, there is a very low basal level respiration in honeycombing, in patients with honeycombing. And we have been seeing this using the seahorse, not only in the post-COVID ones, but we start to accumulate data on the IPF patients also, which makes it quite difficult to measure. Finally, what I can share with you is that this glycolysis increase in the macrophages that we sort and analyze using a seahorse is actually tends to correlate with monocyte infiltration. So we are studying a little bit this, we're trying to understand the profile of these monocytes by FACS and see how this correlates with their interaction with airway macrophages. So thank you very much. I hope I was not too fast. So, and okay, this is the lab, and I've been here in the lab for 10 years now, and it was my pleasure to be able to present you some of our results. Thank you very much, and thank you to Katerina and Professor Tzanakis for having me here for such a long time. Thank you.
So thank you, Elisa. That was a very nice presentation, and it's also, I think that you have done something well. That's why they're keeping up with you for almost 10 years. So because we're running out of time, just one small comment and also a question to you. So this is really nice data that you presented on macrophages, and it's I think I was always a big fan of finite immunity in lung fibrosis, and also how they these macrophages, they can exacerbate the disease, not only on stable condition. Although my mentor in Yale didn't like innate immunity cells, but that's another story. So there are actually three types of macrophages. So there are tissue-resident macrophages, interstitial macrophages, and also the monocyte-derived macrophages. So based on the data that you have shown to us
in mice,
yeah, and also in humans.
It's a good comment.
That's the thing. In humans, we don't know.
Yeah. I mean, it's less data, but and also people, they don't like, especially immunologists, they don't like to separate macrophages into M1 and M2
anymore.
Like
as you saw, there are 13 different types just in the BAL.
Yeah.
Imagine the tissue, imagine the blood, imagine other organs. The complexity is enormous.
But the tissue-resident macrophages that you have shown, the positive, the CD163 positive cells, that they, if we have them, it's not necessarily bad.
That's in the BAL. All are data in BAL.
Yeah, this one saying. So these are in the BAL. So I think like maybe there's a shift towards the monocyte-derived macrophages that they migrate to the lung. We have also data showing that increased monocytes, they can predict dismal prognosis in patients with IPF. So that's why it might be a shift towards the to have diminishment of the tissue-resident macrophages and increase the CD14 monocyte-derived macrophages. So this shift
we see that we measure CD11C and CD14 and the airway macrophages. I need to do the analysis now for a large set of patients, but we tend to see that the increase of CD14 positivity in macrophages and monocytes is associated with ILD disease severity. It's higher in IPF. But what you need to think about monocytes is I am not sure if they're a bad thing or a good thing. And this is what we're trying to also understand, because monocytes are there to go and help the wound healing, and they go and help because they respond to a damage signal. So that's what everything, right? So that's why we're always surprised when we actually separate IPF from the different ILDs. We seem to lose all these mechanisms in IPF. I don't know if it's too late what we see and it's already, the damage is beyond repair and they are exhausted or senescent. But for me, this is why it's so interesting to have this post-COVID data set where we actually have an actual disease that started, we know when, and then we can see it a few months later and separate between the people that will have just a inflammatory ILD,
Well,
and then
that's an acute onset. That's a problem.
yes, no, but 3 months later, for example, and then you get some feeling of why some are fibrotic and what is the difference, and if you have some patients with previous severe disease and how this looks, and we can fit them in there to compare them. So I think the answer is we don't know so much because we focus too much on the mice. And the mice don't even have fibrocytes.
So the galectin-3 inhibitor, you don't think has a lot of luck?
I'm not sure.
In the treatment of IPF?
I don't. Why not? I wouldn't go that far. But what I'm saying is that
I just have one curiosity because yes, so a short question. As pathologists, we use CD68 or CD163 as the same thing. Is it correct or not?
I don't think so.
Okay,
I don't
good.
think so.
Okay, we're just 5 minutes late. Thank you very much. One more question.
Sorry, that's excellent. I didn't get it all, but we want to look macrophage projections in the tumors. You can see different. One, not different, but one question I have, of course, the signal in many diseases in the airways is what plasticity, that the cells are not really decide to go one way straight up. And also this is one that you see monocytes, the good or bad. I don't think that we should go this way. I think we should go today in a good, tomorrow in a bad. If you get into that on plasticity, or can you look at that, or something that there is in fibrosis and not?
Yeah. So I don't have any data on plasticity. As soon as you put the cells into plastic, they change. So you make a more homogeneous population, I guess. But the plasticity answer comes from the single cell analysis, where you actually see this. I mean, it's depending on the person who analyzes the data. Okay, so you can increase or decrease the different populations you see and the levels of overlapping gene expression. And I think this is where your answer probably lies, to the fact that I wouldn't go every single cell has a unique gene expression, but it's wherever the cell and at which timing you collect it in the blood, it's like a snapshot of very different population within a population that we call macrophages. So yeah, they're extremely plastic, even I think from morning to evening.
Okay, thank you very much.
I have to upload my. Excuse me. May I upload?
We are ready. Kostas, can you hear us?
Yes.
Okay.
Are we live?
Yes.
Okay.
Yeah.
Okay. It's a great honor to be here with you today. I'm very sorry that I'm not there, but I really had prior obligations with the clinic department.
Okay, Kostas.
I'm not seeing anything live right now, though. I only see myself.
Okay, if we have any problem, we'll discuss with you later. Good afternoon to all. My name is Konstantinos Porpodis. I'm a pulmonologist. I'm associate professor in Aristotle University of Thessaloniki. Let me introduce my co-chair. Konstantinos Amitas is a pulmonologist in the 7th Clinic of Sotiria, Athens. First of all, I want to thank Professor Antoniou for the invitation. I'm very happy to be here and to be chair of this excellent round table. We all know that spirometry still remains the gold standard technique to identify respiratory problems, but we all know that spirometry has many limitations because it requires significant patient's cooperation and willingness to undertake maximal respiratory efforts, and that's difficult for patients. So nowadays we have, let me say, alternative new methods, non-invasive methods to measuring the mechanical properties of respiratory systems. We have a change in the program. The first speaker is Elisa Tsitoura. I think Elisa, I'm not sure about the name. Is a postdoctoral researcher in Laboratory of Molecular in University of Crete. And his lecture is about to be the novel methodology of breath analysis. Elisa, you can start.
Ευχαριστώ πάρα πολύ. Thank you very much. So today I would like to introduce you to the measurement of volatile organic compounds, which is actually a branch of metabolomics that studies exhaled breath. So we know that the exhaled breath contains thousands of volatile organic components, that these originate from systemic and local lung metabolic processes, and they have a great potential for diagnostic and other type of biomarkers once you can associate them to pathological processes. So the type of volatile compounds that you can find in the breath can fall into these categories. So they are, as I said, organic compounds, and they can be alcohols, aldehydes, ketones, and different organic acids. You are mostly familiar with these types of assays so far that have been used in clinical practice, like the FeNO assay for Th2 responses in asthma. There are some testing for this small intestinal bacterial overgrowth, the SIBO, and malabsorption of carbohydrates. You know the H. pylori test that measures urea. And recently it was clearly shown that even viral infections like COVID can be detected in the breath, and this can actually be used as a type of test for COVID positivity. So the field is vast. There are hundreds of already reported VOCs, and there are, as we see, dozens of clinical trials with promising results with potential biomarkers for different types of diseases. So the field has had to overcome some technical challenges, and this is probably why you don't have, you haven't had the chance to use this type of technology in your practice. But it usually is the contamination with environmental VOCs. It is the instability of the VOCs and in combination with the type of exhalation. They're pretty low in abundance. And also there is a strong contamination with different materials that have been used in order to collect or analyze the VOCs. However, and I find this slide quite impressive because not so many people are familiar with the use of breathomics in the clinics, but there are several diseases now that are investigated and actively pursued into using breathomics in their diagnosis. The most important and the most advanced is cancer. So several types of cancers are already being tested, and you probably all heard of the stories of dogs being able to smell cancer. So this is not some science fiction history. It is actually possible to detect different metabolites produced by the cells according to the differences in metabolism, proliferation, activation, inflammation. That can be different between healthy and disease states. So I'm going to keep it as simple as possible because I'm myself getting just introduced to the technology, but from what we know, or what is actually developed today is two types of analysis. One of the two actually measures and identifies the VOC, so it's using mass spectrometry of the exhaled VOCs. So this is very complicated, but it gives you the actual type of VOCs that you have in a sample. And usually this is mostly offline. So it means you have to store the exhalate, send it for analysis in a specialized lab. The other technology that is very rapidly evolving is the electronic nose. So the e-nose, there are several companies that have developed this type of machines. Actually, is a sensor of VOCs. It will not tell you which VOC is in the exhalate, but different sensors in the machine that will come in contact with the exhalate will send a different signal. And so here you talk about the actual components, here you talk about a signature or a breath print. And this is what you analyze against huge databases of known exhale prints. The other very important advantage of this technology is that you actually have a signature as soon as you breathe out into the machine. So, for example, our collaborators that use the e-nose in Amsterdam and work with us, they actually showed that they could detect positive SARS-CoV-2 infected individuals faster than the rapid test. So the one technology that I think you cannot see anything in this, but anyway, what is the biopsy? So the biopsy, of course, as you understand, will give you an idea of the actual different VOCs, and then you can compare it with a VOC biopsy library that is usually built by each company that provides the machine that and the system to measure VOC from your patients. So this is a recent review of biopsies in exhalates, and as you will see in respiratory diseases, COPD, asthma, and ventilator-associated pneumonia and some infections, as well as lung cancer, are the mostly studied diseases so far, with where they have identified specific compounds that are associated with its disease. So here's an example of aldehydes, of organic acids, and et cetera, it goes on. But what I really wanted to show you was that So far in respiratory diseases, only this type, asthma and COPD and lung cancer mainly, have been studied. There are very few studies in ILDs. So the other technology, as I already said, is based on the fact that the eNose technology mimics the human smelling system. So as the people who develop the technology like to put it, you actually don't know you are smelling a rose because you don't know exactly what is in the smell of a rose, but your brain has known from previous experiences and the visual that this is a rose, so you can like smell it with closed eyes. Or so you can think that smell is a complex mixture of VOCs. And then you can think that each disease is a very complex mixture of VOCs, and each individual in each disease will have its own print. So this type of technology is slowly and developing, and you will see more of it now, because now there are more than hundreds of thousands of prints already stored in databases where you can actually go back and look what type of print each person will give. So again, this is the example of how the breath system works as a similar way as our recognition of the smell system. So this is how they also like to depict the signature, because everybody always asks, so okay, but what are you reading and what are you testing? But the actual is that they don't know. They don't know which VOC they're testing. They just see an accumulation of a signature. So the technology that is part of our big biomarker study in the lab is the Spironose, which, as I said, is a very simple exhalation before spirometry. The patient and Evangelia can maybe answer some questions about how easy it is to take the sample. And then online, immediately as the air is sensed, there is an online system that directly conveys the information to the database in Amsterdam, and then they can do the analysis and give out a report. So the type of how the measurement looks is basically looks like this. You have like 7 sensors. And this is like usually how you would do spirometry, but each sensor sends a particular signal. And the most important signal is this part here, which is the prolonged exhalation, and you have the highest concentration of the VOC. So they analyze this part here according to the different sensors. And as I said, each sensor has different sensitivity for a mixture of VOCs. So technically, it's very difficult, I think, to understand if we are not experts in physics, engineering, and biochemistry, but to show you a few papers that maybe help convince you a little bit of the power of the technology. So this was their original study with the eNose, where they could quite nicely separate healthy COPD, asthma, and lung cancer patients. And this is a very early study with few individuals where they had to solve a lot of technical issues. And in this paper, if somebody is interested in the technology, can go and look how they managed to overcome this. And then they send us their unpublished data with a bigger size patient sample. And again, you can see how principal component analysis of the different sensors can actually provide a nice separation of the 4 different types of the diseases in this using eNose. Again, in lung cancer, they have very confident results. They're quite confident in the use of eNose in lung cancer. You can see here the separation between healthy and lung cancer patients. and between asthma and COPD. So it was pretty well established by now that they can actually use this technology for diagnosis of these diseases. They are now taking it one step further into the subtypes and the phenotyping within diseases. So here is a study where they took chronic respiratory patients with asthma or COPD, and they just use an unsupervised analysis, and they could still find a subgrouping of eosinophilic predominant, non-eosinophilic predominance, neutrophilic inflammation, or people who were taking their medicine and were doing great. So this is also very important in this technology now, that you can actually use it to get an idea of what we're talking this morning, that maybe diagnosis is not entirely possible, but for each patient, you can maybe allocate them to different groups that would help disease treatment or prediction. And again, here is a nice correlation they had with the eosinophil counts and the eNOs, and the neutrophil counts and the eNOs. So this is also quite impressive in asthma. And as I said, and the next, what was very interesting for them and very important is, can we detect at baseline which patients will respond to therapy? So this is a study here where they tested lung cancer patients at baseline before and tried to understand if they would respond to anti-PD-L1 treatment. And they went one step further to actually use this technology to say that you can actually have a cutoff here. So patients that are responders are on this line and the non-responders are this line. So basically these people here, there is no point going into treating them with anti-PD-L1, which is a very also expensive therapy. And it depends on the cutoff value that you decide whether you want to lose this patient that maybe he would have responded, or you are more strict in the decision to proceed with therapy. So they also did it post-therapy, so immediately after treatment, so that another issue that was also raised this morning, that maybe you can start a therapy and then very quickly want to know if you have a response or not, and then stop it early enough, not wait for a whole year. So I guess all these things are very relevant to ILD treatment and decisions. So let's see what they have done for ILDs. So clearly, they can show very nice discrimination of healthy versus ILD patients. I will not go into all the details, but you can contact us and them for more information regarding this technology. They are very eager to collaborate and hear from you. Another very interesting comparison was IPF versus non-IPF individuals. And again, with not so many numbers, but still you can show a discrimination. And then it starts to get too good to be true, as Katerina says. You can actually discriminate chronic HP from IPF, which could make sense because it's a very different inflammatory profile. And this is what you have to keep in mind with the power of this technology. It might not reflect HRCT, UIP, probable UIP, or the other spirometric components, but it's very, very good at detecting inflammation and the hundreds of different types of inflammation for each disease. So I believe that this technology is very useful in this area. So you can see, for example, I don't know if there is an IPAF slide, but I think there was at some point. So not to take too much of your time, the idea is that there are many advanced studies up to this stage, stage 4, study cohort with external validation. There is no yet evaluation in clinical practice, but they are very close. As you can see, some of the areas are quite close. And this is the research pipeline of the technology that we use in the lab. So you can see already validation for COVID. I went really, really fast. And this is just a reminder that in our big biomarker study, we are actually measuring both signatures with the eNose, and we are collecting breath biopsies to be analyzed at baseline, 6 and 12 months. And this, I hope, will give a further indication about therapeutic, diagnostic, prognostic. And of course, this study is designed by BI also, and they were very, very keen in involving VOC measurements in our experimental procedures. And I think they were really right. So thank you very much for your attention. I hope you are more familiar a little bit with the VOC and all this technology.
Thank you very much, Elisa. This is really new methods very promising to help us for diagnosis and monitoring several respiratory diseases. The question is how far or how close we are this technique to become routinely used clinical practice. I'm not very sure. That's okay.
Why?
Okay.
Thank you, Elisa, for the talk. They indeed seems very promising, all these techniques. I was impressed about what you said about the detection of COVID. I would like your comment on that. And if you know any other possibility for other infections or something that could be helpful in everyday clinical practice.
Yeah, I think the main clinical application now is just this that is approved. But you can imagine why, because an infection will cause inflammation in the lungs. So, and all viruses interact very differently with our innate immune system and our adaptive. So I guess there is a lot of area to understand the different infections. But for ILDs also, I think it's very important, and I'm very curious what the study that we're doing in the lab will show and how they will be able to analyze the data of the patients before and after therapy and see which patients have, what they really would like to do actually is to correlate the eNose signatures with the BAL cell counts and correlate whether there are lymphocytes, higher amount of it. And they are very interested in this type of correlation as in asthma, because these cells are quite actively metabolically and actually provide these discriminating signatures that the eNose might detect.
Professor Bosios.
Excellent presentation, excellent work. We have some in Karolinska put patients with asthma, and there are very promising results because you get the very distinct phenotype or result directly. So I think it can. I think it's close. It is close. That I think the next year in our clinical practice we will find that in front of us. But I think what you say, this is unique. Because I know that this is the problem. The most of the studies, they have clinical characterization of the past. You know, eosinophilic asthma, for example. They don't have BALF data. So I'm very hopeful, and I think this is unique you're doing. If you are going to get your cellular data inflammation with their phenotyping. This could be unique because this is what we are missing. We don't know which is what.
Exactly, and in our study, we will not only have the cell numbers, we will have single cell analysis and transcriptomic analysis and proteomic analysis. So they will be able to link, I hope, certain pathways in different patients, in different diseases, like we will have IPF and chronic HP and CTD, ILDs, and not clearly diagnosed ILDs. We have a group like this in the study. And I think it will really help us identify certain leads for further testing among the different groups. So as for clinical practice, Katerina and the people who do it at work, they will say to you that it's quite easy, actually.
Yes,
so
you just brief. Yes, excellent. This is what is missing.
Yeah. But I don't take the credit for it. I'm just presenting for them. Yes. I haven't done anything about this.
Very nice presentation as the previous one. My question is that because nose is so sensitive, the environment can change the answer. So the fingerprint that I have in Stockholm could be different compared to the fingerprint here in Crete.
Yes, so as I said, these were the major hurdles of using this technology and implementing it and creating systems that can actually be sold to clinicians. And in the eNose in particular, what they have is a system where they have the outside sensors and the inside sensors, and they are the same sensors, but they are also measuring environmental cues at the same time as they measure the exhaled breath. So the combination of the outside response of the sensors of the outside environment with the exhaled breathing is what gives the signature. So the signature is not so simple. The data from a single breath on the eNose comes from, let's say they have, I think, 4 inside sensors and 4 outside sensors, each one with 7. So it's their ability is their strength, let's say, is based on the amount of data they collect. And this is how they regulate. And I think the only problem that this technology has for a normal hospital room is that it requires no alcohol in the room. So that's the only limitation that they asked for the measurement. Please do not use any alcohol. So that's the only thing that their system cannot deal with as of environmental problem.
If I may add to the discussion, because I have no input from the room you are right now. First of all, thank you very much for this very interesting talk. My prior experience with exhaled breath condensate, which is not, of course, not exactly the same with the eNose procedure, is that all these procedures have some methodological issues regarding standardization, dilution, environmental factors that you've discussed already, as well as factors that influence the results regarding the patient, let's say food intake prior to the examination and stuff like that. Do these things now have solutions in the eNose procedure?
Yeah, for the eNose, they convince us that this is not an issue apart from the thing with environmental alcohol. For the
so if the patient consumes alcohol before the examination, doesn't that...
At all in the room. It should be a room without alcohol, alcohol-free room. That's
if he consumes alcohol, if he has alcohol...
Yes, thank God they have a very small room in the hospital and they... So, but the condensate and the problems that you described, they were actually addressed also in the mass spec device that we are using. So what they are doing there is that they don't use condensates. They actually have a tube with sorbent metals, and they kind of trap the VOCs, and you don't need to have them cold. You can ship them, and so the technology has advanced in levels that we do not understand because it's engineering and chemistry.
Perfect.
And but this is that's what one of my first slides was, because they really stressed how much work they had to do to standardize the method. And I think this is, as you say, this is the main problem why clinicians don't trust it so much. But I'm sure you wouldn't use only this readout to make any decisions anyway. It's just a help.
Okay.
We have time only for one more question. Okay.
Yeah, just to ask you, and I'm sorry if I missed this being a bit late for the start of your talk, do you have a sense that various anti-inflammatory treatments change the signal?
Yeah, they do. I think this is what you can really show, that the treatment response is actually very easily and nicely measured. So that's another very powerful aspect of this technology. You can very quickly, without a lot of tests, perhaps check the response for your asthma treatment, for example.
Or treatment in CHP, for example. Do you have a sense that early response in the signal predicts a better treatment outcome? Or have you looked at that?
We have not looked. We will see. We will see how it will look in the ILD cohort of Katerina. I really don't know. Yeah, we need to be patient for a couple of years before we have all this data. For the moment, we're just working.
Of course, more pain. Due to difficult.
I wonder why I said that.
Due to difficult terminology of the topic, I have the permission from the organized committee. If someone of the audience has to ask something in Greek language, please feel free to ask something.
No.
Italian? Okay, we don't know Italian. Okay, Kostas, you can present the next speaker.
One short question, sorry. I think that urine should be more clean for the analysis. Do we have this kind of analysis for urine?
So for urine, we don't have the analysis, but for urine, you would have to have something on top of your urine sample to smell it, right? Yeah. So this is called, it's a third, I didn't put it in the presentation, it's the third type of VOC, which is called headspace measurement. It's used in plants, like you can put a jar on a plant and then collect. So, for example, with urine, you could actually do that.
Kostas, I want to say that due to a misunderstanding, Dimitris has prepared his talk in Greek language, but I don't know if he can speak in English. You can present him.
Yeah, I'll present him and he'll answer the question himself, I suppose. Well, it's an honor to present Dr. Toumpanakis. He's a fellow pulmonologist / intensivist in the 4th Respiratory Medicine Department here in Athens Children's Hospital, Soteria. And he's going to give an excellent presentation regarding oscillometry.
One moment to share my screen. Okay. Do you see my screen? It's okay?
Yes, we can see.
Okay. So first of all, I would like to thank the organizing committee and my friend Katerina Antoniou for the invitation, and to apologize for my English, because indeed I prepared the talk in Greek, so I will try to do a translation. So we'll talk about oscillometry.
You talk in Greek language if you want.
Okay, εντάξει. Ωραία, εντάξει. Ωραία, βάλαμε την ταλαντοσημετρία στις νεότερες τεχνικές, ωστόσο πρέπει να πούμε ότι σαν θεωρία η ταλαντοσημετρία υπάρχει από πολύ παλιά, ήδη από το 1955 βλέπετε δημοσιεύσεις γιατί οι φυσιολόγοι ήταν από παλιά, έδειχναν ιδιαίτερο ενδιαφέρον να μελετήσουν τις μηχανικές ιδιότητες του αναπνευστικού σε πάρα πολλές κάτω από διαφορετικές συχνότητες και ταλαντώσεις, διότι μπορούμε να πάρουμε έτσι περισσότερες πληροφορίες για το αναπνευστικό σύστημα. Ωστόσο, όντως, τα τελευταία χρόνια η ταλαντοσημετρία έχει λάβει πάρα πολύ μεγάλη αξία, και αυτό διότι πρώτα απ' όλα έχουμε πλέον μηχανήματα που είναι πιο εύκολα διαθέσιμα και στην κλινική πράξη, αλλά και γιατί έχει φανεί ότι είναι ένα εργαλείο με το οποίο μπορούμε να μελετήσουμε τους μικρούς αεραγωγούς, καθότι μέχρι τώρα δεν έχουμε κάποια gold standard μέθοδο για να μελετάμε τους μικρούς αεραγωγούς, και ξέρουμε ότι οι μικροί αεραγωγοί παίζουν πάρα πολύ μεγάλη σημασία και στη χρόνια αποφυλακτική πνευμονοπάθεια. Το ξέραμε από παλιά, αλλά ειδικά τώρα έχουν εκεί μελέτες, seminal studies στο New England για παράδειγμα, που δείχνουν ότι μέχρι και στους ασθενείς με εμφύσιμα έχουμε πρώτα παρουσία νόσου των μικρών αεραγωγών και μετά εμφανίζεται το εμφύσιμα. Για παράδειγμα, βλέπετε εδώ δεξιά, έχουμε ασθενείς με εμφύσιμα και τι βλέπετε, ότι στις περιοχές που δεν έχουν ακόμα εμφανίσει εμφύσιμα ξεκινάμε να έχουμε βλάβη και απώλεια των μικρών αεραγωγών. Άρα λοιπόν οι μικροί αεραγωγοί φαίνεται μάλλον να εμφανίζονται πιο γρήγορα από το εμφύσιμα, και ξέρουμε ότι οι αλλοιώσεις στο τείχομα των αεραγωγών και η απόφραξη προκαλείται είναι αυτό που προκαλεί κυρίως τον περιορισμό της εκπνευστικής ροής στους ασθενείς με χρόνια αποφυλακτική πνευμονοπάθεια. Και επίσης έχει φανεί και με μελέτες όπως για παράδειγμα με την Atlantis Study, ότι η νόσος των μικρών αεραγωγών εμφανίζεται σε όλα τα στάδια του άσθματος και ιδιαίτερα στους ασθενείς με σοβαρή νόσο. Άρα λοιπόν χρειαζόμαστε την ταλαντοσημετρία για να μελετήσουμε τους μικρούς αεραγωγούς, και γι' αυτό τον τελευταίο καιρό συζητάμε πάρα πολύ για την ταλαντοσημετρία. Πώς γίνεται αυτό? Στην ουσία έχουμε εδώ έναν ασθενή που αναπνέει ήρεμα και στη συνέχεια με ένα μηχάνημα έχουμε ένα σήμα με πολλαπλές ταλαντώσεις, το οποίο επιπροβάλλεται πάνω στην ήρεμη αναπνοή του ασθενούς. Άρα ήδη εδώ έχουμε μια πολύ μεγάλη διαφορά με την σπυρομέτρηση, ότι δεν χρειάζεται ο ασθενής να κάνει κάποια βίαιη εκπνοή, δεν χρειάζεται καν να συνεργαστεί. Το μόνο που χρειάζεται είναι να στηρίζει τα μάγουλά του για να μην έχουμε έτσι artifacts από τους ανώτερους αεραγωγούς, και στην ουσία απλά όπως αναπνέει ήρεμα επιπροβάλλεται ένα κύμα στην αναπνοή του. Τώρα αυτό το κύμα μπορεί να έχει διάφορες μορφές, να έχει μία συχνότητα, πολλαπλές συχνότητες, αυτό που λέγεται pseudo-random noise. Μπορεί να προκαλέσει κάποιες διαφορές στα αποτελέσματα αναλόγως τι χρησιμοποιούμε, όμως αυτό τώρα είναι αρκετά, δεν χρειάζεται να το αναλύσουμε στην παρούσα παρουσίαση. Σημασία έχει ότι ό,τι και να χρησιμοποιήσουμε θα πάρουμε σαν μέτρηση την εμπέδηση του αναπνευστικού συστήματος. Και τι είναι η εμπέδηση του αναπνευστικού? Μπορούμε να την έχουμε στο μυαλό μας σαν τη συνολική αντίσταση, και είναι ο λόγος της πίεσης διατηρωή. Και μάλιστα γιατί παίρνουμε περισσότερες πληροφορίες, διότι βλέπετε ότι αυτά εκφράζονται σαν συνάρτηση της συχνότητας ταλάντωσης του αναπνευστικού συστήματος. Άρα λοιπόν παίρνουμε ένα τελικό σχήμα, όπου στον άξονα του ψ έχουμε την εμπέδηση και στον άξονα του χ έχουμε τη συχνότητα. Και βλέπετε εδώ ότι συνήθως οι συχνότητες που μελετάμε είναι γύρω στο 5 έως 20. Είναι και συχνότητες που εδώ δεν χρειάζεται να έχουμε συνεργασία του ασθενούς. Και η εμπέδηση μετά χωρίζεται σε δύο συνιστώσεις. Στη μία είναι η αντίσταση, βλέπετε εδώ από πάνω, πώς εξαρτάται η αντίσταση του αναπνευστικού συστήματος από τη συχνότητα. Και παίρνουμε συνήθως σαν παραμέτρους το R20 που εκφράζει κυρίως τους μεγάλους αεραγωγούς και το R5 που εκφράζει τους μικρούς αεραγωγούς. Και παίρνουμε και μία άλλη συνιστόσα που ονομάζεται reactance. Τώρα αυτό δεν ξέρω πώς μεταφράζεται ακριβώς. Ανάδραση, επαγωγική αντίδραση, τέλος πάντων δεν έχει σημασία. Reactance, το οποίο με τη σειρά της εξαρτάται από την ελαστικότητα του αναπνευστικού συστήματος και από την αδράνεια. Βλέπετε εδώ ότι αυτή είναι η συνάρτηση της reactance με τη συχνότητα. Κάποια στιγμή συναντάει τον άξονα του Χ και αυτό εδώ είναι η resonant συχνότητα. Είναι η συχνότητα που στην ουσία η επαγωγική αντίσταση ισούται με την αδράνεια. Και πάλι παίρνουμε τη reactance στη συχνότητα 5 σαν παραμέτρους και επίσης παίρνουμε και το ευαδόν εδώ κάτω από την καμπύλη. Τώρα, γιατί μας ενδιαφέρουν όλα αυτά? Διότι έχει φανεί ότι ανάλογα της παθολογίας που έχουμε στο αναπνευστικό σύστημα, οι παράμετρες αυτοί αλλάζουν διαφορετικά και μάλιστα μπορούν να μας δώσουν πολύ πιο καλή απάντηση για αυτό που λέμε το structure function, δηλαδή για το πώς σχετίζεται η λειτουργικότητα με τη δομή. Για παράδειγμα, βλέπουμε εδώ μία νόσο του αναπνευστικού που προκαλεί κυρίως στένωση των μεγάλων αεραγωγών. Η διαφορά που θα πάρουμε εδώ στην ταλαντοσημετρία είναι ότι δεν θα αλλάξει η reactance, αλλά θα αλλάξει κυρίως η αντίσταση και μάλιστα θα έχουμε την ίδια αλλαγή σε όλο το εύρος των συχνοτήτων. Τι γίνεται όταν έχουμε restriction, δηλαδή έχουμε περιορισμό. Όπως ξέρουμε, ο περιορισμός θα αυξήσει την ελαστικότητα και θα δούμε μια μετατόπιση της elastance και άρα και της reactance προς τα κάτω. Δηλαδή, στην ουσία αυτό γίνεται πιο αρνητικό, άρα αυξάνει σε απόλυτο αριθμό η reactance. Γιατί το πιο σημαντικό που μας ενδιαφέρει, γιατί αυτό βλέπουμε και σε νόσους μικρών αεραγωγών, είναι τι γίνεται όταν έχουμε στένωση των μικρών αεραγωγών και μάλιστα και ανομοιογένεια. Βλέπετε, δεν έχουμε δηλαδή την ίδια αλλαγή σε όλα τα μέρη του αναπνευστικού. Εδώ θα δούμε ότι έχουμε μία αύξηση της αντίστασης, η οποία όμως εξαρτάται από τη συχνότητα. Στις μεγάλες συχνότητες, οι οποίες είπαμε κυρίως εκφράζουν τους μεγάλους αεραγωγούς, έχουμε μια μικρή αύξηση. Αυτό που θα παρατηρήσουμε όμως κυρίως είναι να αυξάνει η αντίσταση στις χαμηλότερες συχνότητες, κοντά στο 5. Και το ίδιο βλέπουμε και για την ελαστικότητα. Άρα λοιπόν, ιδιαίτερα για την νόσο των μικρών αεραγωγών που μας ενδιαφέρει στην ταλαντοσημετρία, αυτό που θα δούμε είναι να αυξάνει το R5, να αυξάνει η διαφορά του R5 από το R20, να γίνεται πιο αρνητικό η reactance στη συχνότητα 5 και να αυξάνει και αυτό το εμβαδό. Απλά εδώ θέλω λίγο να εφιστήσω την προσοχή σας ότι επειδή έχουμε μια τάση οποτεδήποτε βλέπουμε αύξηση της αντίστασης στις χαμηλές συχνότητες να θεωρούμε ότι είναι νόσος των μικρών αεραγωγών, δεν είναι συνώνυμο. Έτσι, εάν έχουμε ανομοιογένεια στο αναπνευστικό σύστημα, θα έχουμε πάλι την ίδια απάντηση. Και το ίδιο ισχύει, βλέπετε εδώ, και για την reactance, γίνεται πιο αρνητική και ο λόγος είναι και η ετερογένεια, αλλά και η νόσος των μικρών αεραγωγών. Και μπορεί να σκεφτεί κάποιος γιατί η νόσος των μικρών αεραγωγών μπορεί να συνοδεύεται με στην ουσία αύξηση της ελαστικότητας στις χαμηλές συχνότητες, διότι όταν έχουμε νόσο των μικρών αεραγωγών, βλέπετε εδώ μπορεί να έχουμε closure των μικρών αεραγωγών και έτσι υπό δυναμικές συνθήκες εδώ να φαίνεται ότι έχουμε μεγαλύτερη ελαστικότητα. Τώρα, στην κλινική πράξη, πού μπορεί να μας βοηθήσει η ταλαντοσημετρία? Έχει φανεί με αυτή την πολύ ωραία μελέτη ότι η ταλαντοσημετρία, επειδή ακριβώς ανιχνεύει την νόσο των μικρών αεραγωγών και η μικρή αεραγωγή είναι αυτή που κυρίως από εκεί ξεκινάει η βλάβη, μπορεί να χρησιμοποιηθεί για να ανιχνεύσουμε την πρώιμη νόσο. Και αυτό έχει πάρα πολύ μεγάλη σημασία και πρόσφατα υπήρχε και πολύ ωραία δημοσίευση στο Blue Journal για το πώς πρέπει να αρχίσουμε σιγά σιγά να ασχολούμαστε με το pre-COPD. Τι βλέπετε εδώ? Βλέπετε ότι σε σχέση με καπνιστές οι οποίοι είχαν συμπτώματα, ακόμα και να μην είχαν αλλαγή στη σπυρομέτρηση, έχουμε αύξηση των δικτών που δείχνουν νόσο των μικρών αεραγωγών. Έχει φανεί επίσης ότι η ταλαντοσημετρία, οι παράγοντες δηλαδή που παίρνουμε από την ταλαντοσημετρία, σχετίζονται με τη φλεγμονή. Βλέπετε εδώ ουδετερόφυλλα λεμφοκύτταρα. Καπνιστές που έχουν παθολογική ταλαντοσημετρία έχουν περισσότερα ουδετερόφυλλα, περισσότερα λεμφοκύτταρα και έχουν και σε σχέση και με τους φυσιολογικούς αλλά και με καπνιστές που δεν έχουν παθολογική ταλαντοσημετρία αύξηση των δικτών φλεγμονής όπως την τελευκίνης 8 και τσιοταξίνης. Επίσης, η ταλαντοσημετρία μπορεί να μας βοηθήσει να κάνουμε monitoring της νόσου και αυτό διότι βλέπετε ότι όσο αυξάνει το σπυρομετρικό στάδιο, όσο δηλαδή έχουμε gold 1, 2, 3 κατά σπυρομέτρηση. Κατά αντίστοιχο τρόπο βλέπετε και μεταβολές στην ταλοντοσημετρία. Βλέπετε εδώ, για παράδειγμα, σε σχέση με την ήπια νόσο, στη σοβαρή νόσο έχουμε αύξηση της αντίστασης και ιδιαίτερα, όπως έχουμε πει, στις χαμηλές συχνότητας, αυτό που λέμε το frequency dependence, και κατά αντίστοιχο τρόπο έχουμε μεγαλύτερη μεταβολή και στην reactance. Και επειδή πρέπει πάντα να κοιτάμε και αυτό που λέμε τα patient-reported outcomes, έχει φανεί ότι οι δείκτες λειτουργικότητας των μικρών αεραγών σχετίζονται σε σημαντικό βαθμό και με τα συμπτώματα και με τη δύσπνοια, βλέπετε εδώ σημαντική συσχέτιση, όπως και με την ποιότητα ζωής, όπως εκφράστηκε με το St. Joseph's Respiratory Questionnaire. Τώρα, υπάρχουν επίσης στη βιβλιογραφία και μελέτες που έχουν δείξει ότι μπορούμε επίσης να πάρουμε πληροφορίες όταν αναλύσουμε την ταλοντοσημετρία μέσα σε έναν αναλυτικό κύκλο. Δηλαδή, αν πάρουμε, όχι να παίρνουμε τη μέση εμπέδηση, αλλά να παίρνουμε την εμπέδηση κατά την εισπνοή σε σχέση με την εμπέδηση στην εκπνοή, έχει φανεί, βλέπετε εδώ για παράδειγμα, δεν έχουμε μία τιμή, αλλά έχουμε τι γίνεται στον αναμνηστικό κύκλο. Βλέπετε εδώ ότι στους ασθενείς με χρόνια αποφρακτική πνευμονοπάθεια έχουν μεγαλύτερη εμπέδηση κατά την εκπνοή, προφανώς διότι υπάρχει μεγαλύτερη σύγκληση των αεραγών στην εκπνοή, ενώ αντίθετα στους ασθενείς με άσθμα δεν το παρατηρούμε αυτό και επομένως μπορεί ίσως αυτή η τεχνική να μας βοηθήσει να διακρίνουμε και ασθενείς με χρόνια αποφρακτική πνευμονοπάθεια από ότι ασθενείς με άσθμα. Έχει χρησιμοποιηθεί επίσης η ταλαντοσημετρία για την ανίχνευση του περιορισμού της εκπνευστικής ροής. Βλέπετε εδώ για παράδειγμα ασθενείς με χρόνια αποφρακτική πνευμονοπάθεια. Η διαφορά που έχει η εμπέδηση εισπνοή με εκπνοή στους ασθενείς που παρουσιάζανε περιορισμό της εκπνευστικής ροής ήταν αυξημένη σε σχέση με ασθενείς που δεν παρουσιάζανε. Και επίσης τον τελευταίο καιρό έχουν βγει και αυτό είναι δημοσίευση από το 2013, αλλά βγαίνουν πλέον και αρκετές μελέτες, με το οποίο μπορούμε να μελετάμε και την απάτηση στη βροχοδιαστολή με τη χρήση της ταλοντοσημετρίας. Και σύμφωνα με τα τεχνικά στάνταρ που έχουν δημοσιευθεί το 2020 στο ERJ, βλέπουμε ότι μία 40% μείωση στην αντίσταση στα 5 Hz ή 50% αύξηση της reactance στα 5 Hz θεωρείται σαν όριο για να έχουμε μια θετική απάντηση στη βροχοδιαστολή. Τέλος, σε πιστεύω πιο πολύ ερευνητικό επίπεδο, αλλά μελλοντικά μπορεί να είναι και χρήσιμο στη κλινική πράξη, ακριβώς επειδή η ταλαντοσημετρία δεν απαιτεί κάποια συνεργασία από τον ασθενή, μπορεί να χρησιμοποιηθεί και για τη μελέτη των μηχανικών ιδιοτήτων σε ασθενείς που δεν μπορούν να συνεργαστούν, όπως για παράδειγμα σε διασωληνωμένους ασθενείς ή σε ασθενείς που είναι σε μη επεμβατικό μηχανικό αερισμό, και πιστεύω μελλοντικά ότι αυτό θα μας φανεί πολύ χρήσιμο. Φανταστείτε πώς θα ήταν να μπορούσαμε να έχουμε έναν ασθενή σε παρόξυση και να μπορούμε να μετράμε τις μηχανικές ιδιότητες χωρίς να χρειάζεται να κάνουμε σπυρομέτρηση. Άρα λοιπόν η ταλαντοσημετρία, και έχω γράψει εδώ forced oscillation technique, θέλω να ξεκαθαρίσω ότι αυτό forced, δεν υπάρχει κάτι forced στην ταλαντοσημετρία. Είπαμε ο ασθενής αναπνέει ήρεμα και απλά επιπροβάλλεται το σήμα. Άρα λοιπόν μην μπερδευόμαστε, το forced εδώ δεν σημαίνει για παράδειγμα όπως με τη σπυρομέτρηση. Έτσι λοιπόν μπορεί να μας βοηθήσει να ανιχνεύσουμε την πρώιμη νόσο και να βάλουμε διάγνωση. Σχετίζεται με τη σοβαρότητα της νόσου και τα συμπτώματα. Μπορούμε να κάνουμε να μελετήσουμε τη βροχοδιαστολή και να κάνουμε και monitoring των ασθενών μας. Είπαμε ότι δεν απαιτεί τη συνεργασία του ασθενούς, έχει καλύτερη σχέση με την ανατομία. Υπάρχουν βέβαια ακόμα κάποια ερωτήματα, υπάρχουν διάφορες συσκευές και μεταξύ τους δεν είναι πάντα και τα αποτελέσματα, υπάρχουν κάποιες μικροδιαφορές. Υπάρχει ένα θέμα με τις προβλεπτικές εξισώσεις. Πιστεύω ότι όσο αυξάνει η χρήση της ταλαντοσημετρίας, τόσο αυτά τα ερωτήματα θα απαντηθούν. Και απλά θέλω να δείξω εδώ, αυτή η μελέτη προσπάθησε να δει λίγο τη σπυρομέτρηση σε γυράσκον πληθυσμό. Βλέπετε ότι η ηλικία, και ιδιαίτερα όταν συνδυάζεται και με με γνωσιακά προβλήματα, είναι ένας παράγοντας για να έχουμε κακή συνεργασία του ασθενούς στη σπυρομέτρηση. Άρα λοιπόν σε αυτούς τους ασθενείς ειδικά, όπως και στα πολύ μικρά παιδάκια, μπορεί να έχει μεγάλο όφελος στη ταλοντοσημετρία. Έχει φανεί ότι είναι γενικά, έχει καλή επαναληψησιμότητα και έτσι φτάνουμε σε ένα σημείο που, όπως κοιτώντας τη σπυρομέτρηση μπορούμε να δούμε, βλέπετε εδώ για παράδειγμα, χωρίς να έχουμε ούτε δείκτη τυφενό ούτε τίποτα, αν βλέπαμε αυτή τη σπυρομέτρηση θα λέγαμε ότι εδώ προφανώς ένας ασθενής με απόφραξη, εδώ είναι προφανώς ένας ασθενής με περιορισμό. Μακάρι να φτάσουμε σε ένα σημείο να κοιτάμε και την ταλαντοσημετρία και να βλέπουμε εδώ τις χαρακτηριστικές μεταβολές που έχει η αντίσταση και η reactance και να μπορούμε να βάζουμε έτσι και τη διάγνωση. Γενικά η ERS έχει κάνει τον τελευταίο χρόνο μια προσπάθεια για να γίνει μια έτσι, ένα σταντάρισμα της οσcillομετρίας και έχει δημοσιεύσει τα τεχνικά standards και πρόσφατα δημοσιεύτηκα και η κλινική χρησιμότητα. Μπορεί όποιος θέλει να βρει τις δημοσιεύσεις στο διαδίκτυο και για όποιον ενδιαφέρεται και περισσότερο και για τη μηχανική από πίσω υπάρχει αυτό το πολύ ωραίο βιβλίο του Bates και ένα πάρα πολύ ωραίο review του ίδιου συγγραφέα στο Comprehensive Physiology. Και με αυτή τη διαφάνεια σας ευχαριστώ πάρα πολύ για την προσοχή.
Thank you very much, Dimitris. The value of oscillometry seems that from the fact that ERJ already published 2 papers for this method, and they are free to download if someone wants to take. You can download it. We know that this technique can diagnose the small airways disease. Nowadays, can we talk that this is the method that can distinguish the patients with obstruction from healthy subjects? And if can distinguish the patients with obstruction, like asthma or COPD, from different degree of obstruction?
So the main problem with techniques that have a high sensitivity is that sometimes you may overdiagnose, and possibly for oscillometry this is also the case. So it may be very easy with oscillometry to say that someone has a small airway dysfunction, and so I think that we have to find out exactly who these patients are, that with oscillometry we can diagnose obstruction that have also symptoms and etc. So indeed, because it's very sensitive to detect changes in small airways, we might get an issue in overdiagnosis. And for that reason, I want to say that oscillometry does not replace all the other techniques, that we have to think oscillometry as something to add on in our tools we have to diagnose our patients. And to distinguish between asthma and COPD, it is a study that I saw you from Professor Usmani, who showed that the difference between reactants in inspiration and expiration may allow us to detect the COPD patients instead of asthma patients.
It's a cheap method with accurate and reliable results. So I think if someone he can use it, it's very cheap. Professor Tzanakis.
Dimitris, thank you for your excellent talk. I'd like to ask you...
Please, can you use the microphone?
The small airways mechanics depends somewhat with the lung expansion and the lung mechanics. On the other hand, lung mechanics are also based on extra lung mechanics like chest wall. Do you think that in the mixed problems with chest wall problems like obesity, like kyphoscoliosis, like myopathy, maybe have the same accuracy, or these circumstances affect the measurements of oscillometry?
Yeah, you are right that sometimes with oscillometry it's not very easy to discriminate between obstruction and restriction, but especially for extra thoracic diseases, I believe that the changes that we are going to see with are going mostly to see changes in reactants and not that much resistance. So I try to remember if I have seen a study with oscillometry and extrathoracic disease, but I cannot recall such a study at that point. But I think that you may get changes in reactants mainly and not so much at the resistance.
Is there any other question from?
If I may add, Kostas. Dimitri, thank you very much for this excellent presentation. The place of oscillometry for small airways disease is well placed and well based. We all know that. Do you think there's enough evidence to use oscillometry in rather rare instances where you have small airways disease, like in bronchiolitis obliterans in transplantation patients, to detect that maybe even earlier than when the clinical issues emerged?
Yes, and I think that when oscillometry becomes even more easy to have, then we will get more and more clinical experience with this technique. And of course, to have a tool that you can detect early bronchiolitis, that would be very helpful. So I think that we need to start using it to get experience, and then we'll see that we are able to detect the changes early. And an issue is that to see if we detect early and we treat early, we will also see a change in the course of the disease. So all these are questions that need to be answered. But as we all understand, especially for bronchiolitis that you said, if you are able to detect it better, then better for the patient.
We have one last question, and Kostas, after that you can close the table.
Okay. Dr. Toumpanakis, thank you very much for your great presentation. It's Kostas Karagiannis from Heraklion, Crete. I would like to ask you, at your impulse oscillometry method, do you use the percentage of the predicted value as the result, or the Z-score and minus 1.6 for standard deviation? And what about, sorry, and a second part question, what about the reference values for impulse oscillometry?
Yeah. Yes. So as I said also in my presentation, we have an issue with reference values for oscillometry. We need studies with that will definitely have reference values. But I think this is a general question. I think it's what you do also with spirometry, and so it's better to use the lower limit of normal. So it's better to use a Z-score. But of course, we are used also to have the percentage. So I see both of them. But okay, to be honest, from scientific value, I think it's better to use a Z-score. But we are used to having the 80% predicted values as normal. But I think that the trend lately is to use the Z-score and the lower limit of normal.
Costa.
Before to
Okay.
conclude,
Do we have any more questions?
Katerina has something to say.
Yes, just I would like to thank Dimitris for this nice lecture. To say that Dimitris is currently in London in Imperial College, and he's working with Professor Omar Ousmani, who is also the head of the Airways Assembly of European Respiratory Society. And we have also with us Apostolos Bosios, who is the secretary of the ERS Assembly group. And as he's in London and he's nearby the Royal Brompton Hospital, and I'm taking the opportunity to ask him about some studies in smaller ways with oscillometry in interstitial lung disease, and if not, to further, collaborate and sharing some ideas in this field. Dimitris?
Yes, I think that Okay, I'm mostly interested in obstructive disease, but I've seen lately some small studies regarding small ergos and fibrosis. And I think that's a field where we can do more. And happy to collaborate and with you, Katerina, also, and to see more studies about. But I think there are some published studies showing that with oscillometry you can have some results in fibrosis patients. And I believe there is some data now.
Okay, excellent. I guess there are no more questions. In that case, I would like to thank everybody for being here today. It was a very interesting session, I believe. I'm very sorry again for not being there, and thank you very much, Professor Antoniou, for the invitation. Let's continue with the program, okay?
Thank you. Next year in Heraklion, all of you.
Yeah, I will.
Pick also Omar to come with data in interstitial lung disease. He's working with Elizabeth Renzoni, so both of them and you, and of course Kostas in Heraklion next year. Save the date.
Thank you, and bye-bye, Apostolos. I didn't see you, but bye-bye.
Bye, Dimitris.
Bye.
Dr. Koutsopoulos, who is Kostas Karagiannis and Irini to chair.
Good afternoon. Thank you and honor for being invited in this very important congress held from Respiratory Department of the University of Heraklion. And thank you to the organizing committee, especially Professor Tzanakis, Professor Antoniou, and Professor Schizer for this honor. And we have between us two distinguished colleagues, two very eminent science, full of success, Professor Venerino Poletti from Italy, Forlì, and Professor Crestani, who will be connected online, to tell us about cryobiopsy versus genomic classifier. To my opinion, genomic classifier is not well known in Greece. I don't know what means genomic classifier testing, and we will see now. Professor Poletti.
Thank you very much, Iraklis, for your kind introduction. And I have a great pleasure to, may I have the slides? Good afternoon, Bruno. You are my opponent. Can you see my slides?
We see Bruno actually, but
if I can have my slides, I would like to know if Bruno can see the slides. No.
Okay, it's better, Bruno.
So this is a genomic classifier, is Bruno. So I think
I don't see you.
But you should see the slides.
No, not yet.
Not yet. One second. So how is the weather, Bruno? We are very English. How is the weather in Paris now?
It's raining.
Oh,
it's raining.
Good. It's very English. Very, very English. Can you see the slide now?
Yes, perfect. Thank you.
Okay.
So, you know, there is a very, very famous novel in Italy now by Enrico Pandiani, and the name of the novel is Les Italiens. It's a detective novel, and the subject of this novel is a group of detective Italians that live in Paris. So the comment about this novel is that Italians are usually good detectives. They are even better when they live in Paris. So I have a tough job, you see my face here, to debate with Bruno regarding this issue, this topic. So the first point is genomic classifier. How does it work? It's a strange analysis taking into account fingerprints, but it works in that way, very simple way. You collect 3 to 5 transbronchial samples, you put them in a jar, in something that is outside the common way, so you don't have microscope, and you have a final answer after RNA analysis. I think almost 200 genes are analyzed. You have yes or not, or no or yes. So for UIP is a binary answer. Here we have the paper, I think the important paper on the topic by our friend Luca Richeldi. What is clear is that and I have the luck, the fortune to have here Arthur Wells that can comment on that. The sensitivity of the test for UIP is 60%, and the specificity is 92%, with a predictive positive value of course, 92% and negative predictive value of around 60%. The test was validated in this cohort of patients, mean age 63 years. The UIP frequency, according to pathology, was 60%. But what were the patients not included in the validation process? 33 patients, they didn't have specific pathological patterns. The majority of them were females, and the majority of them had not surgical lung biopsy. So, taking into account this data, probably the analysis was done in a very selected group of patients. And if we consider this approach, we have the pretest probability of an event. It depends on the prevalence of the disease at the moment, or it depends, as suggested by Arthur, on the single probability of the event, if you consider age, high resolution CT scan, and so on. And you have a test that can have a likelihood ratio. This is the formula for the likelihood ratio. And if you see here, the likelihood ratio, according to the data provided from the article, Luca article, you see that if you have a prevalence of 60% and a likelihood ratio of 6.2, at the end, the probability to have the disease for the single patient would be more than 90%. But if we have a prevalence or a frequency of 30%, the answer, the final answer will be 75%. So it works well in a scenario in which the pretest probability of having UIP is high or significantly more than 30%. Assuming that likelihood ratio stays stable if we change the pretest probability of the event, and I think is not true. Other point to define. Among the different UIP patterns reported by central pathologists, we have a definite pattern was detected only in 55% of cases. We have probable pathology in 45. The classifier had false negative mainly when UIP pattern was discordant. And you see here, of course, when the information provided with the genomic classifier was added into or inserted into the multidisciplinary discussion, we have an increase of confidence of the diagnosis. So criticism, we lose material. 3 to 5 transbronchial biopsy samples in different lobes have to be pulled. We don't need microscope. We have yes or not. We have not a differential list of diagnosis, and by serendipity, we are not able to detect other entities, such as, it happens, microscopic tumors. What is the conclusion from the authors? Overall, these results suggest that the recognition of UIP pattern by this approach may be useful as a surrogate histopathology in combination with high-resolution CT scan, clinical factor, and so on, mainly in the diagnosis of IPF. So we have this scenario. Bronchoscopies need to be done. We need a bronchoscopy, we need material. At least three samples for ENVISA analysis. It means that you have 5 samples, you increase even more the rate of pneumothorax. First scenario, it is not UIP according to ENVISA. What it is, discordant UIP, that means UIP at the end. Probably UIP, that again could mean UIP, another entity, but we should have enough tissue for microscopic analysis, but we don't have it. Second scenario, it is UIP. What is the prevalence of UIP in the cohort? Is high, or what is the prevalence of the probability, per test probability of having UIP for the single patient? UIP with ancillary finding are not considered, or UIP favoring a IPF. So this scenario could be accepted or may be accepted by the patient if the treatment is similar in different fibrosing ILDs. So we have more. We have cryobiopsies. These are the samples. There may be even 1 centimeter of largest axis. We have standardization of the method. There is a very nice paper published quite recently in respiratory medicine. And we have diagnostic yield with a long list of differential diagnoses. UIP, UIP with ancillary finding, UIP in combination with future indicating HP, organizing pneumonia, cicatricial organizing pneumonia, and so on, NSIP, and so on. Smoking-related ILD. We have bioptic strategies. We know that if we capture tissue from different parts of the lung, we increase the diagnostic yield of the method, as showed by Claudia Ravagli in this paper. And we have this kind of samples. We can have a microscopic analysis, an SIP, cellular findings, fibrosing HP with cicatricial organizing pneumonia, inflammation in the citrolobular area, some granulomas, fibroelastotic tissue that is typical of PPFE, but can be observed also in a UIP. And UIP with high confidence, patchy fibrosis, fibroblastic foci, and onicumbing changes, and other more sophisticated diagnosis and analysis. This is a case of Erdheim-Chester disease, and the diagnosis before the biopsy was fibrosing ILD. We didn't have any clue, or we didn't discover any clue indicating the diagnosis, and the diagnosis was unexpected. For me, histiocytes in the subpleural area and in the centrilobular area expressing C100 and mutated for BRAF W600E. And we have a good pathological agreement. We don't have yes or not, but we have agreement between pathologists very similar to that observed with surgical lung biopsy. Even if you consider tabular criteria, according to this paper by Australian group, on surgical lung biopsy, you have a diagnosis of definite UIP in 50% of the cases, and this is the opposite way with cryobiopsy. But in that paper, they didn't consider that tabular criteria are not the same thing as is confidence in the diagnosis, because confidence in the diagnosis is based on the so-called touched knowledge, and probably UIP and definite UIP in this in specific clinical context are no longer entity to live separate. Diagnostic confidence, we know that when we can increase the diagnostic confidence if we introduce this information in the multidisciplinary discussion. 2 papers confirming that by Sara Tomasetti and others. We had a very, very nice long meeting in Forlì, Athol, you remember well, and we have again another meeting in Forlì with the second paper confirming the high confidence is a multidisciplinary study. Prognostic impact, another study by our group showing that information provided by cryobiopsy can separate patients in IPF and non-IPF from the clinical behavior and prognostic point of view, and patients with UIP and non-UIP. Another point to consider, changes in strategy treatment in the context of a multidisciplinary discussion. Again, another study made by our group. You see here all the co-workers are involved. Athol Wells was a great supporter of our research, Tom Colby, Jerry Yu, and so on. What we made, making a long story very short, we showed that cryobiopsy changed completely the diagnosis in almost 1/5 of the cases, and if it didn't change the diagnosis, it changed completely the confidence, so allowing specific treatment approach. And you see here in the red line, when the diagnosis of non-IPF became a diagnosis of IPF thanks to cryobiopsy, the clinical behavior was completely different. Diagnostic accuracy, we have only 1 paper confirming or dealing correctly with this approach, and they saw that there is a good agreement between surgical lung biopsy and cryobiopsy, even for histopathological pattern or clinical diagnosis. But the main message from this study is that the diagnosis made by with high confidence in the cryobiopsy sample, so you don't need surgical lung biopsy. Safety issue, just coming at the end, we know that the main complication, if we can consider a complication, is pneumothorax, can increase if you have biopsy in different segments of you use a 2.4 cryoprobe, or you have a higher coarseness score in the resolution CT scan or a UIP diagnosis. But the more severe or life-threatening complication, if major bleeding, this can happen because this is a biopsy sample, a big vessel, and a significant sample of lung parenchyma. And if you don't use this approach, you can have, or the patient can have problem. Complications and hospital admission, we have data in favor of cryobiopsy, of course, and in real life, we have 200 cases per year with cryobiopsy, and this volume of activity cannot be done in any surgical department. And what is happening in Europe is the same approach. But I am happy to confirm that all these studies were very helpful in order to introduce cryobiopsy in different guidelines. This is the hypersensitivity guidelines. The more recent guidelines, if you use a microscope, I'm quoting Athol Wells, the name is in the panel, and I'm mainly involved in cryobiopsy, just to make this statement clear. But this is the most important part for me. It was a very great experience. We had the guidelines in RJ, ERS guidelines, European Respiratory Society guidelines on transbronchial lung cryobiopsy in the diagnosis of interstitial lung disease. The paper is online. What we can say very, very shortly, cryobiopsy has to be considered before surgical lung biopsy. Cryobiopsy can be considered even in cases in which surgical lung biopsy cannot be done because of comorbidity and age and so on. And the third point, if you have a cryobiopsy negative, you should consider first, at least at the moment, surgical lung biopsy. And this is the flow chart you can find in the paper. We will have new data. Yes, this is a patient with interstitial lung disease. We want to have the periphery. Are we sure that we are in the periphery? Yes, we can be sure if you use this kind of approach. This is a fluoroscopy, but this is a combined CT scan. So you know exactly where you are. We are just in the pleura. This is the first approach. We have an ongoing study now. And this is the second one, body vision approach. Is so-called augmented fluoroscopy, because you don't use CT scan, you use fluoroscopy. And you see here if it works. This is a movie here. Oh, sorry, it doesn't work. But anyway, it works, yes. With combined CT, you don't see the moving. With augmented fluoroscopy, you see when you move the cryoprobe, and you are very sure to be there. And we can have rapid on-site analysis of the tissue without destroying the tissue with this kind of microscopes. This is a study with the Amsterdam group using laser microscope. And this is a new microscope. We are trying to have a study on that. Is a Vivascope, is a confocal microscope. And you can have this kind of analysis without destroying the tissue. You see here, you see pleura in the upper right corner, and we see that there is lung parenchyma, probably non-UIP, but we can have a rapid on-site analysis. So genomic classifier is another, probably, and Bruno will sustain this much better than me, another brick in the wall, but we have urgent need in research. Exploit lung samples with immunohistochemistry molecular test, identify genomic markers in blood, and liquid biopsy could be the next alternative or the next research horizon. Thank you very much for your attention. I will wait you all in Ravenna in the 22nd and 23rd of September for the 9th edition of this seminar. Thank you very much for your attention.
Thank you very much, Prof. Any question from the audience? After? Okay.
Yes. So now it's my pleasure to introduce Professor Bruno Crestani. So for those of you who arrived now, this afternoon, Professor Crestani is the head of the respiratory department at Bichat Hospital in Paris, in France. So it was my honor to be with him in his team for more than 1 year. So now I'm more than happy that he's here with us, even though online. So Professor Crestani, we're excited. We can't wait to hear you talk about genomic classifiers.
Okay. I don't thank you. Really, I do not thank you, Katerina, for suggesting my name for a ProCon with Venerino about such a topic, because cryobiopsy, obviously, Venerino Poletti is the best one. Look at this, my idol, Kaiser, Venerino. Obviously, you won. Obviously, you won, and I think there is no much doubt. But I would say you killed me with maths about cryobiopsy, and not only for cryobiopsy, I would say, and but for the genomic classifier. I think you did a mistake. If I can come back one slide, I took the liberty to change the title, because the title was Cryo versus Genomic Classifier, and I added this sentence: for the identification of UIP. Because obviously genomic classifier is only doing that, just helping in the identification of usual interstitial pneumonia. As you explained, it tells yes or no for usual interstitial pneumonia, and it tells nothing more. You were kind enough to compare cryobiopsy with surgical lung biopsy, which was not the aim of this pro-con debate, Venerino. Anyway, yes, you are the boss, no doubt. So, in fact, there is no pro and no con. As you told us a few minutes ago, Venerino, the recent guidelines clearly establish that transbronchial lung cryobiopsy can be regarded as an acceptable alternative to surgical lung biopsy. So there is no doubt, I think now, and your group did so good that, yes, this new procedure is now included in the guidelines, and really it's a very nice success. And the guidelines also wrote something about the genomic classifier. We make no recommendation for or against the addition of genomic classifier testing for the purpose of diagnosing UIP in patients with ILD. So clearly, it's an open recommendation. In fact, no recommendation means that we need more research, and probably we will need more evidence to position the genomic classifier. I would say I am naive. I am a bit naive because I am working in a place where I don't do myself a cryobiopsy. When I need a cryobiopsy, I send the patient outside. We are still doing surgical lung biopsy, less than before. But I would say I'm using the cryo. I have absolutely no experience with genomic classifier. And just to answer my Greek colleague who told a few minutes ago that he doesn't know what is the genomic classifier. Currently in Europe, it is almost impossible to have a genomic classifier results. And the Veracyte company, I think they did not establish yet the genomic classifier for European patients. Anyway, I think we are all convinced that the future of ILD diagnosis will be non-invasive. We listened to Elisa Tsitoura a few hours ago, about exhaled air analysis, and we published this year our experience in collaboration with Maastricht, with gaseous chromatography. And Atolwells could say what he thinks of the future of HRCT analysis, which is clearly the next frontier for the diagnosis of ILD. And I already believe that cryo is already too much invasive to be the future of ILD. And maybe it is already the past of diagnosis of ILD. And indeed, if you consider cryobiopsy, it's a 6 millimeter piece of lung. The transbronchial biopsy, which is used for the genomic classifier, is a 2 to 3 millimeters sample of a lung, which is taken through endoscopy. It does not require a general anesthesia. It can be done with a local anesthesia in an ambulatory patient. It does not require a surgical room. It is really probably less invasive than the cryobiopsy. And indeed, cryo is invasive. It can be morbid. You saw the excellent and unique results of Forli, where 200 cryo are being performed per year. But this experience is not the experience that is observed everywhere. For instance, in Vanderbilt, they published 3 years ago their experience in 200 patients with cryobiopsy, in most of the case for the diagnosis of ILD. And as you can see, the in-hospital mortality was 0.5. The 30 days mortalities were 2%, 90 days, 2.5. Vanderbilt is not a poor place for lung disease. And just to compare with elective surgical lung biopsy, the British experience, in the most recent patient, The in-hospital mortality 1%, 30 days 1.5, 90 days 2.8, very similar in fact. So Forli is a unique place with a unique experience, but cryo outside of Forli is probably more like in Vanderbilt. So remember, invasive and morbid. It is also expensive because you need to go to the hospital, you need to go to the surgical room, you need expertise. You need the expertise of Venerino Poletti, which is very difficult to obtain. And there is also evidence, and I think Venerino did a good job telling us that there was a limited agreement between observers when looking at the samples. These samples were given to me by Professor Aurélie Caz. She's a pathologist in Bichat Hospital. She's the pathologist who receives the cryobiopsy which are being performed in another hospital in Paris. So she gave me a typical positive sample with usual interstitial pneumonia with a very contributive cryobiopsy. Okay, it's fine. With this kind of samples, she can make a confident diagnosis of usual interstitial pneumonia. But she told me, look at this, Bruno, I received this last week. Artifact, hemorrhagic fluiding, in this sample, almost no alveoli that could be assessed. She told me this was a non-diagnostic cryobiopsy. And this happened, and we saw the numbers in the tables from Venerino. And moreover, the inter-observer agreement between pathologists can be not that good. I took the worst numbers from the recent paper from Cooper, looking at one major criteria for the diagnosis of usual interstitial pneumonia from a pathologist's point of view according to the guidelines. One of the 4 criteria is recognizing marked fibrosis, architectural distortion in a predominantly subpleural or paraseptal distribution. Clearly, the kappa value between pathologists was very poor, 0.1. This is one of the 4 criteria for the diagnostic of UIP on a surgical lung biopsy, and clearly does not apply to the diagnostic of usual interstitial pneumonia with cryobiopsy. And indeed, for the 3 others criteria, patchy fibrosis, fibroblast foci, and the absence of features against a UIP diagnostic, the confidence, the kappa value were good and even very good. So the people who are doing cryo suggest to change the criteria for UIP just to adapt them to the cryo. And it could be considered unfair to change the criteria according to the method. But anyway, I agree that here the inter-observer agreement can be very good. One issue, and Venerino showed this, is the limited confidence in the result of cryobiopsy. You showed this picture, Venerino. The diagnostic confidence of pathologists for assessment of biopsies in patients with interstitial lung disease, comparing transbronchial cryobiopsy or surgical lung biopsy, we see that the high confidence comes with surgical lung biopsy, doesn't come for transbronchial. I agree that there are intermediate confidence, which is very good, but the proportion of low confidence is quite high, about 40%. And this puts the pathologist in a poor situation, probably outside of very big centers. And I agree again that if you see 200 cryo in a place, probably your expertise is increasing, your confidence also. But outside from these big centers, probably this is what is real life for cryo. And this is similar results in a smaller study performed in Europe, in Belgium. Benoît Bondu, who published his experience, so showing that, again, the agreement between pathologists for the most likely diagnosis was much better for surgical lung biopsy as compared to transbronchial lung biopsy, cryo, obviously. And again, the diagnostic confidence was very low or low in 1/3 of the cases with transbronchial cryobiopsy. Again, this is the real life of cryobiopsy outside of very big centers. So the other problem is discordance, in fact, with surgical lung biopsy. I agree this is a small series. It's, again, Benoît Bondu experience. Look, and I focus just on this point. 6 patients with transbronchial lung biopsy where the pathologist make a diagnosis of NSIP. These 6 patients went for surgical lung biopsy. From the 6 NSIP samples, 1 NSIP, 5 typical UIP. So this means that when I go for cryobiopsy and I make a diagnosis, a pathological diagnosis of NSIP, it means I have to go for surgical lung biopsy. It is like having a non-diagnostic procedure. This is, again, real life of cryobiopsy. And I know you don't like this paper, Venerino. It has been really discussed. The poor concordance between transbronchial biopsy, cryobiopsy, and surgical lung biopsy in the diagnosis of diffuse interstitial lung disease. It's a French study, even if the first author is Italian. The pathologist is a world expert. He's one of the pathologists who validated the other studies that you perform. So this guy is an expert. And what I would focus just on one thing. This same pathologist from the same patient had the opportunity to see the result of transbronchial cryobiopsy and then surgical lung biopsy. On cryo, he identified 9 UIP. After surgical lung biopsy, from the 9 UIP, 5 were confirmed, 2 were HP, 2 were NSIP, and on the surgical lung biopsy. So again, even when you make a diagnostic, a pathological diagnostic of UIP on the cryo, it can be UIP or it can be anything else. So there is here again an issue, even with expert pathologists. So my belief is that we need to go beyond cryobiopsy, at least to identify usual interstitial pneumonia, which is the only thing with which to deal with the genomic classifier. So where comes the genomic classifier from? It comes from these studies, which are almost 15 years old now. Selman and others, Kaminsky, showed that if you look at the transcriptome signature from a surgical lung biopsy from patient from idiopathic pulmonary fibrosis, NSIP, or hypersensitivity pneumonitis, you can see that there is a signature, a molecular signature, which can make the difference between IPF, could be called idiopathic UIP, versus HP or NSIP. And the company Veracyte worked on this and developed a 190 gene machine learning classifier. And they first showed that indeed, when they worked on surgical lung biopsy samples, they were able to differentiate UIP versus non-UIP with this mRNA signature with a very good sensitivity and an excellent specificity. This was with surgical lung biopsy. And from this evidence, a kind of proof of concept, they went to transbronchial biopsy. Transbronchial biopsy, again, non-cryo. the usual transbronchial biopsy that we performed under local anesthesia in a patient sitting in the room as an ambulatory patient. And they excluded in this study the patient who had a typical UIP on HRCT and the probable UIP on HRCT, because this patient, we don't need currently, according to the most recent guidelines, we don't need to go for a proof, histological proof. And what they showed that with transbronchial biopsy, the tool was able to differentiate UIP versus non-UIP with a quite good sensitivity, quite good specificity, and you see the positive predictive value and negative predictive value that were observed in this study with the typical prevalence of UIP. So if I come back one slide, it's clear that with surgical lung biopsy, the sensitivity and specificity are better than when we go for transbronchial biopsy, but it is obvious. This is a 2 millimeter sample. And we need 3 of these samples because they are small. And obviously, the sensitivity and specificity are a bit lower. And then this was validated in this Luca Richeldi study that was published last year. Again, I agree. We need 3 samples at least taken during a transbronchial biopsy in a patient with during an endoscopy procedure. And then it goes through a specialized system with extraction of mRNA, and we get a yes or no answer for UIP. And in this population where 60% of the patient had a final diagnostic of UIP, they gave some interesting data as a diagnostic tool. Interestingly, however, and you could have told that, Venerino, they proved the UIP pattern in these patients or the alternative pattern with cryo in 35%. So I'm not telling you that cryo is not good, but here it can be used in the clinical pattern. So you already showed this data. In this study, the sensitivity was lower than in the first studies, but the specificity was very good, allowing for a positive predictive value, which was quite excellent in a population where the UIP prevalence was 60%. And they give us this kind of curves where indeed the prevalence in this year was 0.6, sorry. So we have the positive and negative predictive value. Obviously, if you decrease the prevalence, the positive predictive value will decrease, and the negative predictive value will also, at the contrary, will improve. So these values depend on the prevalence. But I think these data are quite interesting if I want to go for clinical practice. There is another paper that was published a few weeks ago, which used a different way of trying to validate the usefulness of the signature for the diagnostic of UIP. It is a kind of decision impact survey where they selected 11 cases from the BRAVE cohort. All the cases had an HRCT which was not UIP, who had a positive signature for UIP, and a final multidisciplinary discussion diagnosis of IPF. And these cases were submitted to physicians who, with a pre and post evaluation, the physician gave a look at these cases and they answered about their preferred diagnosis, preferred treatment, the invasive or not procedures before and after receiving the results of the NVIDIA positive result. And this is very interesting. Without the genomic classifier, you see here the percentage of preferred diagnosis, IPF here, or unclassifiable here. And after receiving the results of UIP positive, you see the rate of IPF, which is increasing, a decrease in the unclassifiable case, which is quite interesting. And this is why this tool would be useful. If we focus on the indeterminate case, or where the clinician considered that the diagnosis most consistent was non-IPF, when they received the result of a genomic classifier, they completely changed their diagnosis. What about the degrees of confidence in the ILD diagnosis? Clearly, when you give to a pulmonologist a result telling him the test is positive for UIP, the rate of confidence higher than 90% increase very significantly, while here the kind of uncertain diagnosis is reduced. This is not surprising, obviously. And again, what about invasive procedures before or after receiving genomic results? As you can see, the referral for surgical lung biopsy is quite big, almost 40%. Physician deciding to initiate treatment was obviously increasing. So if after this data, which I agree are not as good as the evidence we have for cryo, I can say, I think we can agree that the genomic classifier obtained on a transbronchial biopsy is less invasive. Maybe less morbid also, because you don't need to go to the surgical room. However, it can be expensive. And currently it is not available in Europe, for instance, but available in the US. There is no expertise needed. You just have, as a pulmonologist, to take the sample, 3 samples, and send them to their site. There is no need for agreement between observers, between pathologists, for instance. You get a yes or no result. But I agree that, and I don't like it, I don't like the black box, which from my point of view would limit my confidence of the results. I don't know what is in the box that tells me yes or no. But it could be useful, as suggested by the Lasky study. And there was an editorial going with a paper of Luca Richeldi. And one of the sentences about the genomic classifier was that it may be more generalizable in the pulmonary community because it is not reliant on access to a thoracic surgeon, an experienced pulmonary pathologist. This is for surgical lung biopsy. And we could say also an experienced pulmonologist with expertise in cryobiopsy. So with this, where could it go? If we take here the guidelines for diagnosis of IPF, could be here. When a patient has a CT scan which is indeterminate for UIP or alternate diagnosis, consider going for endoscopy, performing transbronchial biopsy with genomic classifier. If it is UIP, then it's IPF, it's done. If it is non-UIP, then consider either going for cryo or surgical lung biopsy, but according to the guidelines, I think we could go first to cryo. And interestingly, and you know that, there are data suggesting that you could improve the diagnostic yield of a cryobiopsy by adding the genomic classifier to cryo for the identification of UIP. So I think that with this, Venerino, we will be happy together. So Venerino, my idol, I think you lost. Ciao. I'm ready to answer on that now.
Thank you, Professor Crestani, for an excellent talk. I think we'll may proceed now with a lot of comments. I think there will be, or questions.
I hope Venerino understood that I was provocative.
Bruno, I was shocked because when I saw the king, the black king down, I said, it's me. Oh, thank you very much, Bruno. When I said the Italians, because Bruno is Italian. So he speaks very well Italian, and his parents. Yeah, so we are Italians again. Now, Bruno, you made, as always, a very good talk and very, very precise talk. Yes, I think both of us has good point and bad points to consider. And probably veracity is the first step for the future. We will have more and more genomic classifiers for different disorders probably in the near future, and that could be helpful to analyze smaller pieces of lung tissue. So I think probably in the future cryobiopsy will not be used. You have to say that cryobiopsy can be used also with simple bronchoscopy, because now we have smaller cryoprobes and we can collect more material, and this is another important point to consider. We can have larger samples with no crash artifact with a simple bronchoscopic approach. So another step with less invasivity and less morbidity for the patient and material for molecular analysis. Okay. I am so sad not to having you here, because we could have more fun, but in the near future probably.
Yes, it will be my pleasure, Nerino. Again, I am really sorry not to be in Heraklion, but you know what? There are two young pulmonologists in Bichat who want to go to Forli and learn cryo with you. But Venrino, I think this is an important point. I was kidding, but I do believe that the cryo in Forli with 200 cases per year will never be similar to cryo in a center where they perform one cryo every 2 weeks, for instance. And this is similar to other procedures where we need expertise. And this is something very important. And rather than having cryo in every hospital, I think it is better to send the patient to a center with expertise, with performing cryo many times per week. And I think the pathologist will be better, the anesthesiologist will be better, and of course the pulmonologist who is performing the cryo will be more experienced, and at the end this will be safer for the patient. I really am convinced about that. So I really believe that cryo in Forli is excellent, but be careful when we consider the general place where cryo is being performed.
Sergio, yes, thank you very much. I think the training is important, of course. Also for thoracic surgeons to make open lung biopsy or VETs, you need. Sometimes I see cases in consultation with open lung biopsy samples that are completely not useful for the diagnosis.
I agree.
Professor Harari. Bruno, can you hear me?
It's Sergio.
Yes.
Sergio.
Yes. I agree with most of the things you said, and I think you are right saying that we have to develop less invasive technique to stratify patient, and probably the future will be completely different. Said that, we perform cryobiopsy since several years, is expensive in operating group in general anesthesia, with all the problems you said. We do not do the volume of cryobiopsy Venerino does. We do around 30 to 40 cryobiopsy per year, and we published also our data. And are very different from the one of the American ones. We have 10% of pneumothorax, 50% of this pneumothorax needs to be drained, 50% resolved only with patient. And we did not have, we had only one, the first patient I made, and it was a learning mistake, a major bleeding. So I'm not sure, for example, mortality seems to me really unbelievable. And I think in well-managed organization, a safe, with all safety of procedure is quite a safe procedure. Invasive, but quite safe.
I agree with you, Sergio. It was a pro-con debate, so probably I took one of the
of course.
And I paid Bruno saying, please quote only for Liso.
Yes, yes, but I remember talking to other people telling, yes, our experience with our first 50 cases of cryo were a bit difficult, etc. But really, I think it's an important procedure and a step forward. And I agree that the positioning of the classifier at this time is not so easy. And in my experience, performing transbronchial biopsies, the usual ones, not with cryo, can be also challenging to the patient with a pulmonary fibrosis.
Yeah.
And we all know that we can have bleeding, pneumothorax,
acute exacerbation.
Acute exacerbation, some patients going then to the intensive care. So maybe less invasive, agree, but not without precaution. Yeah.
If I can add a comment, I've done really hundreds of transbronchial biopsy in lung transplant recipients, hundreds. And probably I feel more comfortable to do cryobiopsy in a general anesthesia and operating room than to perform transbronchial biopsy in a normal bronchoscopic setting.
Yeah, this is a good comment, Sergio, because I remember when we were young, a long time ago, we had transbronchial biopsy in a dentist chair, and without fluoroscopy. And my master, he performed this kind of bronchoscopy. I remember a case, an 80-year-old child that he performed transbronchial lung biopsy in that way. So the experience they had and we had in the past is not the experience we have now with transbronchial biopsy. And another point, I think that if I would need a biopsy, I would like to have general anesthesia, Bruno. I'm a coward, so I think that general anesthesia should be dedicated to all the patients. But this is another comment, yeah. But the cryobiopsy, small probes are very promising for obtaining good material, yeah.
Okay, I think
we have time, yeah.
We'll have more time. Okay.
Just two questions.
A very, very short question, very short answer, yeah.
Question one. Recently, when I perform TBLC, I usually use radial IBUs together with fluoroscopy, as well as a rapid touch imprint cryocytology. I would like to hear it from you. And the second question is, to my opinion, you don't use classifier testing, genomic classifier testing in organic hospital. Do you?
No. It's not in Europe yet. This is the second question. The first question, yes, we use radial labels if we have alveolar consolidation, because it's easy to recognize the area in which you have the biopsy. For the rapid on-site analysis, yes, you were in our center, you can touch the cryoprobe in the slide, but it's not so. It's useful for tumors, not for interstitial lung diseases. For interstitial lung diseases, this kind of new microscopes could be very useful, but again, they are very expensive. Okay.
Enrico, may I ask you something?
Yeah.
Are you using, or do you have any experience with endobronchial optical coherence tomography? You know, this method which is being developed in the US.
No.
And,
Bruno, I know the topic because we had a discussion. I'm not experienced with OCT. There is a paper saying that they are able to recognize honeycombing. I have some experience with CLE, and now we have an ongoing prospective study using confocal laser random microscopy in order to identify the area. But honestly speaking, OCT could be useful if you don't want to have the tissue. Otherwise, it's better to have convex CT or body vision because you know exactly the segment you want to explore. Yeah. But it's my
it is just imaging, in fact.
Yeah.
Okay, I think we have to close the session now. Thank you. It was a hard debate. I think when Professor Poletti had more studies and more data to support his. No, I didn't want to say that. Excuse me. No, I have to support Professor Crestani just to say that maybe genomic classifier is the future. There's not much data yet, so I want to. There is a balance here, but thank you both for this. Thank you.
Ciao. So coffee break and at 6 o'clock for the hot topic session.
countries, bringing together healthcare professionals and other experts working in respiratory medicine, united under a collective mission to promote lung health and alleviate suffering from respiratory disease, advocating to reduce the burden of respiratory disease in Europe and producing science and unbiased education to share with healthcare professionals worldwide. We seek to tackle the current challenges in respiratory medicine across 8 respiratory disease groups. At the heart of everything we do are our members and our patients. Promoting funding and helping to drive a variety of activities to advance respiratory medicine. Funding vital research projects, recognizing excellence, sharing and exploring new findings, and publishing one of the world's leading scientific journals in the field of respiratory disease. We create unbiased medical education and continuing professional development under the leadership of world-renowned experts in their field, harmonizing the standards and practice of respiratory medicines across Europe, helping thousands of healthcare professionals to improve their medical knowledge and skills, offering access to the highest quality online materials, and publishing learned educational journals and handbooks. We share knowledge, promote collaborations, and best practice through ERS events and conferences. Increasingly investing in the latest technology to make cutting-edge education accessible and affordable to healthcare professionals worldwide. Across the two pillars of science and education, we are dedicated to encouraging researchers and healthcare professionals to improve their skills, increase their knowledge, advance their careers, and ultimately improve patient care. Our leaders and dedicated officers advocate for change in Europe on behalf of the society by raising awareness of lung health issues with politicians and the public. ERS and European Lung Foundation work closely with the EU and related institutions to ensure policies are based on science and patient needs. Through ELF, we work with patients, understanding their needs and hopes, involving them in research and guidelines, and supporting their active role in decisions concerning diagnosis and treatment of lung disease. ERS and ELF come together to provide support and information for patients, raise awareness about key issues affecting lung health, and campaign for healthy lifestyles and the prevention of disease. Each year, we host the largest gathering of respiratory professionals in the world at the ERS International Congress, a showcase of excellence for respiratory medicine. It's one of the world's major platforms for the release of new data. Additionally, giving access to live sessions and recordings to tens of thousands of virtual delegates, sharing new thinking and inspiring the respiratory community. The ERS International Congress is an essential ingredient for the advancement of respiratory medicine. The European Respiratory Society, supporting its members in advancing respiratory medicine and improving patient care, offering access to the highest quality unbiased medical education to all healthcare professionals around the world, raising awareness of unmet research and educational needs, and promoting lung health to meet the needs and hopes of our members and our patients worldwide. The European Respiratory Society. Every breath counts. The European Respiratory Society is the largest scientific and clinical organization in respiratory medicine in Europe, with a growing membership from over 160 countries. Bringing together healthcare professionals and other experts working in respiratory medicine, united under a collective mission to promote lung health and alleviate suffering from respiratory disease. Advocating to reduce the burden of respiratory disease in Europe and producing science and unbiased education to share with healthcare professionals worldwide. We seek to tackle the current challenges in respiratory medicine across 8 respiratory disease groups. At the heart of everything we do are our members and our patients. Promoting funding and helping to drive scientific research through a variety of activities to advance respiratory medicine. Funding vital research projects, recognizing excellence, sharing and exploring new findings, and publishing one of the world's leading scientific journals in the field of respiratory disease. We create unbiased medical education and continuing professional development under the leadership of world-renowned experts in their field, harmonizing the standards and practice of respiratory medicines across Europe, helping thousands of healthcare professionals to improve their medical knowledge and skills, offering access to the highest quality online materials, and publishing learned educational journals and handbooks. We share knowledge, promote collaborations and best practice through ERS events and conferences. Increasingly investing in the latest technology to make cutting-edge education accessible and affordable to healthcare professionals worldwide. Across the two pillars of science and education, we are dedicated to encouraging researchers and healthcare professionals to improve their skills, increase their knowledge, advance their careers, and ultimately improve patient care. Our leaders and dedicated officers advocate for change in Europe on behalf of the society by raising awareness of lung health issues with politicians and the public. ERS and European Lung Foundation work closely with the EU and related institutions to ensure policies are based on science and patient needs. Through ELF, we work with patients, understanding their needs and hopes, involving them in research and guidelines, and supporting their active role in decisions concerning diagnosis and treatment of lung disease. ERS and ELF come together to provide support and information for patients, raise awareness about key issues affecting lung health, and campaign for healthy lifestyles and the prevention of disease. Each year, we host the largest gathering of respiratory professionals in the world at the ERS International Congress, a showcase of excellence for respiratory medicine. It's one of the world's major platforms for the release of new data. Additionally, giving access to live sessions and recordings to tens of thousands of virtual delegates, sharing new thinking and inspiring the respiratory community. The ERS International Congress is an essential ingredient for the advancement of respiratory medicine. The European Respiratory Society, supporting its members in advancing respiratory medicine and improving patient care, offering access to the highest quality unbiased medical education to all healthcare professionals around the world, raising awareness of unmet research and educational needs, and promoting lung health to meet the needs and hopes of our members and our patients worldwide. The European Respiratory Society. Every breath counts.
This year marks my first year as ELF chair. Unfortunately, it's been a year marked by COVID-19, relatively physical distancing, remote consultations and meetings. I know it's taking a toll on many respiratory patients, but we hope it will be different in the coming year. But it's also been a year that has revealed our community's resourcefulness, our adaptability, our innovation, our fresh ideas and approaches to deal with uncertainty. This is also true for the European Lung Foundation. In the past year, we have managed to get a new ELF chair in position. We have adapted a new strategy with 6 strategic goals: to be patient-led, to increase knowledge and understanding, to engage effectively, to have a strong voice, to ensure good governance, and to increase our resource and outreach. We have also modified the ELF Council so it's now a 50-50 split between EIS leadership and patients. This spring, we launched our new website, which ensures better synergies and link with EIS web resources. Amongst other things, it has better usability and is more people-focused. We have also strengthened the visual content on the website to ensure a more diverse communication of contents. The website also contains patient input process details and a new section on fundraising. In general, the new website has helped us to strengthen our patient input. We have developed and focused our disease-specific patient advisory groups to better match the interest of patients and to strengthen the links and synergies to the EIS assemblies. This year, we have added 4 new patient advisory groups and giving us 13 in total. We have provided patient input to more than 35 EIS projects in the course of the last year, including 20 task forces and 15 TRCs. One of the new innovations that we introduced in the course of the last year is a format that we call the Patient Conference. The idea with the patient conference is to have our disease-specific patient advisory groups lead on defining the content and co-host the patient conference with EIS professionals. In February, we had our first patient conference on bronchiectasis, and in July, we had our second on long COVID. For both events, we had just under 2,000 registrations, with half attending on the day and many more watching the videos afterwards. This is a format that we plan on developing further in the coming year. Another innovation for ELF is the development of a fundraising strategy. We have developed documents and processes for driving our fundraising forward. Our first venture into fundraising was the Virtual Conference Challenge, which took place in conjunction with the 2020 EIS Congress and helped us to raise more than £4,000 for our Healthy Lungs for Life campaign. This year, we have launched the Take the Active Option fundraising campaign. I hope you join it. You'll find more details on our supporter section on our website, which is created to help income generation to improve lung health globally. This past year has been extraordinary in terms of developing and strengthening patient input through digital tools and platforms. We hope to develop this further in the coming year, but we also hope we get to see each other, to meet, to think, to discuss, and to develop together, because this is the essence of what ELF stands for.
But it follows a simple human aspiration: to care for others, to make people feel better. This is our true calling. We should never forget it. So it feels natural for Chiesi Group to be a B Corp, choosing to serve a purpose beyond profit, a path we've followed generation after generation, and that today is officially recognized. We are the largest pharmaceutical group to be awarded B Corp certification. We join a community of companies that meet the highest social and environmental standards, with sustainable choices, a reduced impact on the planet resources, and a deep respect for people. A group of leaders who use business as a force for good. Being a B Corp for us is more than a certification. It's a commitment. It's our promise to every person, especially the most fragile ones, to communities, suppliers, institutions, and to the future generations, that we will make the world feel better.
So, good afternoon again. We are slowly turning to the end of this
in respiratory medicine in Europe, with a growing membership from over 160 countries, bringing together healthcare professionals and other experts working in respiratory medicine, united under a collective mission to promote lung health and alleviate suffering from respiratory disease, advocating to reduce the burden of respiratory disease in Europe, and producing science and unbiased education to share with healthcare professionals worldwide. We seek to tackle the current challenges in respiratory medicine across 8 respiratory disease groups. At the heart of everything we do are our members and our patients. Promoting funding and helping to drive scientific research through a variety of activities to advance respiratory medicine. Funding vital research projects, recognizing excellence, sharing and exploring new findings, and publishing one of the world's leading scientific journals in the field of respiratory disease. We create unbiased medical education and continuing professional development under the leadership of world-renowned experts in their field, harmonizing the standards and practice of respiratory medicines across Europe, helping thousands of healthcare professionals to improve their medical knowledge and skills, offering access to the highest quality online materials, and publishing learned educational journals and handbooks. We share knowledge, promote collaborations and best practice through ERS events and conferences. increasingly investing in the latest technology to make cutting-edge education accessible and affordable to healthcare professionals worldwide. Across the two pillars of science and education, we are dedicated to encouraging researchers and healthcare professionals to improve their skills, increase their knowledge, advance their careers, and ultimately improve patient care. Our leaders and dedicated officers advocate for change in Europe on behalf of the society by raising awareness of lung health issues with politicians and the public. ERS and European Lung Foundation work closely with the EU and related institutions to ensure policies are based on science and patient needs. Through ELF, we work with patients, understanding their needs and hopes, involving them in research and guidelines, and supporting their active role in decisions concerning diagnosis and treatment of lung disease. ERS and ELF come together to provide support and information for patients, raise awareness about key issues affecting lung health, and campaign for healthy lifestyles and the prevention of disease. Each year, we host the largest gathering of respiratory professionals in the world at the ERS International Congress, a showcase of excellence for respiratory medicine. It's one of the world's major platforms for the release of new data. Additionally, giving access to live sessions and recordings to tens of thousands of virtual delegates, sharing new thinking and inspiring the respiratory community. The ERS International Congress is an essential ingredient for the advancement of respiratory medicine. The European Respiratory Society, supporting its members in advancing respiratory medicine and improving patient care, offering access to the highest quality unbiased medical education to all healthcare professionals around the world, raising awareness of unmet research and educational needs, and promoting lung health to meet the needs and hopes of our members and our patients worldwide. The European Respiratory Society. Every breath counts.
Katerina, it's okay, or we're waiting for 5 more videos? Okay, this is the last session of this very interesting workshop. And we have 2 challenging topics to present from 2 very distinguished expertise in these topics. Please, Rigi, introduce the first speaker.
Professor from the Medicine Department here in the University of Greece will talk us about the role of molecular imaging, PET-CT, and pulmonary fibrosis.
Good afternoon. First of all, I would like to thank the organizing committee, to thank Professor Tzanakis, Katerina, and Sofia for inviting me to participate in this very interesting scientific event in the second Cretan Summer School of Respiratory Department. When Katerina asked me to give this talk, I was terrified because PET is mostly for oncology, for oncological diseases. But it was something exciting, so I accepted, and I think that it will be interesting to see and to learn things that are not in our clinical daily practice, and we have a lot to do with our colleagues pulmonologists. The topic of this talk will be about molecular hybrid imaging method of nuclear medicine, PET-CT, in patients with idiopathic pulmonary fibrosis. As we know, ILDs, interstitial lung diseases, is an umbrella term more than 200 different diseases with different clinical course, treatment, and prognosis. And IPF, idiopathic pulmonary fibrosis, is the most common idiopathic interstitial pneumonia with a known etiology and the most common pattern, the usual interstitial pneumonitis. Differentiating patients, IPF patients versus other forms of ILDs is critical due to the different prognosis. We know that IPF patients have a worse prognosis, and due to the different therapeutic management because IPF patients may not respond to immunosuppressive therapy or may respond to antifibrotics. So, the diagnostic workup in IPF is a challenging and evolving area, and initial investigations are laboratory tests, pulmonary function tests, blood tests, and invasive diagnostic procedures, BALF, bronchial US, and biopsy. Imaging plays an important role in IPF patients, and the initial investigation is the conventional radiography. Conventional radiography can establish disease chronicity and progression, can rule out other diseases like heart failure, cancer, infections, but unfortunately has no specific findings. So till now, the most important imaging modality in IPF patients is the HRCT. The HRCT with a typical pattern. We heard a lot of many times today in several talks about UIP. UIP, if there is UIP, we have a conclusive diagnosis of IPF. But if in other cases, if there is a probable UIP, possible UIP, so we need more diagnostic tools and biopsy. Despite the advantages of HRCT, the high specificity and the high positive predictive value, that means that based on these parameters, we can avoid several times, a lot of times, the need for invasive diagnostic procedures. There are a lot of limitations and drawbacks, and these limitations and drawbacks are due to the nature of HRCT. Because HRCT is a purely structural, as we all know, and mostly qualitative and not quantitative imaging technique. And so it can only give indirectly information, references regarding metabolism. And we all know that molecular medicine has a molecular approach. So metabolic activity, metabolism, and molecular processes is very critical for the best diagnostic and therapeutic management of our patients. So the most important drawback and limitation of HRCT is the limited prognostic value and the limited role in disease monitoring. So, based on all this, we can understand that till now there is no single test able to give a definite diagnosis in IPF. So we are in front of a multidisciplinary approach. And in this multidisciplinary approach, PET seems to have a role. As we know, PET, positron emission tomography, is the only molecular functional imaging till now. It is an imaging modality of nuclear medicine. And it is it is a standard of care in oncology, very important in cardiology and neurology. But nowadays, there is a great interest for non-oncological diseases, including IPF. Just a few words for PET. PET is based on the use of several radiolabeled biomarkers, and this is very important because with these radio-labeled biomarkers, we can evaluate all the molecular processes in several diseases, including IPF. Which is a possible role? Has PET any role in IPF? Well, we will see this in the near future, I think. But nowadays there is a great effort in evaluate the possible role. The possible role could be in detecting and staging the active fibrotic disease. So the most important thing is not the initial diagnosis for PET, but to evaluate the activity, to assess the disease progression, to have, if PET has a prognostic role for treatment monitoring, to differentiate active fibrosis versus scar tissue. And the most important advantage of PET is the ability to offer quantitative analysis and quantitative information. So we can not only evaluate qualitatively the IPF, but also to quantify several molecular processes. Why PET could be important in IPF? As we know, IPF is characterized by both inflammation process and fibrinogenesis. And nowadays we have in our hands two very important radiolabeled biomarkers, the known to all of us FTG, and a glucose analog labeled with 18 fluoride for inflammation. But nowadays we have new radiotracers, new molecules, new biomarkers called FAB tracers, and for this we will talk later. Just to start from the possible role, because we don't know yet, the possible role of FTG PET in IPF patients. Several studies are published. The first was in 2006 in a Respiration Journal. It was a study with a small pool of patients, only 7 patients, and as we can see, this was not used the PET-CT that we have now, because just to remind you that PET is a functional image modality, but it can't give anatomical information. So for this reason, nowadays we have the hybrid imaging tools, PET-CT. We have the PET compartment for the functional information and the CT compartment for the anatomical information. So in this study, it was very early, it was in 2006. They used only PET, and we can see the problem. I don't know if, or with, okay, is it? No. Yes? Yes. This is an example with only PET, not PET-CT. So we can see that there is only the high uptake of FTG, but we can't see the anatomical regions. So in this patient, there is a high uptake of FTG in the lung parenchyma, higher than the liver. So this patient showed that perhaps it has an active disease. What will be the role of PET in activity? As we know, FTG is a marker of the metabolic activity, of the glucose metabolism. It is captured, it is transported into the cells via glucose transporters, and then it is trapped in the cell. It is with the help of exokinase, it is phosphorylated, it is trapped, and we depict with the amount of FTG with a PET scanner. They showed that, first of all, in a high percentage of these patients, of about 86% of these patients, had a positive FTG PET. And what is the meaning of this? That in this area, in these patients, there is some activity. So we can follow some therapy for these patients, because if we have something inactive, then perhaps it was useless to give some therapy. So another finding in this study was that with the high uptake of the radiotracer in several areas, then it is helpful to identify areas of increased uptake for biopsy purposes, just to guide the biopsy. And moreover, they showed that based on FTG PET, we can classify patients who could not be expected to benefit. And why this? Because if there is no uptake, that means inactive disease. So we can avoid trials of expensive therapy, so to save the public health system and to avoid adverse effects. Here we can see an example, as we said before, the high uptake of the radiotracer of the lung parenchyma. And so this patient was candidate for a therapy, underwent prednisone, and several months later they showed that it was a lower uptake of the FTG. That means that it was a kind of response. But unfortunately, after tapering off prednisone, there was again a high uptake, so it was a relapse. Other possible roles of PET. They tried to show if FTG PET was able to distinguish patients with IPF versus patients with other forms of diffuse parenchymal lung diseases. So in this direction, a publication was done in 2009. And they, as we can see here is a PET-CT They used also the quantification by using a quantitative parameter, the SUV. I think that you all know what is SUV. SUV is it shows the amount of the FDG trapped in a dedicated area. So the results were a bit disappointing in this for this purpose. Despite the fact that SUV was high in IPF patients, it was not statistically significant different with versus other forms of DPLD. So FDG PET was not able to give this information, but it was very good in separating patients, IPF patients versus normal subject with a very high SUV in IPF patients. The most important finding in this study was that, as we know, HRCT is an anatomical imaging method. And the most important pattern is the honeycombing. That means, what does it mean, honeycombing? Mostly fibrotic areas, mostly inactive areas. But they showed that in these areas with these fibrotic areas, they found the highest uptake of FDG. And that means that in these areas, there are regions with activity. So this is a very important information for treatment monitoring and for the therapy assessment. Other roles, possible roles on disease monitoring, but the most important seems to be the role of FDG PET in order to predict progression-free survival, if PET has a prognostic role. A very important study was published in this direction in 2017, and they used not the usual SUVs that we all know, but more specific quantitative parameters like MLV and TLG. MLV is the metabolic lung volume, and TLG is the total lesion glycolysis. That means the areas with high glucose metabolism. And they found that there was a negative correlation between these two parameters and FVC and DLCO. So patients with high FDG uptake, that means patients with high MLV and TLG, and low FVC or DLCO are patients with more severe disease. Moreover, they found out a positive correlation between GAP score and these two parameters, so they showed that these two parameters could be independent factors of progression-free survival and could predict the risk of death and the progression of the disease. And here we can see the importance of these two quantitative, more specific parameters, TLG and MLV. We can see that SUV was not the ideal quantitative parameter because it can't clarify patients with different stages. There is an overlap. But on the other hand, we can see the other two quantitative parameters, mostly the MLV, that is very important in order to for the risk stratification. They also noticed that patients with high values TLG and MLV are those patients who were non-survivor and who present a disease progression. And here is an example. Here we have a normal subject with no increased uptake of the radiotracer in the lung parenchyma. And here is a patient, an IPF patient, with not a good survivor. As we can see, there is a high uptake of the radiotracer in fibrotic areas. Another possible role, as we can see, there are very many possible roles, but we have to see it in the future. Another possible role will be the role in the prediction to refine the risk stratification. There are a lot of studies in this direction. They showed that patients with high FDG uptake are associated with poor survival. As we can see, there is the green line with a TBR, high TBR that shows poor survivor, and with low TBR that shows a better prognosis. And moreover, they noticed that in a follow-up of the 3-year mortality was very high in patients with high values TBR, high with GAP3 stage, and with low values FVC and DLCO. What else? They also thought that, as we know, gap scoring index is the only, perhaps, clinical scoring system for prognostic accuracy. But is there a role of FDG PET in this direction? If we combine PET, could probably have a better risk stratification of these patients. And they showed that there was a modification, a change in the risk stratification. As we can see, patients based only on gap index, there are low risk 31, intermediate risk 38, and high risk 21. But it was changed, this risk stratification, very much by adding PET and by adding quantitative CT. Yes, all these advantages, very nice. With PET-CT, we have the CT compartment for morphological changes. We have the FDG part for activity, for inflammatory activity. But the dominant role in IPF and the most important process in IPF is the fibrinogenesis. And the FDG PET-CT has now the role in to demonstrate active fibroblasts. So nowadays, a group of scientists from the University of Heidelberg thought that if they found a radio-labeled biomarker able to show directly the activate fibroblasts, then this modality could be very useful. As we know, the dominant role in IPF have the abnormal fibroblast proliferation, differentiation, and activation. And just to remind you that fibroblasts are found everywhere in almost all tissues, but in a quiescent stage. And they become activated when there is an injury. And so they migrate towards the sites of injury in order to orchestrate the repair. So they thought that in cases that any disease has activate fibroblasts, then we can use this tracer in order to demonstrate the activity, this activate fibroblasts. So the first tracer for PET imaging was the FAPI inhibitors, are peptidomimetic quinolone derivatives that have high affinity to be bound in FAP. And FAP is the transmembrane protease found on fibroblasts. So in every area that there are active fibroblasts, then FAPI will be have the affinity to bind, so to target these patients. As we said before, PET is mostly for oncological diseases, but nowadays there is a great interest, scientific research and clinical interest on the use of PET in non-oncological diseases, including IPF. And we can see here that FAPI, this radiolabeled biomolecule with 16,8 gallium, showed a high sensitivity and high specificity in shown active fibroblasts. A very important study that I found in the literature, because we all try to learn nowadays for these new radiotracers, was in the Lancet Rheumatology of 2021 for patients with SS-associated interstitial lung disease. We know that these patients, in a high percentage of these patients, there is association with ILD. So it is very important to separate, to distinguish patients with and without. Here is an example. For a patient of SS-ILD, we can see the high uptake of FAPI tracers in fibrotic areas, and they showed that there was a very high uptake of FAPI in SS-ILD patients compared to control group. They showed also that FAPI was able to show the progression of the disease, a very important information that we can't have this information from anatomical imaging methods. And it is very useful in order to classify patients with active versus inactive disease. Moreover, there is a great interest on the therapeutic assessment and on treatment monitoring. Here is an example. Here is a patient with a high uptake of FAPI, SSILD, and several months later, after therapy, there is a progression of the disease. And here is another example, more lucky, I can say. There is a high uptake of the FAPI in the baseline study, and a lower uptake, that means response. So in conclusion, we can say that positron emission tomography, the only till now molecular imaging, is a standard of care in oncology, very important neurology and cardiology. But nowadays there is an enormous interest for non-oncological diseases, including IPF. We have in our hands till now two very important radiolabeled biomarkers, the FTG, the glucose analog labeled with 18 fluoride, which shows the activity, the inflammation activity in IPF patients. But we have also the new FAP tracers, very promising. It seems that these tracers open a new chapter in molecular imaging in IPF in order to quantify the fibroblast activation and to be very useful in SSILD. Finally, we can see that nowadays we have a high number of molecular probes for fibrosis specific and fibrosis associated process, but unfortunately only a few of them is now available for clinical practice. We have a lot to do. There is a need for more extensive preclinical evaluation in order to translate all this information, all this data on clinical use in the next few years. So, dear colleagues, pulmonologists, we have a lot to do because now we are waiting our PET-CT, the first digital PET-CT in Greece. It will come in September of this year. So we have a lot to do for our patients. Thank you very much.
We are very happy for that. Thank you for this comprehensive presentation. Is there any question from the audience or comment?
Thank you, Professor Tzouvelekis, for the nice, very interesting talk. To be honest, I'm not very familiar with the literature, so I was impressed. A first comment about the highest UV uptake in fibrotic regions. Maybe it's not so impressive after all if we think the dense regions with myofibroblasts that we suppose they are highly activated cells. So maybe I think if Professor Poletti was here, maybe he would agree with me that there are a lot of pathways, also molecular pathways, developmental pathways that show similarities between lung cancer and IPF.
Yeah,
so maybe it's not so weird after all. Yeah. And I have two small questions. If you are aware if there are data in the literature comparing IPF, UIP pattern, I mean, with non-UIP, or IPF with NSIP patients with ground glass on HRCT, if you know what I mean. And regarding the second part of your talk with FAPI, I was also very impressed because I was not really aware of that. And I was wondering if there is any data on the literature also about IPF patients before or after treatment, if there is any improvement for the FAPI uptake.
Okay.
Thank you.
Thank you. Yes? Professor Arthur, something to say?
Going to agree with you to begin with on the profibrotic markers. I think that's fascinating, a source of future work. Grave reservations about FGG PET in IPF. Inflammation doesn't drive disease. In honeycomb areas, we very often have secretions and subclinical infection, and on we know in scoring histological specimens, and its fibrosis, it's also a lot of inflammatory cell infiltration. But don't manage to link that to disease progression in IPF. So I would question Now, GAP is great in very large cohorts. It will give you on average mild, moderate, and severe disease. If you don't have large cohorts, it lumps severity. So an FVC of 74% is the same as an FVC of 56%. So all sorts of things will refine GAP, including using continuous variables. So I think if you were going to make a case for risk stratification, and maybe you're able to cite this, you would need to show that FDG PET was independent of individual variables rather than GAP. Do you know if that's been done?
No.
So it's the fact that what you say about it's a fascinating area. Just a note of caution about FDG PET.
I think that we need a combination of both FDG and FAP.
The problem just FAP.
Just FAP. Okay, now because FAPI, FAPI, we can have high uptake of FAPI in cancer cells and in many other. So it is not so specific, and the role of FDG and FAPI is not for the initial diagnosis. Is for the activity, is for the prognosis, is for the treatment, therapy, monitoring. Is not to say, yes, this patient has IPF. Is an additional method to all this that we have in our hands now. And also,
So, and I would like to hear also Professor Vassalou on what I'm going to say. My personal experience regarding FDG diseases is in the context of progressive massive fibrosis.
Yeah.
Physicians say that, okay, let's do a PET and see if it is therapy or not. In my experience,
it is always active.
It is not necessarily progressive. So this is why I'm not sure whether FDG positivity can be used as a
the activity, you can see the activity by high RCT.
No, by PET. So you have
by PET
with PMF and it's positive, and the patient is stable for years to come.
Yeah. Okay.
Actually, I would defend FDG PET in non-UIP and sarcoidosis.
Sarcoidosis, yes,
and
it is.
There, I think you've got the inflammatory fibrotic model. So patients with sarcoids seldom get worse if they're vigorously treated.
Yeah.
They may die of their treatment, but they don't tend to die of their interstitial lung disease. And I think there's enough there that if you have apparently irreversible disease, and we'll leave PMF out and talk about the wider range of fibrosis, then there is truly a dichotomy between those patients who have and don't have FDG uptake.
Yeah.
And I think there's enough data that used well, the signal does help guide treatment in that setting. My concern is applying
inflammatory,
where inflammation isn't actually part of pathogenesis.
Yeah, I choose this topic because with sarcoidosis, something we know the value of PET, and I choose this topic because I thought it was more interesting.
This is really a very interesting topic, but should we move to the next? I mean, this is an endless discussion, I believe. Yes, that's right. We'll have plenty of time after the session, I think. Okay. Now, I believe it's time to move to the next hot topic, which is, I believe, the hottest among the two, since it refers to the climate change. So I invite Professor Harari, a well-known expert in the field of rare diseases and pulmonary hypertension, to speak about, to give us the novel insights regarding the effect of air pollution and climate change in the pathogenesis of ILDs. Professor Harari,
Thank you very much. Thank you, Katerina, Professor Tzanakis, and Sofia for the invitation. My presentation could be very short, but we have no data about climate change, so we can stop here. We have some data, unfortunately for you, about pollution. So whilst prevention of ILD and reducing exposure to potential causative agent is crucial, this is a complex field, as we all know. The clinical management of IPF is challenging. For patients with a progressive disease with unknown cure, realistic goals include slowing the rate of disease progression, optimizing comorbidities and functional status, managing symptoms, and preventing what is preventable. And perhaps pollution can interact with one or more of these goals. The difference in epidemiological parameters may be a result of heterogeneous methods used when true geographical difference in IPF epidemiology. It is unknown if the incidence and prevalence of IPF are influenced by geographic, ethnic, cultural, or other factors. Evidence about the role of air pollution in the development and in the course of the disease are still scarce. According to a paper I will show you now of Dr. Johansson, the increase of ozone and nitrous oxide exposure over the preceding 6 weeks was associated with an increased risk of acute exacerbation IPF. This study was conducted in South Korea. It was a retrospective study correlating in this large cohort of more than 400 patients followed in one ILD centers of South Korea for over 10 years, and they demonstrated that a significant relationship between ambient ozone and NO2 level and acute exacerbation of IPF. The magnitude of the associated risk is comparable to what has been reported. The authors wrote for visualization of other chronic lung disease like COPD, asthma, and so on. And air pollution is a potential modifiable risk factor for IPF exacerbation, either via behavioral adaptation of a patient or community-level reduction in exposure through environmental policy. And here you can see the hazard ratio, and in particular for ozone and NO2, there is a strong correlation. So, Cézé published some years later, Thorax is the group of Anesi Maizano, that the onset of acute exacerbation was significantly associated with an increased mean level of ozone in the 6 preceding weeks. Mortality was significantly associated with increased level of exposure to PM10, and cumulative level of exposure to particulate matter of coarse and fine particles were above the WHO recommendation in the vast majority of the population. And as you know now, WHO recently raised down the level of the threshold for pollution. So here you can see the hazard ratio about air pollution exposure and mortality with the correlation with coarse and fine particle. This is a study from Wittenborn, and is a quite limited number of patients. It's around 130 patients, and they measure the PM10 concentration associated with an increase in the rate of decline of AVC in IPF, suggesting a potential mechanistic role for air pollution disease progression. The next year, Always Johnson published a study with different conclusion, always a small study, 25 patients with IPF, followed for 40 months with home spirometry. So a quite interesting model of study with geolocalization of pollution, and they did not find any correlation with progression of the disease, but patients were exposed to highly polluted area had a lower lung function. But again, there are some limitations in these studies, and there are too small population to have a firm conclusion. This is a different study. This is a study that considered more than 5,000 patients that were studied in a preventive study in about coronary artery disease. So patient had at least 2 CTs, heart CT, and a number of patients had also a high resolution CT, and patients were followed, so more than 5,000 patients were followed over 10 years. So it's quite a very large database, and they look for ILA, and the ILA increase of 1.7 for an increase of 40 parts per billion of NOx. And NOx, you know, are very strongly related to vehicle pollution. There was an overall trend towards an association between higher exposure to NOx and greater progression, also of ground glass opacities, always with 40 parts per billion increment in NOx. So this is quite interesting because it was a very large database followed for 10 years. The primary goal was the cardiovascular risk, but the information we had on ILA and ground glass opacity was quite interesting to me. This is another study that was conducted in India with several limitations and biases by saying, and the last author is Ganesh, the role of air pollution in hypersensitive communities has not been studied. Venerino, please, yes, if someone can close the door. Thank you very much, Arthur. The ILD India registered recruited consecutive consenting patients with ILD from many centers from March 2012 to June 2015. Thank you again. And nearly half of 1,084 patients with new onset ILD were living in India had a clinical diagnosis of hypersensitive pneumonitis, and they found a correlation with PM2.5 level. And also an increase of PM2.5 was associated with an increased risk of developing hypersensitive pneumonitis. I must say that there were some epidemiological biases in the study, and also the registration of pollutants were quite, I would say, quite fair. So they correlated anyway, there's coarse and fine particles with hypersensitive pneumonitis, and could be a rationale for that. This is a recent paper that done another work. They study the cross-analyzing location of IPF cases and areas of pollution concentration in a retrospective way, and on 500 patients in a observatory IPF CAT over 3 years, and mapping PM2.5 level the areas more polluted had a higher concentration of IPF cases. So the question we tried to answer some years ago was different. So the question we tried to answer was, what's the role of chronic air pollution exposure in the development of IPF? Does it have a role? So I live in Milano, and as you can see, this is Lombardy, and it is a region surrounded by mountains. And Lombardy has 10 million inhabitants, is the most populated Italian region, and is also one of the most polluted areas in Europe because of the industrial plants, intensive agriculture, and high population density. And now there is also an open discussion about the possible interaction or active role of COVID in the first wave of disease in our region. The presence of the Alps and Apennines act as a barrier, favoring stagnation condition and accumulation of pollutant. The Po River basin, the Po is a river, one down from here, is bordered on three sides by mountains. Weather disturbances are frequently unable to cross the Alpine barrier, and poor air mass exchange cause frequent phenomenon of thermal inversion, with smog and pollution being trapped close to the ground. So just to give you an idea, these are the concentration in Europe of PM10 in 2015, and this is Lombardy. 2000 PM 2.5, again, red, NO2, NO3. So as you can see, it's really a very polluted area. So this was the paper published in 2018, and what we have done, we try to consider PM10, NO2, O3, and correlating with the incidence of IPF over 10 years. So we consider from 2005 to 2010, but we consider also to check and avoid any consideration of cases from 2000 to 2005. So we try to be sure that there was no prevalent cases. We also observe the period from 2000 to 2005. And we use three different possible definitions: generic case definition, at least one hospitalization or outpatient visit with diagnosis of IPF; broad case definition, no medical claims with diagnosis of any other interstitial disease on or after the last medical claim with a diagnosis of IPF; and a narrow was hospitalization or outpatient visit with a procedure code for surgical lung biopsy or CT scan of the thorax before the last medical claim with a diagnosis of IPF. At least 5 years of follow-up. If we consider the generic case definition, we have nearly 3,000 cases, broad definition 2,000, narrow definition 1,300 cases. And this is the table that reports how the population is distributed. Of course, more males, median age, municipality means the number of cases for area, and we also corrected our data for season, and we requested hourly NO2 and O3 concentration by our official traffic monitoring station. For each municipality, we estimated the chronic exposure to NO2 using the average daily overall and seasonal NO2 level from 2005 to 2010. All background monitors located within 10 kilometers from a municipality limits and all traffic monitors located with 5 kilometers were considered. We identified area with homogeneous exposure to each pollutant, like this one that was built up. NO2 and O3 concentration. So if you look at this table, as you can see, overall concentration, cold season concentration, warm concentration, and this change, these different colors are for generic case definition, broad case definition, narrow definition. In any way you consider, and there is an increased case of IPF related to increased NO2 concentration. And this is age and gender, just the incidence rate, the comparison between areas with an average NO2 concentration above and below 40. So no association was detected between IPF incidence and PM10 and O3 chronic exposure. A marginally significant positive association was observed between IPF incidence and NO2 concentration, and we observed that for each 1 microgram per meter increment in the chronic NO2 concentration, the incidence rate of IPN increased between 0.4, 49, 0.60, depends from the way you use the definition, depending on the IPF case definition used, the monitor selection strategy for exposure assessment, and the season considered. So this study was the first one that suggested that pollution can play a role in the development of IPN. And probably the best way to study this problem could be to have a subject-specific monitoring of pollution. However, the advantage of the administrative data is that you have a large and unselected population to consider and to sample. Air pollution induces oxidative stress, telomere shortening, and cellular senescence, dysregulated fibrogenesis and inflammation. And this, you know that we consider IPF a telomere dysfunction that can be triggered by genetic and environmental factor and to develop the entire phenotype. NO2 exposure has been also associated with other respiratory disease like COPD and asthma, and traffic-related air pollution exposure increase the risk of post-transplant bronchiolitis or Breitling syndrome. So inflammation, oxidative stress, TGF, beta-1, profibrotic activity can play a role in aberrant wound healing with telomere shortening and develop IPF. So this was the editorial accompanying the paper with Bruno, who was one of the authors, that suggested that genetic susceptibility can play a role, and other things like pollutants, bacteria, virus, tobacco can be trigger of the development of the disease. And we know that probably there are many factors that can interact in developing susceptibility and vulnerability of patients for the development of IPF. And finally, I want to show you a very interesting study that is not still published, but I think it will be very soon, that consider nearly 500,000 samples coming from the UK Bank of biosamples and matched this enormous amount of data and information with patients who develop incident cases of IPF and try to correlate not only pollutant concentration, but also the risk of development of the genetic of IPF. So they had I cannot say exactly, but they had in the biobank a genetic evaluation of a risk score for the development of IPF that interact with pollutants. So as you can see, they divided in low genetic risk, medium genetic risk, high genetic risk, and there is a strict correlation between pollutant and risk of genetic risk that interact in the development of higher risk to develop an incident case of pulmonary fibrosis. Long-term, they conclude that long-term exposure to NO2, NOx, and PM2.5 were significantly associated with an increased risk of incident IPF in exposure response fashion. The joint effect analysis revealed that the association between air pollutant and the risk of incident IPF were strengthened by the genetic susceptibility to IPF, and they suggest that improving quality is helpful for reducing the incidence IPF, especially in individuals with high genetic risk. I will stop here and I take questions if there is any.
Thank you very much for your really very interesting talk. Professor Wells.
The microphone, please. Somebody's carrying the microphone somewhere. It's a lovely story. I think very plausible, isn't it, when you think about the rising prevalence of IPF generally in so many countries with rising pollution. Can you just clarify from the moment you measured the concentrations, how many years of follow-up from that? I got a bit lost.
In my paper?
Yeah.
5.
Yeah, I just wonder if that maybe understated the association, if we believe that IPF in many cases has a lead time, potentially 2 years before it develops. I'm impressed that you saw this with the follow-up of just 5 years.
We had 5 years before, as I told you, to avoid to have prevalent cases in, and we consider only 5 years of follow-up.
Yeah.
The thing I can tell you is that we also done another paper, epidemiological, although it's using administrative data on our region. And it seems that the incidence is stable over time, doesn't seem to increase over time. And in that paper, we studied 10 years of follow-up.
Right. Thank you.
No, thank you. Thank you, Arthur.
Sorry.
Valeria? There are probably effects that needs to be detected also larger population of 10 million.
Thank you very much, Sergio. I was shocked by your maps.
Yeah.
The maps, and you see the map of COVID-19 pandemic in Lombardia, the first wave. Is it possible to have a correlation between the incidence of the ILD and the incidence or the effect of COVID-19?
We organized with Professor Mannucci, that you know well, and Francesco Forastiere, an international meeting on pollution 2 weeks ago in Milano. And that was one of the main points of the discussion. The preliminary data from everywhere seems to support the idea that COVID can play a role in the severity of the disease, not in the incidence. This is up to date. Perhaps tomorrow it will be different, the situation. And it plays a role in as all viruses in the pollution, play a role in predisposing more people as vulnerable to the interaction with virus, and this is well known. And so the preliminary data coming from Italy, but also from other countries, seems to support at this time only the fact that probably enhance the aggressivity of a virus, but it does not seem that it play a role in the diffusion of the virus. There is no also basic science evidence of interaction like it has been for other virus between, for example, coarse or fine particle and the virus.
Okay.
Thank you.
What I'd like to say is that we should, I believe we should see the role of air pollution on IPF as to separate, let's say, the first one, on the one hand, we should see the causative, whether there is a causal relationship between air pollution and IPF, where the evidence is scarce and it's not so easy to prove it. And on the other hand, we have to, there is a lot of evidence and increasing evidence on the role of air pollution on IPF acute exacerbations. And symptoms. And we also perform a study in Greece. It is published in Environmental Health, and with a personal exposure assessment, and we have a double risk factor, an increase, 2 times increase in risk factor for acute exacerbation in the areas that are most polluted with particulate air pollution PM2.5, PM10, and also NO2. And as regarding the short-term effects, we also found strong correlation, strong associations with air pollution and increase in symptoms. And the other thing that I would like to say to, let's say something about also climate change. Climate change with desertification and also all these fires that we have around, and going to increase PM2.5, going to increase coarse particles. And so we might expect an increase also in at least in acute exacerbation of IPF. And I don't know whether we're going to see some increase in HP. I would like to have your comment, your opinion.
I have no comment about that. I think one thing we should discuss in the respiratory community is the impact of the war in pollution, because this will be a real problem. There is a recent paper published in, I think, Science Reporter, very well written by epidemiologists who analyze the effect that is very, is very large, and it depends from fire, for combustion, from water contamination, from possible radioactive lakes. So I think as a respiratory community, we should also do an action of public aware regarding this problem that is not still, it's so dramatic the war that probably this problem is not faced and discussed.
Okay. Thank you very much for your presence and for all your input. Have a nice day.
The European Respiratory Society is the largest scientific and clinical organisation in respiratory medicine in Europe, with a growing membership from over 160 countries. Bringing together healthcare professionals and other experts working in respiratory medicine, united under a collective mission to promote lung health and alleviate suffering from respiratory disease. Advocating to reduce the burden of respiratory disease in Europe and producing science and unbiased education to share with healthcare professionals worldwide. We seek to tackle the current challenges in respiratory medicine across 8 respiratory disease groups. At the heart of everything we do are our members and our patients. Promoting funding and helping to drive scientific research through a variety of activities to advance respiratory medicine. Funding vital research projects, recognizing excellence, sharing and exploring new findings, and publishing one of the world's leading scientific journals in the field of respiratory disease. We create unbiased medical education and continuing professional development under the leadership of world-renowned experts in their field, harmonizing the standards and practice of respiratory medicines across Europe, helping thousands of healthcare professionals to improve their medical knowledge and skills, offering access to the highest quality online materials, and publishing learned educational journals and handbooks. We share knowledge, promote collaborations and best practice through ERS events and conferences, increasingly investing in the latest technology to make cutting-edge education accessible and affordable to healthcare professionals worldwide. Across the 2 pillars of science and education, we are dedicated to encouraging researchers and healthcare professionals to improve their skills, increase their knowledge, advance their careers, and ultimately improve patient care. Our leaders and dedicated officers advocate for change in Europe on behalf of the society by raising awareness of lung health issues with politicians and the public. ERS and European Lung Foundation work closely with the EU and related institutions to ensure policies are based on science and patient needs. Through ELF, we work with patients, understanding their needs and hopes, involving them in research and guidelines, and supporting their active role in decisions concerning diagnosis and treatment of lung disease. ERS and ELF come together to provide support and information for patients, raise awareness about key issues affecting lung health, and campaign for healthy lifestyles and the prevention of disease. Each year, we host the largest gathering of respiratory professionals in the world at the ERS International Congress, a showcase of excellence for respiratory medicine. It's one of the world's major platforms for the release of new data. Additionally, giving access to live sessions and recordings to tens of thousands of virtual delegates, sharing new thinking and inspiring the respiratory community. The ERS International Congress is an essential ingredient for the advancement of respiratory medicine. The European Respiratory Society, supporting its members in advancing respiratory medicine and improving patient care, offering access to the highest quality unbiased medical education to all healthcare professionals around the world, raising awareness of unmet research and educational needs, and promoting lung health to meet the needs and hopes of our members and our patients worldwide. The European Respiratory Society. Every breath counts.
This year marks my first year as ELF chair. Unfortunately, it's been a year marked by COVID-19, relatively physical distancing, remote consultations and meetings. I know it's taking a toll on many respiratory patients, but we hope it will be different in the coming year. But it's also been a year that has revealed our community's resourcefulness. our adaptability, our innovation, our fresh ideas and approaches to deal with uncertainty. This is also true for the European Lung Foundation. In the past year, we have managed to get a new ELF chair in position. We have adapted a new strategy with 6 strategic goals: to be patient-led, to increase knowledge and understanding, to engage effectively, to have a strong voice, to ensure good governance, and to increase our resource and outreach. We have also modified the ELF Council so it's now a 50-50 split between EIS leadership and patients. This spring we launched our new website, which ensures better synergies and link with EIS web resources. Amongst other things, it has better usability and is more people-focused. We have also strengthened the visual content on the website to ensure a more diverse communication of contents. The website also contains patient input process details and a new section on fundraising. In general, the new website has helped us to strengthen our patient input. We have developed and focused our disease-specific patient advisory groups to better match the interest of patients and to strengthen the links and synergies to the EIS assemblies. This year, we have added 4 new patient advisory groups and giving us 13 in total. We have provided patient input to more than 35 EIS projects in the course of the last year, including 20 task forces and 15 TRCs. One of the new innovations that we introduced in the course of the last year is a format that we call the Patient Conference. The idea with the Patient Conference is to have our disease-specific patient advisory groups lead on defining the content and co-host the Patient Conference with EIS professionals. In February, we had our first Patient Conference on bronchiectasis, and in July, we had our second on long COVID. For both events, we had just under 2,000 registrations, with half attending on the day and many more watching the videos afterwards. This is a format that we plan on developing further in the coming year. Another innovation for ELF is the development of a fundraising strategy. We have developed documents and processes for driving our fundraising forward. Our first venture into fundraising was the Virtual Conference Challenge, which took place in conjunction with the 2020 EIS Congress and helped us to raise more than £4,000 for our Healthy Lungs for Life campaign. This year, we have launched the Take the Active Option fundraising campaign. I hope you join it. You'll find more details on our supporter section on our website, which is created to help income generation to improve lung health globally. This past year has been extraordinary in terms of developing and strengthening patient input through digital tools and platforms. We hope to develop this further in the coming year, but we also hope we get to see each other, to meet, to think, to discuss, and to develop together, because this is the essence of what ELF stands for.
The European Respiratory Society is the largest scientific and clinical organisation in respiratory medicine in Europe, with a growing membership from over 160 countries, bringing together healthcare professionals and other experts working in respiratory medicine, united under a collective mission to promote lung health and alleviate suffering from respiratory disease, advocating to reduce the burden of respiratory disease in Europe and producing science and unbiased education to share with healthcare professionals worldwide. We seek to tackle the current challenges in respiratory medicine across 8 respiratory disease groups. At the heart of everything we do are our members and our patients. Promoting funding and helping to drive scientific research through a variety of activities to advance respiratory medicine. Funding vital research projects, recognizing excellence, sharing and exploring new findings, and publishing one of the world's leading scientific journals in the field of respiratory disease. We create unbiased medical education and continuing professional development under the leadership of world-renowned experts in their field, harmonizing the standards and practice of respiratory medicines across Europe, helping thousands of healthcare professionals to improve their medical knowledge and skills, offering access to the highest quality online materials, and publishing learned educational journals and handbooks. We share knowledge, promote collaborations, and best practice through ERS events and conferences, increasingly investing in the latest technology to make cutting-edge education accessible and affordable to healthcare professionals worldwide. Across the two pillars of science and education, we are dedicated to encouraging researchers and healthcare professionals to improve their skills, increase their knowledge, advance their careers, and ultimately improve patient care. Our leaders and dedicated officers advocate for change in Europe on behalf of the society by raising awareness of lung health issues with politicians and the public. ERS and European Lung Foundation work closely with the EU and related institutions to ensure policies are based on science and patient needs. Through ELF, we work with patients, understanding their needs and hopes, involving them in research and guidelines, and supporting their active role in decisions concerning diagnosis and treatment of lung disease. ERS and ELF come together to provide support and information for patients, raise awareness about key issues affecting lung health, and campaign for healthy lifestyles and the prevention of disease. Each year, we host the largest gathering of respiratory professionals in the world at the ERS International Congress, a showcase of excellence for respiratory medicine. It's one of the world's major platforms for the release of new data. Additionally, giving access to live sessions and recordings to tens of thousands of virtual delegates, sharing new thinking and inspiring the respiratory community. The ERS International Congress is an essential ingredient for the advancement of respiratory medicine. The European Respiratory Society, supporting its members in advancing respiratory medicine and improving patient care, offering access to the highest quality unbiased medical education to all healthcare professionals around the world, raising awareness of unmet research and educational needs, and promoting lung health to meet the needs and hopes of our members and our patients worldwide. The European Respiratory Society. Every breath counts.